Welcome to APEC. It's March 15th, 2025, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody watching us on YouTube. So our schedule was Maddie Buchanan presenting on a new experimental demo of LENR, Bryan St. showcasing his new Pi 7 Inertial Propulsion Drive, Jarod Yates, as well as Dr. Matthew Szydagis discussing sample analysis for two separate samples of ARTS parts, as well as the St. Augustine and Roswell bounce site wreckage. So that was the schedule that we had lined up. Maddie Buchanan is not with us right now, so we're going to start out with Bryan St. talking about the Pi 7 inertial drive. And I should also mention that we may have more UAP sample material coming in later. That's something that we will kind of come back to. So we're going to take things a little bit fast and loose, but I am really excited. This is the biggest story of 2025 in terms of UFOs. And again, Jarod and Matthew Szydagis have done over a year's worth of work on this. They absolutely have just blown this out of the ballpark. So I cannot be more excited about it. After that, we're going to be hearing updates from lab partners and finishing off the event with an open discussion by conference attendees. Okay, so a couple of quick updates. Today's event, we are broadcasting on StreamYard through the Alt Propulsion YouTube channel. If you haven't subscribed to altpropulsion.com, please go to our website. I would love it if you were able to sign up for our email list at the website. Also, please subscribe to our YouTube channel. That way, when new presentations and new files are available, you will see them in your YouTube recommendations. I have been uploading all week. I'm going to be adding more in the next couple of weeks. We have lots and lots of material. Some of this is archival. Some of this is new material that folks have sent me. No one has seen this before. It's really amazing. So again, Alt Propulsion on YouTube, and make sure to visit our website on altpropulsion.com. So if you're watching on YouTube now, you can ask questions using the live chat feature on the right-hand side of the page. And we will try to ask them to our presenters depending on time constraints, also depending on if we catch them, because they do scroll up the side of the page pretty fast. You can always view conference replays, details, and speaker info on our website at altpropulsion.com. Okay, so I am super excited. I think it is time to rock and roll. I'm going to bring Bryan St. in. So Bryan, welcome, sir.
Welcome. Thank you. Appreciate you having me on.
Oh, absolutely. So let me bring in your presentation. So this is an inertial propulsion drive, and I think, everybody who attends APEC is familiar with this. What I love about your work is you do heavy duty, like, I don't know what you call it, industrial grade. A lot of people who build these, this is a mechanical device, right? And one of the problems is they shake themselves to pieces. And a lot of people build really small ones that will run for a couple of minutes and then they just fall apart. The stuff you're building, this is like commercial grade. So I'm really excited.
Yeah, I learned a long time ago that if you're going to build something that you actually want somebody to look at, you really don't want it falling apart in the middle of a presentation. So that's where we're at with this stuff. So, most everybody here knows me. I'm Bryan St. I've been working with propulsion systems of all different types for a long time, particularly with the inertial propulsion systems since right around 2019-ish. So today I've got a really short presentation just leading up to how we got to the Pi 7. And then we'll take a look at the Pi 7 itself. I've got it hooked up. It's behind me. It's ready to rock and roll. So we'll go there. So let's see. How do I do this with?
So if you put your mouse, over it, there's back and forward buttons.
Perfect.
Awesome.
Perfect.
Yeah.
All right. So again, anything that I'm going to show, I'm not showing you theories. I'm not showing you conjectures, and I'm not showing you something that hasn't been proven and tested. If it hasn't been proven and tested, there's absolutely no point. So as I've said before, I am not here to prove anything to anyone. Proof is done in the lab. Proof is done on the workbench, and then proof is verified out on the real world application. So right now, the Pi 7 is the latest and greatest. It's the biggest and best so far. It's totally incomplete, but it's starting to really come together with some serious performance edge over a lot of the other ones that I've had. So let's see. I wanted to say that, as our technology has been progressing, propulsion just hasn't. And that's, we all know that. That's why we're here. That's why we're all trying to work together to bring this stuff together. I see a lot of terrific designs out there that are absolutely amazing. I try to keep mine really, really simple, really down to earth, and so to speak, and something that could be repaired out in the field. I spent 40 years fixing all kinds of machinery, and as a full-time technician that way, I can tell you that if you can't fix it out in the field, it's not worth having a one of. So that being said, electric propulsion, it's really becoming the biggest thing. We keep seeing a lot of new EVs. Tesla's come a long ways. It's very unfortunate what we see going on with the trucks out in Europe with that whole issue, but we're starting to see some heavy trucks and stuff like that coming to electric propulsion here in the States. Let's see. We know that it's progressing into almost every area. We start to see some airplanes that are using some electric motors on them, and I think that we're going to start seeing a lot more electric propulsion systems as we get this stuff really working well. And that's not just me, that's a lot of other really great designs out there. Let's see. Aerospace. We're starting to see it move right into aerospace. As Mike Gamble has said, Boeing has played with that out in low Earth orbit for a long time, and we're going to start seeing, I think, a lot more of this. I'm quite sure that Elon Musk is quite open to a lot of this type of thing once he actually sees it producing enough power to be useful. We're entering that new age of propulsion. We're not really in it yet. This is an emerging field. As we know, that's, again, why APEC is here, to help the field emerge and become something that everyone can really appreciate and use. Most of you folks have seen my Pi system, have been here during presentations before, or watched my videos on YouTube. I do have a website that can link you to all of those videos at stclairtech.tech. And there are links to the YouTube videos, and I mirror most of those on BitChute as well. So the history of the Pi, in a nutshell, we started out with a duplication of a Thornson drive, the Ezekiel drive. Energy zone kinetic lifter is what Mr. Thornson called it. We built one, it worked. We built a better one. We ended up with one with 4 wheels, and by wheels, I mean the flywheels, the big gears that actually rotate, that you can see rotating. We built one with 4 of those. We walked it across the workbench. We saw it push up to 15 or 20 pounds of material out in front of it, just sliding it across the painted wooden surface. So we knew right then and there that we were definitely onto something that was worth pursuing. From there, we moved on into what we called the Pi, or the pulsed inertial engine. The only reason that we did a rename was nothing against Mr. Thornson, because I give him all the props in the world for coming up with this design to begin with. But we added some tweaks and some features that I'm sure that Mr. Thornson didn't think of, and we got rid of a couple that he was claiming to have used that I never could just make them work the way he said that they were supposed to. Let's see. All right. We are, okay, the first truly functional one was the original 2- and 4-wheeled Thornson replicas, like we just talked about. Here's a picture of all of those different units. The Pi 1, that was the very first Pi itself. It was running on a timing belt. The gears actually did not touch one another. Both of the wheels were turning in the same direction, and we were overlapping a double pulse ever so slightly to get a little bit better performance. This was the first one that was ever road tested. We actually put it in a motor vehicle, took it out on the highway, tested it with scientific and computerized equipment hooked to the vehicle's computer to watch engine load and how much engine load would go away, how much was decreased whenever the Pi was running. It worked every single time. So from there, we moved on to the 2, which was a stacked design.
And Brian, I'm sorry to sorry to bother you. You're getting some background noise, it sounds like.
Okay, I'm not sure why.
It's like 60 cycle hum.
Not really sure why I would be getting that. I really can't turn off the lights in here or it will get really dark. We can try that. Is that any better?
No. It just started.
Very strange.
Yeah.
Well, I'll tell you what. We're in the midst of a heck of a windstorm. So if all of a sudden I lose connection altogether, it's because the electricity went out.
Okay. You know what? I wonder if that's it. Okay. Well, sorry for interrupting, sir.
No, you're fine. I appreciate the heads up. Is this lighting okay, or would you like the other lighting?
Actually, I would say turn it back on. We'll roll with it. Yeah, it does. You know what? It's that 60 cycle. I bet it's a ballast somewhere or something.
It probably is. I mean, shutting that off turned off all the ballast here in this area, but the transformer that supplies this place is only 100 feet away from the backside.
Oh, there it is. Now it's better. Okay.
Terrific. We'll go with it. All right. So anyway, we went to the Pi 2. That was that stacked design. There weren't a lot of improvements other than we were using 4 weights total that were rotating, and we could offset them in different increments between the 2 wheels. We found out that there was a definite difference between something that would self-propel and move itself across the floor and something that would show the best improvement in a moving motor vehicle. At that time, we did not understand that. That is part of what we're going to talk about later on in this presentation. From there, we went to the Pi 4. The Pi 4 was back to the 2 wheels design. It was chain driven, both wheels going the same direction. Some major improvements. We changed the weights from just solid steel pieces. We ended up with hollow steel weights filled with steel shot, which acted like a dead blow hammer and took out a lot of the bounce. It also prolonged each one of the pulses, making it several milliseconds longer than it was previously. That was a huge increase in performance right there. And then we also added the speed control differential to it. The speed control differential, or the speed differential control, the SDC, that actually just boosts the speed ever so slightly during periods where the motor would be working the hardest. So it actually speeds up instead of slowing down right when the motor would be working the hardest, pulling the weights around and getting ready to actually produce that thrust pulse. We actually took that design and put it back onto some of the older designs and found that it improved each and every one of them exponentially. It was absolutely an incredible achievement at that point. From there, we went to a Pi 5. The Pi 5 never made it off the workbench. It really didn't. It worked great on paper. It worked great in computer simulations. And when we got it put together on the workbench, I said, this thing is too finicky, too hanky, just too many things that can go wrong with it. It might be something that we'll revisit later on, but at this point in time, I'm going to call it a non-functioning Pi system. We were able to get some good thrust pulses from it, but not on a consistent basis, something that we could actually put to use. So Very recently, we went on to the Pi 6. The Pi 6, you actually used a lot of the parts from the 5. We used the weights that were already built to be the dead blow design. And we used some of the brackets and some of the pieces and also at least one of the motors. This was the first design change, not a radical design change, but the first design change that we'd had in a while, because this one ran on 2 electric motors. They used 1 speed controller and then had separate speed differential controls that would bypass the speed control system and boost the speed at those moments when it needed it the most. That also combined with a brand new thing that we just come up with over the past year, 2024, is the quantified backlash drive coupler. It's a really fancy name, fancy term. Think of most everybody out there knows what a Lovejoy coupler is. A Lovejoy coupler will put an electric motor to, say a pump or a gearbox or something, and it allows no real backlash. It takes up the vibration, and it also allows for a little bit of misalignment. So the Lovejoy has been a very common thing for very many years. This built on the Lovejoy type of coupler, but getting rid of the rubber coupler in the center of it and allowing a quantified amount of backlash between the 2 halves. What that did for us was we basically now have 2 pies running next to one another, or over top of one another in this case, that run independently but together. So independently, each one of them creates a pulse. Each one of them is run by a motor that is separate from the other. Each one of them has its own speed control differential bump up. And each one of those cannot outrun the other one because of the QBD, the quantified backlash drive. That coupler was really the key to getting the same amount of power out of the system and getting rid of that pulsation that would drive you absolutely insane if you had to drive one of these for a long distance. We could actually measure the pulsation difference with meters in the vehicle. We could actually set the sensitivity so tight that we could see the engine of the vehicle and how it vibrated across the cylinders as they fired. And when we would turn on the Pi 6, as long as the everything was set properly, and it, in the end we kept it maintained at setting properly, and it worked very well. It would actually even smooth those pulses out, which was an absolutely incredible, eye-opening moment for me, because I never dreamed that it would actually make something that was already working work any better, just make it stronger. So that was never really designed to be a put in use unit. We actually put it out on the highway. We ran it every day for approximately 40 to 60 minutes every day, 5 days a week for about 3 months. And at the end of the 3 months, we showed no appreciable wear in any of the components. Everything was working really, really well. And I said, hey, you know, we're really onto something here. I like this. It's time to go big. It's time to build a really nice, large unit. So that kind of brings us up into the Pi 7. The Pi 7 is the first real redesign. We don't use any spur gears in it. Everything is chain drive, sprockets, chains, roller chains. It runs smooth, it runs clean, and it runs fairly quiet. It's not where we want it yet. It's still in development, but it's really come a long ways from that original Pi, the version 1. It's like comparing a modern Lincoln Continental to the first Model T. It's a huge difference. So what we did with that is we incorporated that quantified backlash drive into a stacked design. So we no longer have to have the motors running a chain that runs another chain with extra jack shafts and things in there. Just all that stuff just takes up power. It uses more power in the electric motors than it needs to. Every single thing in this is roller bearing. There are no dry slides. There are no just lubricated spots where something can move. Every single moving component is a roller bearing, right from the motors all the way to the very last of any of the weights as they sling around. We also got rid of the wheels. With those wheels, they're really not necessary. They were great for building the first prototypes because we were able to index. We take different designs, different numbers, change things around. It was terrific, and I think at this point we've pretty much outgrown that. So what I wanted to do is up the amount of weight that we were slinging on the ends of each of those planet setups, and we've increased that about 3 times what it originally was with the Pi 4 and the Pi 5. And now we're getting some serious power out of it. We're still having some issues controlling it, keeping everything synchronized. Just because it has so much more power than it did before, it actually draws less electricity because everything is running roller bearings, and it's making more power using less input power. The whole thing is running on a 24 volt system, the 24 volts DC with a 30 amp fuse, and I have yet to have ever popped a fuse. We could probably run that on a 15 amp, but I don't want to keep replacing fuses. So I guess at this point, we can take a look at it. We can it's behind me. It is set up. I'm gonna just move myself out of the way here a little bit. Let's get rid of the slideshow if we can. I'm not sure how we get rid of that. Remove from, there we go. Okay, so behind me we do have the Pi, pardon the noise, move the chair out of the way. We have the Pi 7. I'm going to bring it up a little bit closer to the camera. It's on wheels, so it's easier to move than the camera is. And again, we don't have any of those spur gears. If we had had spur gears, we'd have to have a large gear here and a large gear here and another large gear here. Instead, we've got roller chain. Everything is timed. The center sprocket is the one that is not rotating. That allows everything around it to rotate and keep moving in sequence, just as if it was its standard spur gear setup. That quantified backlash drive, we're playing with some different settings on it, but it's right here. It will only allow the two to separate that far. The reason that I've got it blocked so it won't go that far in this direction is if you look closely, these weights are still hollow. They're not filled yet. The weights on the bottom one are filled. So therefore the bottom one takes a bit more power to run than the top one. And it would actually try to outrun and it would almost lock up right against the stop. So I had to back that up just a little bit so that it would actually work a little bit better. One more difference in this one is we're also using 2 speed controllers instead of 1. The backlash drive part of it, the speed differential control has its own speed controller. So I can actually adjust how much boost it gets. So let's turn this on and we'll just watch it run a little bit. Okay. It's actually pretty quiet. It's pretty smooth. That's at a pretty low RPM right there. And now if I turn on the speed differential controller, okay, we're just starting to have a little bit of pull right now. I really don't want it to go over into the camera. I can bring that speed control up just a little bit more. And it is producing a lot of thrust. Like I said, the timing is still a little bit off from where I want it to end up. We're getting really close. We've got to get the masses finished up down here, get these and these to match each other weight-wise. I've got pre-measured amounts of shot ready to go in them. Everything is ready there. I just ran out of time before we were going to have this conference. And I wanted to get this out here and show people that we're still making some good progress on this thing. And I really do believe that by the time we're done, this one should nearly propel a vehicle down the road without the engine from that vehicle maintaining any power to the wheels. So in a nutshell, I guess that's it. I don't know if anybody has any questions or comments. Like I said, Tim, this wasn't going to be a real long presentation. Just a quick recap, and then we'll kind of show off the 7 here a little bit. So I guess that's pretty much what I've got for today.
Bryan, thank you, man. That is totally awesome. That is totally awesome. So let me ask, since we're doing demos, do you have any other devices that you can demo for us? I mean, that demo itself is amazing. So
I don't have anything set up right now for a demo. The Pi 6 was something really cool to watch run, but I stole the motors off of it for the 7. So I can't really run it.
Well, no, I mean, again, it was amazing to watch. The thing that I love about your work is it is heavy duty. It is large, right? You're using chain driven stuff. And yes. I mean, inertial propulsion has a really, really long history. I think a lot of folks aren't necessarily familiar with it, but like I learned about it with, I think, James Bootstrap Cox. And if I remember right, I don't think he's still with us, but if I remember right, he was doing like lawnmower engines, and he was trying to get them to lift themselves straight up, and he had kind of some results, but they'd shake themselves to pieces. So.
They definitely would shake themselves to pieces. The one thing that I kind of alluded to talking about in the beginning of the presentation, we kind of skipped over it because it's almost a subject all of its own. And this is something for people that are way smarter than me to contemplate a little bit. And that is the fact that this is using inertial resistance. Inertial resistance in its common nomenclature is simply the resistance of that inertia to change states. So if it's already in motion, it resists slowing down. That's all we're talking about there. If you recall some of our earlier projects, we had talked about something that we were noticing that almost seemed like an inertial Doppler effect, where once the unit was driving down the road, the faster it went, the more power it would produce. What we've come to realize, it has nothing to do with an inertial Doppler effect, which we really didn't think it did, but it was the only thing that we could think of to call it. That's inertial resistance. The faster something is moving, the more inertia is going in one direction, so it's got resistance to pushing back the other direction. We noticed that with the little Pi Mini. I'm sure that there are still videos of that on my YouTube channel. It was designed to be a demonstrator, basically a toy. And the really cool thing with that was that we could put that on some rollers and it would just rock back and forth. If we put it on a framework with some wheels, then it would roll across the floor. The only difference in rolling resistance was the weight, the mass. The mass added to inertial resistance.
Well, Brian, before we go any farther, I do not want to forget we need to give you an enormous applause. So let's do that. Enormous applause. Bryan St. Clair, everybody. Brian, thank you so much, man. Thank you. And
No
let me
problem.
apologize for interrupting. I didn't want to get distracted there, though.
No. That's fine. I'm easily distracted by anything shiny going by as it is, so that's not a problem.
Yeah, I love watching your stuff. I mean, it's again, you're building on kind of a legacy of design, but you are taking it so much farther, and it is so heavy duty, right? And that's what's required in this area.
It is.
And then,
It is.
so one of the things that I should mention is, like on the Alt Propulsion channel on YouTube, I've been dropping some shorts in there. I don't think I can pull it up quickly, but the Thornson Inertial Drive, that's another one that I think is really interesting. He put that in a canoe. There's footage from, I think, the 1970s. It's in a canoe because it's shaped the same at both ends, right? So they didn't want to do slipstick with the water. And you see him going across a swimming pool, and that's all inertial propulsion. Same idea that you're working with, but again, your stuff is, 30, 40 years newer. So
It's a little bit newer. We've got some newer designs and some newer concepts in there. I think what Roy did was absolutely amazing, and that's why we kind of followed in his footsteps to begin with. I found it to be absolutely amazing that it was that simple and that easy to build something that would work. The first ones that we built, and back to that speed differential control where we boost the speed during runtime, that was found by accident. Our very first unit ran on a flat belt. The belt had no grooves. It was just flat. And it would work, and then it wouldn't work, and then it would work, and then it wouldn't work. And what we finally did is I noticed it one time when my helper turned it on that the belt squeaked. And I said, we've got to tighten that belt up a little bit. And what it was is the belt was slipping at those points. And if it slipped and slowed down, it would stop making thrust. So what we did was we speeded it up at that same point, and that's where we got that boost in output power.
Oops. Okay. I actually, you know what? If you're okay with it, I have a couple. And I've got sound going in the background. Brian, is it cool if I put these up real quick? I will.
Sure.
I'll just do a very quick share. I only have
absolutely.
two that came to mind. There are a lot of previous attempts out there. What I don't have that I feel really depressed about is I don't have anything from Bootstrap. I don't have any of his stuff. I don't even know if he filmed it. So this is the Thornson. Hopefully you guys can see this. Yeah, this is the Thornson inertial. Here it is. Thornson Inertial Drive.
Here, the Thornson Inertial Propulsion Drive powers a canoe in a swimming pool.
Okay, and again, this is a canoe, so it's the same drag in the water on both sides. You can see he's not paddling or anything like that. So in the center of it, they have a box with an inertial propulsion device, and you can kind of see it there. And basically, it's just like an off-center rotator. And I'll run through that one more time. So this is an example. I look at this as a proof of concept from the 70s. And you could say, okay, well, this is only slipstick technology, right? That's what the critics say. But hey, if that's the case, you can still use this for watercraft because that's what he's doing right here. So,
That's part of what we're talking about with our inertial resistance is that this should work regardless of any media because of the mass creating inertial resistance. If I took this right now and put it on wheels, it wouldn't go anywhere. It can just barely move this 300-pound cart. But
this one, if I could jump in, this one is, I just want to show this really quick. Again, these are super short. This is out of Russia. This is Dr. Gennady Shipov. And he did not build this device, but he used this as a proof of, he basically does work in torsion theory, and he came up with a mechanical variant of that. And so this work, this one interests me for a couple of reasons. It's on a greased surface. Again, they're trying to get around that slipstick complaint. And this one's a little bit more similar to yours, I think, in some ways. But
in some ways, it is. If you search back through the archives on my YouTube channel, I've got that one. I've also got the skeletal version of that where you can see the workings. The very first one was actually a wind-up. It worked on a wind-up motor, and it would produce its own thrust.
Okay, you know what? I'm just looking. Okay, I can't find it. I can't find your YouTube channel. Okay, well, let me. You know what? Here, let me. I'm going to stop sharing. There we go. Yeah. Well, so guys, you know, Jarod, David, Drew, Mark, you guys do you want to jump in at all? Okay. Yeah. Well, yeah. So Bryan, I guess the question would be, what comes next with this?
Well, what comes next is we're going to get the timing correct on the speed differential control. We're going to get the weight added to the masses. And what we may do, the length of this planet right here was actually an experiment to see if we could make it shorter in relation with the overall size. It does work, but I think that if we made it almost twice as long, and obviously it's going to make the footprint a little bit larger, but I think that is going to be stronger yet.
Okay.
Once this is up and operational, we will be road testing it. There'll be videos. It's going to be something.
Yeah, that's exciting. And yeah, and if you want, you know what? Let me hunt for your channel real quick. Drew, you had something? Oh, you're muted, Drew. But actually, you're not muted. Your mic is not working. I think, yeah, Drew, I think you have the wrong mic selected. I think that happened before, too.
So I have a question. I'm just curious, how could this lead to a device that flies through the air?
All it needs is a set of wings.
Fair enough. Okay.
I mean, literally, if you think about it, the only reason that we're limited with plane propulsion in aerospace is because the engines run out of air. Once there's not enough air to complete the combustion cycle, the jet engines stop working, and then you're reduced to having to use rockets or whatever. If that same plane could switch over to inertial propulsion, it could keep spiraling upwards until it reaches absolutely no resistance from air. And then the faster it goes, the more powerful it's going to get.
Bryan, can you hear me now?
I can.
Oh, excellent.
Yeah.
First of all, amazing mechanical. I mean, I'm a mechanical engineer, aerospace, and I love to see machines spinny things. So, kudos.
Thank you.
I just don't understand where the momentum's coming from. Are you stealing it from the rotary motion?
We're stealing momentum from the rotary.
Okay, so you're converting rotary momentum
right
into
linear momentum.
Linear momentum. Okay,
Correct.
Fair enough.
So this is the operational side of the unit. So once it gets to this point, that's when the mass swings out. It will not only increase the size, the size of the diameter,
Radius, yeah.
but it also impacts here. Every time there's an impact, there's a pulse, and that's where the shot inside there takes over and increases the length of that pulse time. And then when it comes around to this side, now it's pulled it back in. We've changed our thrust outwards to thrust towards the center. We're spiraling back in towards the center. When this same one gets right here, it's moving forward, even though it's behind it. It hits another stop. So there's actually a secondary pulse. So each of these weights not only converts momentum, it also creates a pulse that is its own momentum generator, twice per
How does it-
revolution. So that's actually 4 pulses per revolution per segment.
How does it not get a counter against the rotating pinion?
There
as
is
it
a
swings
slight
in?
there is a slight reversion. Reversion has generally been half of output or less, and that's where we're talking about the inertial resistance, because if you've got something that outputs 5 pounds of thrust forward and 2 pounds of thrust backward, you might notice that it's pulling harder in one direction than the other, but it's really not going to go across the floor. You know, if you put it on wheels, it's going to sit there and it's just going to vibrate itself to pieces. But
Yeah, but if you're
you put
stealing
that,
momentum from the forward swing, you're also stealing momentum from the reverse of that swing.
Well,
Right. You have 2 different efficiencies in your rotary inertia conversion.
oh yeah, absolutely. And
Do
then
you have more efficiency in the forward swing than you do in the bring it back in swing?
I do. There is more efficiency out here than there is there, but it's only to a magnitude of about half more.
yeah. So, and actually, in a minute, I'm going to put up the St. Clair Tech YouTube channel. But yeah, I had a question though, Bryan. So,
Sure.
one of these devices traditionally vibrate a lot, and when I saw yours, when you were firing that up, right, it has that vibration. I kind of think of that, I might be wrong, like a 2-stroke engine, right? Those things shake like crazy, but as you add more pistons, it smooths out. You get to like a V8, and back in the day, V12s were really popular, and those were super smooth. So could you do this? Could you, like, once you kind of, like, once things are further along and it's more perfected, and you're like, okay, here's our thrust, it's predictable. Could you add more arms and put them out of phase and do basically like a V12?
Absolutely. What you need to do at that point is overlap the pulses. If anybody understands diesel technology at all, diesel engines they're basically like a gas engine, but they don't use spark plugs. They use compression to ignite a fuel. Because there is so much compression, they are very, very prone to harsh vibrations. The biggest issue with them is even numbers of cylinders are harder to control the vibration of than odd numbers of cylinders. So a 3-cylinder diesel engine actually runs smoother than its 2 or 4-cylinder counterpart. And again, it's just overlap. That's all it is. So that's what we're kind of doing with that speed differential control, and then the backlash control on that as well, is we're getting some overlap without affecting how the other one works.
Okay, so let me do this. I want to share St. Clair Tech channel, and I'm going to drop this in there. And this was painfully difficult to find. YouTube does not like this one. I think it's the name. I think it's because there are no spaces in it. But
yeah, probably.
yeah. So you know what? Before I go any further, I'm going to drop this bad boy right into comments, so that people could see. And please subscribe to Bryan's channel. This should be 143 subscribers. Let's get this way up there. It should not be difficult to subscribe, because he is not posting. He's putting up a video every month or so. So you're not going to be overwhelmed by stuff. So click. What do they say? Smash that subscribe button, and I'm going to keep the sound off here. So you were putting up videos. So I think this looks like this is the one you're testing now, right?
That is the Pi 7, just one rotor on it. It's just one stage. The first stage was put together for the most part. And what we did was I put that on a gradient so that I could get rid of the reverse pulses from affecting a scale. I wanted to use just a cheap scale. I didn't want high tech. I've got the high tech stuff. I've got Newton meters and force meters. I wanted to see in real time what the pulses actually look like. And you see it bouncing That's because it's a spring scale. That's the only reason it's bouncing. So what we were getting there is in the forward direction, we were getting about 20 to 22 pounds of thrust most of the time, depending on the RPM. And we were getting about 8 pounds of thrust in the reverse direction. So less than half. We're more than halfway to making forward thrust than we are in the reverse direction. It's still enough reverse direction that we have to have a lot of weight, a lot of mass for it to sit on to make itself actually self-propel.
And I'm just running through a few of these tests in that way. And these are getting older as we go, so we could see it's more rudimentary there, just so people know. It looks like the same device, but you haven't painted it yet.
Right. Yeah. It's the same device. We were just barely getting it put together at that point.
I have a question. So I may have missed this because I missed the beginning of your talk. But so what is timing? What is controlling how the that mass on the outside like rotates outward versus inward? Is it just freely allowed to rotate, or is there some gear in there?
No, it's all roller chains and sprockets. So there's a sprocket that's stationary in the center with a roller chain running on the back side of it, and then running on the front side of the outer sprockets. And that keeps everything rotating the way it needs to. So it's absolutely controlled. There's nothing left to chance on that one. The only thing that's not controlled is that swing right there. That swing is entirely controlled by the speed of the rotation and the change in rotation speed itself. You can see in that video, it's pulsing in both directions pretty hard. And we got rid of that by getting the second one on here. We don't have that harsh back and forth pulsation, but we don't have enough mass to watch it go across the floor. Plus this cart, the wheels on this cart, at this weight, take 18 pounds of thrust to start it moving across the floor. It's designed to be a stable work cart, not a propulsed device, you know. So it works great in one place and not so good in the other.
So I'm highlighting, let me see if I can do this correctly here. Let me zoom in here a little bit. Oops, maybe that's too much. There we go. That is where people need to be. And again, I will drop a link back into chat for that. And so if folks are watching this on YouTube, those chats are actually stored in YouTube. So, okay, so let me do this. I'm going to stop sharing. I'll bring it back down and I'll drop that link back into chat.
You can also get it right from my website, which is www.stclairtech.tech. So there are links there to the YouTube channels. There's a blog that kind of describes the steps that the painful steps that we've gone through to get as far as we have at this point.
Okay, and you know what? Here, let me put this up too, and let me make sure it's okay. Yeah, that's zoomed in 100%. And so just to kind of highlight for folks, they can see you've got lots of links to lots of projects. The blog updated February 16th, so you were staying on top of this. This is not like a dead website. This is actively. And just to scroll through.
And for those of you that like to see UFO pictures, I spent some time at the St. Lawrence Seaway over the last couple of years, and you can take pictures in broad daylight over the Seaway. And a lot of times you'll see, once you zoom in, you bring your pictures back, you put them on the big screen of a laptop. You can see like a helicopter off in the distance. They're pretty plain to see. But what was really cool is that we caught some things actually phasing in, phasing out, and moving in ways that they never should have in broad daylight. So they're on there too.
Awesome. Yeah, and again, I would recommend that people visit this. I'll read out that it's stclairtech.tech, right?
Yes.
Okay. Yeah, and I probably shouldn't go through all these. I will get myself lost. Let me drop that link in there, though. stclairtech.tech. Okay, there it is. So that is in comments, too. So anybody who is watching this can view those. And you know what? I do want to, let me click on that one. Okay. So that's just a mock-up. It's to kind of show people part of the idea.
That is a mock-up. of a trammel, one of the original three-piece trammels. It's a six-sided, three-point trammel. It was originally invented and called the do-nothing machine because nobody could figure out if it was worth trying to use. It was a long time later before the two-pointed one on four sides was found to actually be an ellipse generator, and you could put an arm on it and draw a perfect ellipse every single time. I said, you know what? That sounds like what we've got right here. It's a do-nothing machine that actually does something. That's the two, the Pi 2, and it's moving across the floor. That's a pretty rough concrete floor besides.
Yeah, and I think the important thing for people, and we have a lot of new folks with us, is you have been working on this for a long time. You are building on a legacy that goes back decades, and you are taking this a heck of a lot further than it has gone before. That, and again, you're doing like industrial grade engineering, right? This is heavy duty, and that's what's required for this, you know? And I mean, when people think about devices like this is kind of in my own head, they should compare this to an engine, because it really is, right? It's a propulsion engine. And so you're building them like an engine. It's heavy duty.
Absolutely. I've started out thinking of them as more of a transmission, something to go between a power generator and the final product, but it really is more of an engine. That's why we call it the PI, the Pulsed Inertial Engine.
Yeah. So again, stclairtech.tech, and there are
that fella
lots
right
and
there.
Lots.
If you go back one picture, that fella right there, his name is Tokyo Muramatsu. He lives in Japan. He does not speak English well. We have spent a lot of time corresponding back and forth. He is the first one, absolutely amazing, to go to his website or his YouTube channel. There is a link to it. I cannot remember what it was called. There's a link to it on my webpage. He was the first one I ever saw. He rode one of those across his shop floor. I was jumping up and down when I saw that.
I believe you have video. I don't know if it's on the website. I think you have video of. Okay, well, I'll just scroll through some of the photos. So again, very heavy duty, industrial grade. And there's Ross Small. Ross demoed this one in fact, that is APEC. You know what? It's a screenshot. Okay.
Yeah.
Yeah, Ross is a wild man. I think we all love Ross.
He's a great guy.
Okay, so yeah, let me stop sharing that, and we're almost at the top of the hour. Do you guys have any more questions for Bryan? And again, Bryan, thank you so much for sharing. And you are more than welcome to come back anytime and share updates with us. Lab notes, or that. If you have more presentations, anything along those lines.
Okay, perfect. And I try to have most of the questions answered before people ask them. I really do. There's just so many little things that make this not work that I would rather explain why it does and what not to do than to wait for somebody to ask the question, and then you have to stop and think about it and answer, and it sounds like you're making it up off the top of your head.
Well, and I mean, this is just me, right? But like, I'm a history buff, and the fact that you're continuing this tradition, this path of research, I mean, so many people have started and failed. So many people have started and run out of time and money and resources, and you're making it happen. And so, like, in a very real way, you are keeping the dream alive, and that's amazing.
We're trying like heck anyway.
Okay, well, yeah, I think that we're just about there. So again, stclairtech.tech, and then I dropped the YouTube link in, and I just lost it again too. So we'll have to do a better job of that.
If anybody comes up with questions or comments or anything, there's a contact form on the webpage where you don't have to even put your real email address in there if you don't want to. It just needs something with an @ sign in the middle of it.
I have you in the labs page on the Alt Propulsion site too.
Okay, sure. I mean, either way, it doesn't matter. I'm open to comments, suggestions, concerns, critique. Don't flame me or you'll get blocked. That's all.
No, I'm in that boat too. Yeah, especially right now, it's all politics online. I'm like unfollowing people left and right.
Yeah.
So awesome. Okay, well, I think we're about 3 minutes from the top of the hour. So, guys, do you want to? Why don't we do this? Why don't we put our hands together and give Mr. Bryan St. Clair another giant applause? Bryan, thank you so much. Thank you so much.
You're very welcome. Thank you for having me on.
Okay, and I'm going to take everybody out except for Jarod Yates because we are an hour ahead, and so my schedule is totally off. How are we doing, sir?
Hey, Tim. Doing well.
Arts Parts Part 3. Okay. So this is the main event. If I could set this up for people, you have flown all over the country. You have worked with a ton of PhD scientists. You have worked with several research labs. You have hundreds of photos, videos, close-ups of several different parts, not just arts parts. There have been 2 different samples that you've looked at, as well as there's the Frank Kimbler bounce site stuff. There's Dalnegorsk in Russia, and that's crash data that we received. And then I believe there's the St. Augustine wreckage that Steve provided us. So you are the number one world's expert on this. And like I have said before, I believe this is the biggest UFO story of 2025. Yourself and Matthew Szydagis are spearheading this, and this is all based on your hard work. So thank you, man.
Thank you, Tim. So I know a lot of folks are eager for this, but first I need to start you all off with a 5-minute story of what's taken place recently. So a few months ago, I met some people that were willing to join forces on arts parts testing. One had multiple pieces and wanted to collaborate, and another had lab access and the expertise for exactly the tests we needed to do. This is a dream come true. A week later, I connected with someone else who's done some serious implant sample analysis and who also happens to own some UFO fragments that he personally recovered in 2011. So with all of this in place, I got the arts parts and the San Augustine samples tested at a top tier lab. I drove thousands of miles because flying wasn't an option. Arts parts is already linked to 2 air crashes, one of those being the Mantell incident. So yeah, no flying for me. I spent hours and hours, days in the lab, working shoulder to shoulder with these scientists. We were gathering the best SEM and atomic level TEM pictures and data that on samples that I've seen to date. The sample owners, though, were not present for this for multiple reasons. Then came the trip home. My life was seriously threatened on the drive home. I'm not going to go into a lot of detail on it here, but if you want to know more, I posted a story about it on Reddit. Nutshell is that there was a 15-minute-ish long car chase through desolate, mountainous, icy roads. And just a few minutes after that was over, there was some hovering lights above my car in the middle of absolutely nowhere. It was as sketch as can get. So that said, this work is not for the faint of heart. So once I got home, I started going through all of this data that we had collected. For months now, I have been just day and night, every single day, I've been going through and pouring through this data and going through white papers, trying to see what could possibly relate to this. So a few weeks ago, as I was getting the APEC presentation here all prepped, I gave the arts parts owner a heads up, not our arts parts, but the other new samples that we tested. And then I beta tested a couple of these slides on Reddit, and it blew up really fast, like hundreds of thousands of views in a few days. And then came the miscommunication, the phone call. The sample owner requested that I pull everything down and that I don't use any of their images of their samples because, in their view, peer review is the only valid way to present this. Arrow and Oak Ridge botched their report. The full Oak Ridge report isn't even up for real peer review because we only have a whitewashed version that's a fraction of the original size. And for anybody who's been following my work, you know that open sourcing is very near and dear and at the core of what I believe, but it's kind of naive. It's how I've gotten this far. Some of that data, I already leaked it out there, so it's already out there. I already, though, deleted those posts. Like, while I was on the phone, I was deleting the posts. I don't want to do wrong by anybody. And I had to remove 100 images of their samples from this presentation. I had to gut this presentation completely. Still got some pictures of the Falcon space sample, but we need to give the peer review the chance that it deserves and allow these scientists that are putting in the work to get the credit that they're due. And that's peer review is pretty much the only possible way that we're going to be able to legitimize this sample to the degree necessary to be able to take on Oak Ridge's report. So I'm not going to share any samples or any images of any samples that I don't own. But I still am going to share my observations, you know, what I see, what I think I see. I'm an amateur, so take what I say with a grain of salt on this, because material science is not my expertise, though I am learning very rapidly that it is a very complex field. Yeah, so I'm going to break down my analysis. I'm going to reference the key papers. I'm going to highlight some of the overlaps between other samples and our sample, just highlighting what's in our sample that I feel much more confident now would be in multiple samples. Yeah, the level of technology that's present in this material is unquestionably advanced and pretty I'm sure did not exist in 1996 or earlier, as the Dalnegorsk may indicate. That said, let's go. So let me get this slideshow going. All right, just to recap for everybody, I'm gonna bring up to speed real quick on what the arts parts history is here. So as the story goes, 1947, we get a crash. Some people call this the Roswell sample, but there was actually multiple crashes in the July 1947 timeframe within days of each other. This one was the White Sands crash. The original owner, we're going to call him grandfather, he's on the scene doing the crash recovery process. While he's there, he manages to sneak off a couple of pieces of the underside of this craft. He doesn't say a word. He keeps this all under wraps, keeps it in a shoebox. And then on his deathbed in 1974, he gives custody of this shoebox to his grandson. And then this grandson, after having owned these things and tried to do stuff and failed at getting any answers with it for a long time, he ends up giving them over to Art Bell and Linda Moulton Howe in 1996. Over the course of a few months, he sends 5 letters, and with some of those letters, he sent some packages, and in those packages, there was multiple samples. Then fast forward from there, lots of testing was done in between then and now. In 2024 of April, one of those bigger piece samples eventually made its way over to Oak Ridge National Lab, and they published a classified report. And then fast forward to June, our team gets our own little tiny piece from one of the scientists that had held on to it during that last, since 1996, that it had been going to a lot of different scientists, and one of them kept a little piece and held on to it, and eventually it made its way into our hands. So now we have a sample. 2 days after I gave my July presentation, which was about a week after we got the sample tested, that's when Oak Ridge released a 10-page report saying this is a nothing burger. Nothing to see here, guys. Okay. Then, this year, we have 3 more arts parts samples that are tested. Hopefully, we will see some answers coming out of that in the very near future. I say very near. I don't know when they're going to publish their stuff, but I'm hoping that it's going to be sooner rather than later. So here's an overview of what I'm going to give you in this presentation. We have 3 additional arts part samples were tested. This is a really big deal, even though I can't share much about it. I'm going to go over the scanning electron microscope, the electron dispersive spectroscopy, and the transmission electron microscopy. You see a lot of cool stuff when you look at these little things really close up. There was some weirdnesses in the scanning microscope that confirmed some things with what I've seen in our sample. There was probably the most important thing. The slide, there was 1 out of those 100 that I got rid of that breaks my heart to get rid of, because in my mind, it's at least a steam and barrel, if not a smoking gun of advanced technology. Nanometer sized things that are indicative of high engineering and high technology, which was really interesting, because back in November, I got a chance to talk to Eric Davis while he was presenting at Seoul, and he brought up this thing called programmable quantum matter. I'm going to get into it. He also talks about quantum dots and in his DIRD, which is pretty interesting. I'm going to go over some of those as well. I'm also going to talk more about the whiskers that we've seen on our sample. I'm going to go over the similar craft, talk about Ubatuba and how maybe that relates, talk about the 1986 Russian Roswell event called Dalnegorsk. I'm going to go into the Quincy St. Clair, not the previous speaker, but Quincy St. Clair patent that seems like it may have some overlaps. I'm going to talk about the nanowire that's on our sample and all the possible things that it might be doing. Then I'm going to go into the engineering stuff. Can we actually maybe reproduce this ourselves? As well as the fact that we got ourselves a terahertz laser, which is pretty awesome. And then I'll end it with a good transition into the isotopic stuff that the next presenter, Dr. Szydagis, is going to go into. And I'll wrap it all up for you with a summary. All right. So I do apologize. I've had 2 days to put together this presentation. I have not slept much, so it is going to be a little bit rough. I'm just going to apologize in advance. So scanning electron microscope, you're looking at stuff really close up. In that we see, in that I saw some thickness measurements of magnesium layers that I now feel more confident on what the thicknesses of these layers are. I would say it's about 150 micron average layer for the magnesium zinc layers. Also, important takeaway is there's these rings of the microspheres that rupture. And they seem to have, not all over the place, but in enough spots to make me think there might be a pattern there. They seem to be arranged in rings. And the diameter of those rings may correspond to some far infrared low terahertz frequencies. Here's a zoomed in picture of Falcon Space's arts part sample, where you can see some of these microspheres. You can see how there's kind of a ring there in the center that's attaching them all. That's not normally there with most of these things. That's just helpful for this picture to be able to show you the arrangement that these things are forming in. In another scanning electron image that we have for the Falcon Space sample, here you can see these things have ruptured all over the place. Like most all of them have ruptured at a fairly significantly large size, anywhere from 20 to 40 microns. That's a really important piece of information there, that you're seeing the smaller ones have not ruptured, but the larger ones have ruptured. That indicates a process is taking place. Also in this image, though it is somewhat difficult to see, there is a ring pattern of the ruptured spheres. On the left side of this image, you can see our EDS, where you can see the composition of these things. And this is, I've zoomed way in and it's super blurry, I know. That is one of the ruptured spheres that hasn't ruptured as much as the ones that you see on the right. It is in the process of rupturing, which once again, processes are important for understanding how something might work. In that image, you can see the turquoise is zinc, the yellow is lead, and then the green that's not set at the bottom, the green is oxygen. So we can see in the smaller unruptured ones in that left image that they are mostly composed of zinc. And sometimes that zinc gets oxidized, and it does seem like there is some lead present around it. And you can also kind of tell that these things are hollow inside, or if they did have something inside, it is all gone. Here is some similarities to some other zinc magnesium alloys. In this instance, we can see some nanoparticles of zinc. And you can see how they arrange themselves in a circular pattern like that. This is just somebody else's paper from some other experiment they were doing. This is just an interesting other picture of what a zinc microsphere kind of looks like. And if you look at the scale on that, it's kind of hard to read. It's a little blurry, but it says 20 microns in the lower left side of those images, which is somewhat in the ballpark of what we're seeing in ours. So that's interesting. This slide, once again, it's a little bit rough. I'm not going to go into the exciton polaritons, mostly just the plasmons. You may need to understand and get just a little bit of background on what a plasmon is, because it seems like some of these things might have plasmonic capabilities. So a plasmon, nutshell version, it's just an oscillation of the electrons that are the conductor electrons in a metal. Most of the time, the frequency ranges are in the UV, but sometimes it actually does come down into the terahertz in specific applications. That's about all I'm going to go into on that one. All right, so in the center image here, you can see a 20 nanometer scale. So we're looking at much, much smaller than 20 microns, 1,000 times smaller than 20 microns, right? This is like a transmission electron microscope TEM image here. And you can see the sizes of those dark things is somewhere in the ballpark of 10 nanometers, give or take. That is not a picture of Art's parts. But if one were to look down at the small scale, one might see grains that are small like that. And also arranged in ring shapes. Well, this is interesting because when you arrange zinc grains at just the right spacing apart from each other, they actually can create a waveguide of plasmons, of these waves of electrons. That's very interesting. It may not actually be going on in the sample, but the sizes and the spacings of these things suggest to me that it's worth further inquiry. On the right side, you can see I have a picture of the Oak Ridge National Lab Report picture, for whatever that's worth. And that is a much, much zoomed out picture. It is 200 microns compared to the 20 nanometers of the center image. But in that Oak Ridge image, you can see all of the bright pink spots. That's all the zinc. And since we know that it's 150 micron average thickness of magnesium, you can see that this is actually a lot of layers stacked atop each other. This is not just like one single layer. And you can see that it appears as though the distribution of the zinc in the Art's parts is, it alternates. It's like, it's there for 2 layers. It's not there for 2 layers. So that's interesting. Probably a process taking place. So I said a little bit of stuff about terahertz. I'm going to have to give you guys a little bit background. Most people may not be familiar with what terahertz are. So you can approach terahertz from the bottom up or the top down frequency wise. You can approach it from the RF side and you can get into like the hundreds of gigahertz, not quite the terahertz, or you can approach it from the optical side with light and you can try to bring it down, down, down and try to get down there. But there's this range of 1 to 10 terahertz that's really, really hard to get to. And that's unfortunate because there is an absolute megaton of magic that happens in that band. So 1 terahertz is about 1 picosecond or 1,000 femtoseconds. 10 terahertz would be a tenth of that, 100 femtoseconds. In this magical range that we're going to keep an eye on of 3.2 to 5.6, that would be somewhere in the ballpark of 180 to 300 femtoseconds. The wavelength of this, we're looking ballpark 30 to 300 microns in free space. When you actually go in materials, it can change that number a lot. But so in the magic range, we're looking at somewhere between 56 to 94 microns. Black body radiation. This one's kind of interesting. So this is heat. Black body radiation is heat, right? You're constantly emitting black body radiation from your body, and that's why you can get picked up by a thermal camera. Well, that thermal camera is picking up some of these frequencies. It's just a much, much higher terahertz that it's picking up. So down in the 150 to 270 Kelvin range is where we're looking at for that magic window of terahertz we want. And it turns out you can convert, sorry, I meant to say you can convert terahertz to temperature, right? Because like I said, it's heat. And that would also correspond to anywhere in the ballpark from -4 Celsius to -120 Celsius, thereabouts. Room temperature, you're somewhere around 300 Kelvin, which would be 6.2 terahertz. In a little bit, I'm going to go into the whole temperatures that it looks like is pretty regularly observed on UFOs, which happens to be right smack dab in between that 3.2 to 5.6 terahertz. At -50 degrees Celsius, we're looking at halfway between -4 to -119. All right. This one's going to be just a little bit out there. I was debating even leaving the slide in, but so some folks have talked about terahertz in completely different applications. Travis Taylor was talking about cow blood. There's this stuff in cow blood called albumin. Well, there was a study done back in 2009 that was noticing that some weird stuff happens in cow blood at, once again, in this magic window range frequency. And yeah, weird stuff happens to cow blood, according to Travis Taylor, and there might be a relationship there to UFOs. Additionally, terahertz in the biology realm, it's its whole niche. So microtubules, the cytoskeletal structure that holds your brain cells, your neurons together, also what Penrose says is where your consciousness is. It turns out you can really mess those up with terahertz, so keep your skull away from any terahertz sources. Additionally, DNA, the little hydrogens on your DNA start wiggling at this stuff, and so terahertz can actually unzip your unzip your RNA. Yeah, so there's some interesting relationships in nature to specific magic window of terahertz. That's all I wanted to say with that. So the temperature study that I was talking about, I was saying it was about -50 degrees Celsius. Well, first study that I came across was the 2013 Agudia UAP. SCU did a study on that. They saw in their study, they said that the whole surface of that craft looks like it was about 105 degrees Fahrenheit. That's a lot hotter than -50. But the ambient air was only 80 degrees Fahrenheit. So whatever that thing was, it was warm. But according to this study that was just put out at the end of January, that is probably one of the largest UFO studies, at least the largest laundry list of authors on a UFO study that I've seen to date. In fact, the following presenter is one of the authors of that study. But in that study, that's where they're saying that it seems as though very, very cold temperatures are actually associated to UFOs. This is a very important deal that we have whole surface temperatures, because it's gonna guide a lot further research into this stuff. Also, it does tell us some other stuff here, that in the cases where people have gotten like sunburns from UFOs, that is indicative that maybe some weird stuff is going on regarding any warping aspects. Maybe. All right, this part was pretty exciting. So story goes, I go to Seoul and I get the chance to ask Eric Davis a question while he's on stage. I'm so happy, right? This guy worked with Puthoff for years and years and years, and Puthoff was the main go-to guy for testing arts parts for Linda. So the chance to get to ask him about materials testing, very rare opportunity. Whatever he can, say without getting in trouble. So I just asked him, what can you tell me about materials tests that you've seen that are interesting? Here's what he said. He said, we haven't been able to figure out their technology. The physics, engineering, the manufacturing technology just doesn't exist at this time. This is a couple of months ago, by the way. He says, we're just barely scratching quantum materials now and how to create, this is the money, programmable quantum materials. He goes on, but that was something that came out of this whole thing with respect to some of these aerospace companies that he was interfacing with. Aerospace companies. That is, they made some very interesting discoveries in the advanced material science aspect of the hardware that was recovered. If you look at that lower right image there, you will see one of the first pictures that comes up if you do a Google search on programmable quantum materials. That picture is of some really fancy stuff where you're basically etching into graphene, and you can etch shapes into it, and those shapes are going to confine little packets of electrons and make them do some funny stuff when they're confined. I include that slide because I can't include a different slide. So Eric Davis, he wrote a DIRD, a defense intelligence document, back in 2009, 16 years ago. In that document, he's got, once again, some relatable to arts parts things in it. He's talking about nanowires with programmable matter, programmable material. He's also talking about quantum dots, which is also a very interesting thing with regards to arts parts. He says that quantum dots can actually do a whole host of magic things. They're not just little light capturers. They can do a whole lot of magic. One piece of magic, I said they're at the bottom. They can change the optical, electrical, thermal, or magnetic properties depending on how you tweak them. That's a lot of functionality for a little nano bead. One of the more interesting things I found out about quantum dots is you can use them to make coherent terahertz. That sounds useful. In fact, you can make a quantum dot that can just absorb the natural background heat, black body radiation heat, and it can emit coherent terahertz on demand. That's amazing. This is a thing. No, that's a 4-year-old paper. No idea that this is a thing. You can take heat and convert it into coherent laser, just ambient heat, using nothing other than a nano-sized bead. Wow. You can also take one of these quantum dots, and one way you can tweak them is you can coat them in other things. Well, one of those things you can coat them in is zinc. Not going to go into a whole lot more on that. Lastly, that thermal side of things, you can use quantum dots to convert, instead of heat to terahertz lasers, heat to electricity. That would be very, very useful. If you had a heat sink that could actually convert the heat from your computer processor into usable electricity, imagine how efficient a computer you could have would be. That's a very valuable piece of tech right there, and it's been out for 7 years now. Well, at least I think this is a hypothetical paper. I don't think they actually did the experiment in it yet, but they did reference associated experiments where they're starting to show that it's possible. More on quantum dots. Turns out that you can have lead quantum dots. This paper doesn't say it, but I would imagine you might be able to coat a lead quantum dot in zinc, I'd imagine. Don't know why you'd want to do that. Here's some pictures, close-up TEM pictures of what a quantum dot might look like. On the left there, that one's just a red quantum dot that's made of, I think it's cadmium, selenium, or zinc, cadmium, sulfur. You can see the size, 10 nanometers. You can see how you got aligned grains there, and then it's got like a fuzzy like border on the outside. It kind of looks like a cell. On the right there, once again, you can also see another image of what quantum dots made of zinc might look like. Moving on to some of the whiskers that we have observed in our samples. So these arts parts pictures you can see here, there's no scale on this, unfortunately, because we were looking at this under our metallurgical microscope. We didn't have the software set up at the time to be able to have scale on there, but I can tell you that the diameter, the thickness of one of these things is in the ballpark of about 1 micron, to give you an idea. Whiskers can do some stuff, it turns out. They're not useless. First off, they may be indicative that this thing has been exposed to a prolonged electric gradient. That's important. Once again, that's a thing that tells us maybe a piece of the process puzzle. But additionally, when you start zooming in on terahertz stuff, whiskers have actually been known to have some interesting properties with relation to terahertz. Now, I'm not saying that's what's going on in arts part samples. I'm just saying that this is a potentially relevant paper I came across, somewhat related, where they were showing that in bismuth whiskers, that it can cause a polarization. It can rotate a terahertz beam, and that it has a higher refractive index than like bulk bismuth, which makes sense. I mean, you would think it would. So if you look at the upper right or upper left image, you can see the scale of these things is a bit larger than the scale that I was saying, right? The diameter of those things looks orders of magnitude larger than ours, but can't help but notice how that upper left image looks like this forest of crisscrossed whiskers like that. That's a very interesting image to me. I can't help but look at our bismuth ones, but the jury is still out whether or not these things are made of bismuth or they're made of zinc, or maybe there's both. Maybe you're not limited to just one kind of whisker. All right, lower left image there, that is a picture, once again, from the Oak Ridge National Lab report, if you can trust it. It's kind of hard to see because I made it too small, but I did a little bit of back of the napkin, like pixel counting calculations there. You can see that all those black dots there, that's the bismuth, right? And you can see that it's not a solid crystal. If it was a solid crystal, the idea that it might be acting as a waveguide would make a lot more sense. But it seems as though this thing is maybe not a waveguide because it's so discontinuous like that. So the sizes of those black dots, those bismuth dots, is somewhere in the ballpark of 100 nanometers to maybe 1,000 nanometers, a micron. And the total thickness there in the middle longer green line, that says 800 nanometers at that point. So saying that the bismuth layer is 1 to 5 microns is not accurate. In some places, it is much, much, much thinner and discontinuous, which turns out that there might actually be a use case for these things if they were discontinuous. On the right side, the lower right side image, this is a paper talking about bismuth nanoparticles, some of them in the sizes of what we're seeing in that Oak Ridge image. In that lower right image, the lower left of that under the energy loss column, you can see we have 200 nanometer and 500 nanometer spikes there in the EELS. EELS is just another measurement tool you do during tend to see a couple of other interesting features of a thing, usually like a little elemental analysis, but you can also do some plasmonic stuff with it. It's a useful tool. So it's interesting what I observed there, knowing very little, I will admit, very little about eels. But I can't help but observe how you have a fairly well-defined hump there in the 200 and 500 nanometer that you don't have in many other places. It spreads out at some of those other sizes. So that's interesting. I wonder if that plasmon relationship there might be important. Let's keep going. So a thin film bismuth, if this thing was a thin film, which it's not, but just to give you an idea on maybe some of the other effects that happened with bismuth, is when you hit bismuth with a circular polarized terahertz beam, there's a process that takes place within the bismuth that generates a current inside the bismuth. It's called circularly, I can't remember. I'm sorry. I'm pretty tired. It's photocurrent. Basically, you can use light to generate a current in the bismuth. And that current can then generate its own emission on the other side of the thing. That emission, what goes in must come out. You can get terahertz out of bismuth. For that, that's 30 nanometers, which is a little bit smaller than what we just saw in the those nanoparticles. But I want to say in that paper, maybe it tops out at like 70 nanometers is where you start getting saturation. So interesting, though. There's definitely a terahertz relationship with bismuth at small scales. Then I found this paper. This one's talking about how somebody took bismuth and they put gold wires on it, which I'm going to get to in a little bit here on why gold wires on bismuth might be important. But just the fact that somebody did a test like that is really interesting. Unfortunately, their testing was all in the telecom frequencies, which is hundreds of terahertz, extremely short wavelength. They're like 1 micron wavelength. We're talking, right, 50 to 90 micron wavelength terahertz. So definitely not 1-to-1. And the radius of the gold nanowires they were using was 17 nanometer gold wires, which, once again, it's not in the micron range gold nanowires that we're talking about with the arts parts. But what happens when you take gold wires and embed them into bismuth is that terahertz beam that comes out, yeah, you can actually cause that thing to rotate. You've now put a polarizer, a circular polarizer on that thing in the form of these gold wires. And it actually, it's messing with this very obscure type thing, but it's called Faraday rotation. Faraday rotation is interesting from Ray Stanford's stuff. He has that really famous picture of those Faraday rings on the edge of the craft, which are indicative of extraordinarily strong magnetic fields. In order to twist light that many times around, in order to get that many rings, you have to have an insanely strong magnetic field. Well, bismuth does funny magnetic stuff, and you put gold wires on it and you hit it with terahertz, and it does funny magnetic stuff more. Nowhere near the degree of like the 12 plus rings that we're seeing on his stuff. That's like, you know, kilotesla, gigatesla level like strengths. But maybe there's some kind of relationship here between the Faraday rotation of gold wire embedded in bismuth, Faraday rotation observed in UFOs. So this is going a little bit deeper into what's going on in bismuth. So you can hit bismuth with a right hand circularly polarized beam or with a left hand circularly polarized beam. And different things happen. So if you were trying to get a specific effect out of bismuth that only works with one circular polarization direction than the other, it's probably another avenue to look down. All right, let's get into some of the similarities I'm noticing in other craft that might have some overlaps with arts parts. First one, Ubatuba. So Ubatuba, if you're not already familiar with it, a fisherman is out fishing down in Brazil, Ubatuba, Brazil. And there was a UFO flies over his head, drops some molten metal, and years and years and years later, eventually makes its way by the late, I think it was in the 30s or something, it supposedly happened to the guy. And then by the 50s, this thing actually gets tested. So it's been tested many, many times since then. And there are some very strange things about it, which may support that it is indeed anomalous. One of the things that relates to arts parts, though, that I'm noticing is we got magnesium. It's much, much higher magnesium than what's in arts parts. Arts parts is like 97% magnesium. This is 99.8% magnesium. That's so much more magnesium. And the zinc is much, much lower. We're at like 2.5% zinc in arts parts. This thing's all the way down at I'm not going to say percent. This is parts per million. But there's zinc in there. One other thing I want to mention about this is maybe this could be indicative of what is going on with the craft. This stuff came down in metal molten globs as if it was useless to the craft, as if it was throwaway garbage. And it happens to have much, much less zinc than what's in arts parts. Does that mean that those little zinc microspheres might be getting all used up? And maybe zinc is consumed in the process of whatever this stuff is supposed to do? Maybe. I don't know. I'm just making an observation. All right, this is the one that gets me excited. Dalnegorsk. When I came across it, I haven't been able to stop thinking about the Dalnegorsk case since I came across it. This is so cool. So in 1986, January, there was this tiny, tiny little mining town in Russia that is in the mountains. The height 111 thing there, that's because it was like a mountain that was 611 meters above sea level or something like that. Like it's a super prosaic name. But it's 38 and a half years after the original Roswell Arts Parts event. And it's 10 years before Arts Parts enters the public scene. So this, at a bare minimum, even to a skeptic, this can predate, if indeed it has enough overlaps, it can predate Arts Parts back from 1996 back to maybe 1986 if we consider that this could come from a similar craft. I have got this meta study going on all of the elements present that were tested in this stuff back in the 80s. And I've compared all those against all of the elements that we are observing in Arts Parts. What you see before you, that is just the elements that are the same. There's some differences in the elements in there as well. Might be indicative of transmutation. I'm not going to hang my hat on that, but it might be. Don't know. But it's got sodium, silicon, iron, nickel, zinc, molybdenum, gold, lead, bismuth. That's a lot of overlap there, just if you're looking at like nothing other than the elements that are present in these samples. But it turns out there's also some physical characteristics that are the same too. Has gold nanowires, and it's got those little ruptured zinc lead microspheres that I was talking about. This thing has hollow lead microspheres. So here's the book. By the way, if anybody goes back and watches this after I've uploaded this presentation, I got links all over the place throughout this whole presentation. This is a book I found that was all in German. I translated it. There's a link in the presentation for this book. But you can see in those images, they're showing the little gold nanowires. And actually what they're saying is that these things are 17 micron diameter and that they are made of quartz with a gold core. That is extremely unique and very relevant to Arts Parts. In the lower image there, you can see there's another picture of their quartz-clad gold wire sitting on the surface of the sample, like it's part of the sample. And here's a side-by-side of that image and our Arts Parts quartz-clad gold nanowire. It's not a 1-to-1, but it's got some similarities. Also, let's take a step back for a second. Remember that DIRD, the Defense Intelligence Document that Eric Davis wrote? Well, in that document, one of the things he talks about is these quantum dot particles being on the outside of a control wire. I'm just making an observation here. If you look at these quartz-colored wires on here, do you see some bumps on there? Do you see any similarities between that quantum dot particles control wire picture and our sample? Maybe. Here is some other parts of the Dalnegorsk recovered materials. The important part here is in the center. I got a picture there for you of our EDS ruptured zinc lead microsphere. And below that is the picture of the lead droplets that are like hollow in the middle. Now, I think there is a size difference here, also an elemental difference. You know, if they're saying those are lead and we only see like a bit of lead in ours, and how hollow do those look? I mean, you can go after that all you want. Like it is far cry from a definite overlap. But maybe a relationship, if anything, maybe this can once again help give us an idea on some processes that are taking place, if indeed these come from similar craft. Additionally, though, they also talk about a gold mesh. Now that could be very, very useful, extremely useful. In terahertz applications, gold mesh, that's a thing. So here's a little blurb from that book where they're talking about the gold nanowire that's clad in quartz. The scientist said that the metal fabrics that they found, which I believe is the gold mesh, says that a natural or a terrestrial technical, meaning human-made on Earth, origin is excluded. That scientist, for the life of him, could not imagine any way in 1986 that somebody could be making a gold nanowire encased in quartz at the sizes that they're seeing, nor these gold meshes at the sizes that they're seeing. Like, it wasn't a thing at the time. 10 years before Art's Parts. So here's an interesting thing. So Quincy St. Clair, related to the gold nanowires. Quincy St. Clair, if you know, you know. So this guy has a lot of really interesting patents. Some of them are way out there. Some of them are less so. This one, I'll put it somewhere in the middle. So in this one, he is talking in 2004 about a braided gold coaxial cable. In his case, he's saying a gold within gold, but you could replace the outer gold with quartz and it would perform better. But in this patent, he's talking about a gold coaxial cable in the micron size. He's saying that it couples to space-time itself somehow. It's a dimensional manipulator somehow. The important part is that he says it just so happens that according to all these calculations he's got, should be about 16 to 17 micron diameter. That's interesting. I wonder if he knew about the Dalnegorsk thing. Maybe he knew more. Maybe not. Maybe it was just dumb luck, but that's what's in his patent. Well, he's talking about tapping into subspace or dimensional energy or something. It's worth noting that in the first Art's Parts letter, the grandson is talking about what happened after the crash. So according to grandfather, the crash happened and there was a survivor that grandfather ended up talking with a lot for like 6 months. That ET said that in the process of the crash, he goes through the whole story on what's like started with the crash and then what went on during the falling and then, you know, once they actually landed. But what the alien said was that they had two modes of propulsion on the craft. One is the dimensional power plant, which sounds more like a generator, but he's saying that they use it for deep space travel. Okay, that might be related in some way to what Quincy St. Clair is talking about with the dimensional subspace, something or other with gold nanowire. I'm not sure. Good takeaway from that, though, is that there is two different forms of propulsion according to a document that cannot be like verified, right? We know that this document went to Art Bell, Linda Moulton Howe, but we don't know if the grandson is telling the truth or not because we haven't identified grandson. All right, here's some calculations. I put in definite quotes because ChatGPT, bro. Okay, I was doing this in 2 days. I didn't have time for it. So I'm going to say order of magnitude. I'm not going to hang my hat on this, but I'm going to say order of magnitude. If it just so happens that you had a quartz-clad gold nanowire of the dimensions that Quincy St. Clair is talking about, you're looking in the far infrared range. You're looking at the low terahertz range. I feel confident enough to say you're in the single-digit terahertz, but I'm not going to hang my hat on it. All right, so we're seeing some similarities here and there. We're seeing quartz case nanowire might be in that low terahertz range. The bismuth layer, it just so happens that there may be some interesting plasmonic effects at these particular sizes. I didn't get into it, I apologize, but at some of these similar frequencies as well. The diameters of these ruptured microspheres happens to also be in the ballpark range of this far infrared low terahertz, which might be also indicative of the specific frequencies that we need to zoom in on. Maybe we can take that 3 to 5 terahertz and we can narrow it down to 4 or something, right? Maybe if there were zinc-sized nanograins present in this thing, they might be interacting as far infrared low terahertz plasmonic devices. And then, of course, the magic from Lou Elizondo's book, Imminent, he just puts it right out there. He says, this was the frequency that was really interesting. Gives a range 3.2 to 5.6. Here's some more stuff about how you can improve a nanowire by cladding it in quartz, because you get this negative refractive index of the quartz, and it's a whole thing. It improves your nanowires. Also, though, if you take a nanowire, if you take a bunch of nanowires and you position them in the right way, in the right shape, you can end up steering, doing beam steering. That might be useful for something. If you have a whole array of them like that, you could end up twisting a beam. Once again, we come back to circular polarization and twisting beams. I can't help but notice that that gold nanowire that we got on ours happens to have an angle in it. So got a protractor out, measured the angle. Image on the right there is the scanning electron microscope image of our sample. So the thing is that on the bottom arm that you see here, you can see how it kind of kicks up. It's got a little bend up there. So I measure distances and angles to both. It looks like at the elbow there, the long elbow, it looks like that's at around 120 degrees. And it looks like that little kick up at the end, it looks like that's about a 25-degree kick up. So overall, from tip to tip, you're in the 100-degree range, give or take. I also, using the scanning electron microscope image you just saw, I overlaid that over the other one. And then I took the scale from the scanning electron microscope image to try to come up with a ballpark length on these arms of this thing. There's better ways of doing this, way better ways that look way less messy than this. But this is what you get with a very rushed presentation. It turns out that this potentially phase shifting something or other metasurface gold, if it is maybe gold nanowire, the length of one arm is around 260 microns. The length of the other arm in total is around 240. That little 20-degree or 25-degree bend that we see there, the length to that point from the elbow is around 130 microns. It's right around the halfway mark. Well, that's really interesting because the average layer thickness of the magnesium and zinc is 150 microns. I might just be noticing things that aren't there. Maybe there's no relationship between the lengths of these arms and the thicknesses of the magnesium layers. But it's in the ballpark. The overall length of those is quite different at 60%. But that bend there, that little 20-degree bend there, if we look at that length, if that's important, that's within spitting distance of the average thickness of these layers. From Lou's book, we can see that Lockheed tried to make their own, and he included a picture in there. And I don't know if that picture is the actual one. Supposedly, they failed. The unnamed aerospace company, they tried to make it, and they claimed that they failed. I found a similar image of an engine vibration test block, which is something that maybe an aerospace company would have that looks in the ballpark similar. I don't know for sure if the image that Lou has there is correct or not. I don't expect any wrongdoing on his part, but I don't know if that is indeed supposed to be a layered metamaterial. But if we wanted to make this ourselves, this is where the rubber meets the road. We're engineers. We don't really care about theory. Just let's make it and make it do the thing. Can we buy the parts? Can we shove them together? Can we make this happen? I'm going to put a low maybe on it. Not a hard no, but closer to no than yes. And the reason why is because some of the nanoscopic sized things in this are not something we're going to be making anytime soon. But we could buy bismuth nano powder, make little nano things. We could buy gold mesh grid of the sizes that they describe. And then we could coat that in quartz. We could purchase some terahertz sources. There's a lot of stuff we could do if we wanted to try to make this ourselves on the cheap, right? That's the other thing, is doing this on a budget and not in a, super top-notch lab, but, garage labs like we got. Well, we did happen to find a terahertz laser. I mean, that's pretty awesome. So this terahertz laser, the previous owner, I believe, may have been Sandia. I don't know for sure, but I believe it might have been based upon its previous location. This terahertz laser, when operational, goes from 250 gigahertz up to 7.5 terahertz. Hey, would you look at that? Falls right within our magic window frequency. That's pretty awesome. Now, because we got this for a steal, it hasn't been serviced in about 15 years. So we are in the process. This is late breaking news. We just got this thing, and we just got the service manual for this thing like a couple days ago. So it is a work in progress before we're going to have this thing up and running. But we're a lot farther than not having anything. So here's some more pictures of this thing. Lasers with Z, because lasers are awesome. This is one of those don't mess with it lasers. It's a really, really, really dangerous laser. So we have to make sure that we dot our I's and cross our T's to the nth degree before we even turn this thing on. But we're working on it. All right, and then I'm going to transition it here. The elemental analysis, I do want to make just a little blurb here on the isotopic analysis. So this stuff does some really cool things with regards to radiation. Like it just gobbles up the neutrons in a way that is really unusual. It doesn't do it all the time. It only does it at like the highest possible energy. And it saturates really fast too. So it gobbles them up and now it's done gobbling them up. Like it's really, really weird. So we did that little lower right-hand image you see there. That's a little puck of uber super duper radioactive stuff, some of the most radioactive stuff known to man. And our sample is sitting on it there. We left it on there for 5 hours. Booyah, it activates. That means we were able to make it radioactive and then start measuring all the elements that are in there based upon the spin down half-lives of the elements that are present. So we do that. We get like an initial rough draft. Hey, we're seeing elements in here that is confirming what we already believe to be true about the elements present. And then we do the long test, put on a big old block of slightly less radioactive, but still very radioactive stuff. And we do it for a month. And nothing happened? What? It didn't become radioactive after sitting on a block of this stuff for a month? That's not supposed to happen. So then we put it back on the original thing. We leave it on there for a week this time instead of a couple hours. But it only got as radioactive as it did the first time after a week. That's all I'm gonna say about it for now. I want to not steal any of Dr. Szydagis' thunder because he's got a pretty good thing to tell you here about what's going to go on. But so the summary, this is what I got for the latest Arts Parts update. The microsphere, the lead zinc microspheres, they happen to be arranged oftentimes in circular patterns that may relate to low frequency terahertz. Programmable quantum matter is something worth looking into for a number of reasons. Quantum dots especially are interesting for their relationship to terahertz output, and they can do a lot of other fancy things too. This quartz-clad gold nanowire happens to follow a lot of similar things about it to other gold nanowires used in terahertz functions. The not solid crystal, but instead the very small nanosphere-sized bismuth nanoparticles. It turns out that those actually may have some really decent plasmonic applications. There might be this whole area of plasmonics that we need to deep dive. And because it's bismuth, it can do some really fancy physics. There's a couple of different asymmetries that exist regarding bismuth that are worth pursuing further. And we have a terahertz laser ourselves. It's only a matter of time. Arrow released a short report that said it was slag. According to Hal Putoff in a recent interview that I linked at the very beginning of this whole thing, there's a lot more than just slag in the much longer report. I got a bunch of extra resources there. There's papers galore within this stuff that if anyone wants to learn more about any of the things I've discussed. I had to read a lot of them. So I just want to end this with a super, super big thank you to the scientists that let me be a part and let me put together this new chapter of Arts Parts testing development. Like, I cannot express how grateful I am and how stoked I am at what should be coming down the pike regarding 3 samples instead of just our 1. That's what I got.
Jarod, that is amazing. That is absolutely amazing. Okay, let me take the slide deck out. And what I will do is, again, on the Alt Propulsion website, we archive these. So if it's cool, I will put the slide deck up there. Just get me over a copy. I will upload that and link it. And we have those in Google Drive, and I could share that during the conference. I also have some photos as well of Arts Parts, not the stuff that you were asked to redact, but I have that. I have Dalnegorsk, and Michael Perrone has got SEM photos from the Frank Kimbler Roswell bounce site crash. And so I have those. He's going to come on later and do them. But before anything else, I'm going to bring everybody in here. Let me see. We'll bring the whole gang in. And let's give an enormous applause to Jarod Yates. And I've been calling Jarod on like almost a daily basis for the last few months at this point. And I just want to tell everybody, like anybody who's tuning in, anybody who watches this, on YouTube and replay, Jarod has been working for the better part of a year, and it has been night and day, and he has been scouring the internet. He has worked with, he like physically worked with 3 or 4 PhDs. He has corresponded with probably another 10 PhDs on different samples, analysis techniques, what could be going on with these. So, in my opinion, Jarod is basically the world's #1 expert on this. And there are 2 reasons for that. One of them is the amount of research that he has put in far outweighs what anybody has done in decades. He's also building upon work that's already been done. Linda Moulton Howe and Travis Taylor did research on arts parts and published very extensive documentation that Jarod worked from, and they did that back in '96. Hal Pudoff also did some research on this. Other people have done research. Jarod is the beneficiary of all of that. And then the other part is Jarod is working with multiple samples. He's been able to look at data from Ubatuba as well as the arts parts, 2 different samples there, as well as Frank Kimbler bounce site, as well as St. Augustine. So we've got 5 different samples, and we actually have 3 or 4 more people that are looking at sending us different samples. So again, absolutely, absolutely amazing. Jarod, I cannot thank you enough. I am so appreciative.
Thank you, Tim.
So it looks like, let me see, Matthew Szydagis is up next, and we're actually at the top of the hour. I'm not sure if Matthew is here or not, so I'm just going to hold until I see. Oh, there he is.
I've been here the whole time.
Oh, wonderful.
Yeah, camera
wonderful. Okay.
No point in having camera on when I'm backstage still.
Awesome. Well, if it's okay, Jarod, should we skip the Q&A and go right into Matthew's presentation? Oh, okay. Okay, well, let's do that then. And we're tight on time. We will circle back around because I've got stuff loaded, and then Michael will be coming in later too. So, okay, I'm going to take everybody out. Matthew, thank you so much. And there is your slide deck. And again, you have been working on arts parts sample analysis as well. That's one of the things that makes this such a tremendous story. And I'm really just a bystander in this, but like the work that you guys have been doing is just blown me away. It's almost like you've opened Pandora's box. Once you open it, there's so much that comes out of it, right? So
Tim, will you be driving the slides? So should I say next slide?
Oh, actually, since you uploaded it, you can do the back and forth. If you put your mouse over it, you should see a little slide indicator.
Oh, yeah, it works. Okay, cool. Sorry, I'm not used to StreamYard, so using Zoom. So awesome. Okay, I'm good to go then.
Perfect. Okay, well, let me take myself out and thank you again so much.
Oh, you're welcome, Tim. Oh, Tim, were you going to introduce me? I never sent you a bio.
You know what? No, well, yeah. So I don't have a bio on hand for you, but Professor Matthew Szydagis, University at Albany, right? Physics. You are one of the world's dark matter experts. I think that's worth pointing out. You are also a member of the Scientific Coalition for UAP Studies. You have done a ton of work, peer-reviewed scientific work, along with Dr. Kevin Newth. You've also been working with UAPX group, if I recall correctly. So, you are as deep into this as anybody is, but you're coming at it from a rigorous PhD level scientific perspective. And that's very important to point out to people.
Yes, thank you, Tim. And I was just like Jarod, I was rushing to put these slides together. And so that's why, you sent me instructions for presenters, never sent you a bio or anything, but I have presented at APEC a couple times before, so people may already know a bit about my history. But why don't I just get going right away? First, I want to thank Tim for saving my bacon. What I mean by that is Tim very graciously advertised a course I was teaching online only last year on exotic propulsion. And the tuition from that course was of extreme importance to me. So I want to say thank you to Tim. And second, an apology that Jarod said basically the same thing. Our analyses are nowhere near completed. So Tim says this is the biggest story of 2025. Well, I want to try to temper that. Maybe December 2025. I'd like to ask for everyone's patience while I teach, and my students who I give shout outs to for their work with me on this in the presentation today. I'm teaching classes, they're taking classes. Okay. There's like a brief amount of time in the summer to work on research, but the thing is I'm 100% of my time is funded by the U.S. Department of Energy to work on dark matter. Well, we'll see what the Trump administration has to say about that if they ever unfreeze our grant. But right now we're funded to work on none of this. And so this is all free time, spare time, volunteer work that has just been really hard to keep up with. So I'm being completely honest with everybody. My slides were super rushed. Jarod pulled a couple all-nighters for his. My situation's even worse. I finished writing them about 10 seconds before Tim said, "Hey, can we go to you now, Matthew?" So this is it's a talk, not a scientific paper. And in a paper, you really can't afford, with something given the stigma and taboo on the topic, can't afford mistakes. So there could be errors here. It's a very preliminary results here still, but I still trust I have some very exciting things to share with you today, and to follow on from what Jarod has already told you about. So first, I'm going to dive right into what is the technique of material analysis I'm going to be talking about today. I'm going to be talking about NAA, neutron activation analysis. So what is NAA? So Tim says he loves talking about history, right? So this is an ancient technique. Not by ancient, I mean like 50 years. Okay, this is not a new idea. And I'm shocked by the number of scientists and engineers that I've said, like even who work at NASA, who've never heard of this and don't believe in the results. And I'm like, national labs have been using this for decades. It's a standard technique. So what does it mean? So first of all, I should emphasize that its number one benefit of this technique is it's non-destructive. Non-destructive asterisk. And I was just texting Mark today to please not kill me, because the terahertz laser that just Jarod was bragging about, I would bet any amount of money that that's not going to do anything, because even if it did before, the sample from Vulcan Aerospace that Mark has trusted me with, Jarod has trusted me with, is pretty much hosed. It's been so irradiated that this probably changed the physical structures in it. Now, standard neutron activation analysis is not supposed to do that. But as Jarod said, we got desperate because it wasn't working. So we blasted the crap out of it with both californium and plutonium. And I'm going to get into how this works. So on this slide, you see the basic idea here at the upper right is most stable isotopes are going to be happy to eat an extra neutron, and they become radioactive temporarily. For vast majority of atoms, this is low risk. Like, you don't make your sample permanently radioactive at a high amount. So in fact, just to kind of like, if we have time later, I'll try to play a video of this. I couldn't upload it though. I got an error message, unfortunately, on the browser. But just to mess with people I know, like my sister, who are terrified of radiation, and she's read like the Chernobyl dies, things like that, and where I tried to explain to her that when radiation is used properly, when you know what you're doing, you can safely handle things. So just to mess with her, I actually made a cracker radioactive and a salami, and I actually ate it after it went back down, after it decayed back to background radiation. So I'm not going to get cancer from that because it decayed back. So what neutron activation basically is you take something that's stable and you make it radioactive temporarily, safely, at a small level, in order to produce alphas, betas, and gammas from it. Not so much alphas, primarily betas and gammas. And with traditional neutron activation analysis, you look for monoenergetic peaks from gammas and X-rays, but it's also important to try to catch the betas as well. Betas are much harder to analyze, though, because they're not monoenergetic. They create spectra, and I'll show you examples later. So also, this is a complementary technique to other things. So since Star Trek tricorders don't exist, we need multiple techniques. So this technique is not going to tell you, oh, this is this many microns and this is in that location. It's apples and oranges. That's completely irrelevant to what I'm talking about, because we as humans, at least, do not have any magical techniques that can tell us exactly what something is made of. We have to combine several different techniques for the same samples. So I wanted to also point out, so I actually have a paper that was just published actually in Limina, a journal of UAP studies. You can get it open source there. You can also get it open source on the archive, which I was shocked they let this paper through. They usually like blackball and papers on UFOs. We've gotten increasingly lucky recently. But I highlighted a sentence from one of my concluding paragraphs, I think the concluding paragraph, where I talk about the use of NAA to convince people that something is extraterrestrial. So I've actually been thinking about this for an extremely long time. And one of the art's parts, the one that I got from Mark and Jarod, is actually the first interesting use case I've had of this. It's not the first UFO part, I have to say, but the first set of UFO parts I use NAA on, most definitely not interesting. I mean, interesting to some, like it was a secret. Clearly, it was a top secret U.S. airplane that crashed in the desert, but very clearly made of a combination of human alloys. So it was cool, but this is the first time where there's something potentially interesting, because everything else I've been sent is like pretty mundane or prosaic when we tested it with NAA or with XRF, which is a second technique I'll be talking about today as well. So now let me say a brief word about isotopic ratios, what they are and what they mean. So one of the strengths of NAA is you might be able to do the isotopes, but not just the elements. And why is that? So different isotopes, not elements, different isotopes will react differently to incoming neutron particles from neutron sources as a function of energy. So in case you don't remember what an isotope is, maybe from chemistry 101. So what is an isotope? So an element's unique identity is determined by its number of protons or electrons if the atom is neutral. But if it's an ion, then you can only rely on number of protons is like the unique thing that this is zinc, this is magnesium, this is whatever. But the neutron count will vary. And many elements are composed of multiple stable isotopes. This is not the same idea, by the way, as isomers or allotropes, which are different ways of having the same element with variation. But isotope is where you have the same element, but the nucleus has a varying number of neutrons. So NAA may be able to tell you the ratios of isotopes within elements, but you have to do a careful analysis, because when you detect an isotope with NAA, you're not actually detecting that isotope. So let's say I'm detecting magnesium 28. That's actually 27 because it ate an extra neutron. And so you have to be so careful. You have to know what you're doing. Also, you have to have, if you have enough statistics, one of the powers of this technique is you can pull out things that are at the ppm, ppb levels. That's parts per million, parts per billion, without vaporizing the sample. So it's not like ICP-MS. So it's a non-physically destructive way. Although, as I said earlier, I think the sample I've been testing is pretty well destroyed. Not physically, like it's still there, but it's probably going to look very different now under a microscope. And it's probably not going to do anything with a terahertz laser if it did, because while not physically destructive to the human eye, the way the amount of radiation we had to throw at this sample to get a result was above and beyond what's usually required. And I'll go into that definitely in depth as one of the most interesting preliminary results we have so far. So because if you can't get isotopes out of it because you don't have enough statistics to be able to take ratios of the different isotopic peaks, what you can at least do is reconfirm what elements are inside from using other techniques. Because remember that unlike in science fiction, science fiction gets this wrong all the time, and it makes me tear my hair out. Even Star Trek gets this wrong sometimes too. It's the same elements and it's the same periodic table in the entire universe. Period. Like you can look at the most distant galaxy, and using spectroscopy, you can see what the most distant stars and galaxies are made of. It's the same damn elements as on Earth. And so what's potentially interesting if you have an advanced civilization is new ways of putting those elements together. And if you do isotopic enrichment, new ways, as Gary Nolan has suggested with some of these parts, of putting together specific isotopes instead of just specific elements, because humans have only just barely started doing that in the nuclear age. So most important of all, when it comes to ratios of isotopes, they may be able to tell you if a material is terrestrial or extraterrestrial. Sometimes you can do that with just elements. If, for example, you have a lot of iridium in something, that's how meteorites are often identified. Like, for example, the asteroid or meteor that killed the dinosaurs, its crater shows, or iridium and some of these rare earth elements that, while they are found on Earth, aren't found very often. Now, so if done correctly, a neutron activation analysis should be able to tell you if something is not from Earth, or it's the most expensive hoax in history. So we can do isotopic enrichment, but again, like I said, we haven't always been able to do that. So if a part dates to before we have that technology, and the isotopic ratios are off, that's pretty damning. Again, it's still not conclusive, because somebody like an uber skeptic could just say it's the most expensive hoax, and someone just but still, at that point you've got to, it's pretty crazy then. To remain skeptical that something isn't anomalous. So how does, again, let's dig deeper into how neutron activation works. So you take something that, and this is a huge misunderstanding always when I've talked about this, like at the SAU conference, elsewhere, people think I'm like measuring the radioactivity of the part. I'm like, no, people have done that. Like, Art's part is not radioactive. Like, that's not what I'm talking about here. I'm talking about something that's not radioactive at all at first. And then what we do is we put that object, and ideally a solid. So one thing where we ran afoul of, I wanted to, we had some email exchanges, want to do Ubatuba sample. It's been already like dissolved, and it's like sitting in a liquid. Well, we're screwed then, because then what's going to happen is we're going to get, if we try neutron activation analysis, we'll be activating the container it sits in. I mean, it's just a non-starter. And so it's unfortunate that there's so many samples we can't do this with already, because chemical analyses were done. And it's like, a chemical analysis, I'm sorry, is never going to prove that something is extraterrestrial. I mean, it's not going to happen. But you need an isotopic analysis. You can't do neutron activation analysis if you already destroy the sample. And so, and I already talked with Tim about that. Oh, couldn't you subtract the effect of the container? Couldn't you take some? I'm like, no, that's a non-starter. For different types of analyses, yes, there are ways of subtracting background radiation stuff, but with neutron activation analysis, you basically made it impossible already. So there are certain historical samples where people have asked me, oh, can you do that one? I'm like, that sample has already been destroyed. It's already is suspended in a liquid, and then whatever that liquid is, or whatever that container is going to overwhelm the signal. And so I need, for something like NAA, it's got to be a hunk of solid. If it's already been pre-destroyed, don't even email me. I'm like, I'm sorry, that's just not happening. And maybe if I had I was paid to do this, I would find some way to maybe make it work with a sample that's destroyed already in a liquid, but probably not. And so I need a solid sample, and this is the same californium-252 source that Jarod showed. This is extremely dangerous. In many ways, californium is more dangerous than plutonium. Because I'm a physicist and I work at university, I was permitted to buy this. It's the highest activity source I was able to buy, and it is very dangerous, because unlike an alpha source, unlike a beta source, unlike a gamma source, a neutron source is contagious. The radiation is contagious. That's how this whole process works, is you can produce activation of a source. And so if you handle this source, you can only handle the source for small periods of time. You should not use your hand. You should use, we've got like a robot claw to move this source. If you hold this in your hand is now radioactive. Like, it'll activate the carbon, the oxygen in your body. And so it's not a good thing to mishandle neutron sources. Safety is of the utmost importance. And so what you do is you take your sample, you place it on top of a neutron source, and you wait. Longer is usually better, but as Jarod already hinted at, there have been some interesting exceptions. You want to remove your sample then and place it onto your particle detectors, specifically beta and gamma detectors. So again, common misconception, we're not detecting neutrons. The purpose of the neutrons are to make something radioactive, and then it's not going to spew more neutrons. That's fission. That's not what we're talking about here. It's going to spew betas and gammas. So you want to move the part quickly. because in case there are very short half-lives. There are things with millisecond half-lives, you're never going to detect them with NAA. Because like I said, you need different techniques for different, there's no such thing as a Star Trek tricorder. You need to combine different techniques. And so if something has millisecond, microsecond half-lives you activated, yeah, you are not going to see that. But if you move quickly, you should be able to see things with 1, 2, 3 second half-lives, right? Depending on how much of that isotope is in the material. Important exception I've noted on the slide. Some things have extremely long half-lives, like bismuth. I'm going to come back to that. That's going to be very important later in my talk. To the best of my knowledge, Jarod, as Tim said, Jarod has done so much more research on this, online research, and talking to people, and not just online, driving around the country. Jarod may correct me. He may know better than this, but to the best of my knowledge, nobody's even thought of trying neutron activation analysis for arts parts or any UFO parts, which to me shocked me. I'm like, why is that not standard procedure for like the government? Why isn't it just, like I said, it should be the second to last test. The last test should be destructive. Should be like ICP-MS, where you vaporize it, count the isotopes that way to cross-check the NAA. In my opinion, NAA should always be the second to last test. Like I said, we didn't quite second to last this time. We got terahertz lasers, all this stuff, but that's why I warned Mark and Jarod, like all the tests that come after that, you can no longer trust the results, because we've changed the composition and the physical structure now of this arc part. But as I think you'll see in my talk, it was well worth it and well worth the risk to damage the part to get these amazing, some of the great things I'm going to tell you today. I hope that you're going to be as excited as I am by the end of this talk. So to the best of my knowledge, it's never been done. I asked Eric Davis, he said no. I asked Hal, and he was like, no. And I'm like, what the hell? Like, I asked Travis Taylor, like, no. I'm like, why isn't this part of your standard toolkit? And so, like, as Tim introduced me, I work on dark matter detectors, where it's very important to build your dark matter detector out of materials that are low in radiation. So when I say low in radiation, people think I'm talking about radioactive materials. No, I'm talking about the fact that when you build a particle detector, you need to build it out of materials that are less radioactive than the human body. So that's what I mean by low radiation materials. So one of our techniques that we use to find what the hell is something made of is neutron activation. Standard. I've been doing neutron activation since grad school, since postdoc. I was a postdoc at UC Davis. We would take parts to a nuclear reactor, expose them, and then count them to be like, it's this. We would test titanium and determine it's this % of this kind of titanium. It's got this kind of scandium impurities, things like that. This is standard procedure. And so I was shocked that NASA hasn't heard of it. Like Kevin's friends at NASA were making fun of it, didn't believe it's a thing. I'm like, it's like a 5-decade-long thing. And to me, this is just evidence of how, as scientists and engineers, we're not interdisciplinary enough. We overspecialize, and people don't even know that, like, standard techniques with hundreds of publications, and they've never heard of it. And so it's so simple. You expose your sample to a natural or artificial source of neutrons. It doesn't work with not all sources of neutrons will work with all elements. So for example, an americium beryllium source, like I own one of those, not very good at doing this. Californium is great at doing this because the energy spectrum matters. I'll come back to that as well later. The flux matters and the energy spectrum matters. But neutron activation itself works for nearly the entire periodic table. There are exceptions. The most important exceptions are hydrogen and boron, because boron will be happy to take your neutron. It's not going to give you shit back. And hydrogen will be happy to take your neutron and turn into deuterium, which is stable. And so, yeah, you cannot do this. There are certain elements, especially the lightest elements, where your sample could be 98% that element, and the NAA will register 0% because it's just the technique is not designed to detect that type of element. But for most of the elements, especially the heaviest elements, you can look at gamma energies, beta energy spectra, and the decay times. So a radiation detector is a must. But the downsides, again, of this technique is people always ask me, is it magnesium oxide that you found? Is this that? I'm like, I don't know. This technique does not tell me about compounds. It does not tell me about molecules. It does not tell me if we've got covalent bonds, ionic bonds, completely irrelevant. For that, you need Raman scattering. And as I said, I hope, I've been meaning to ask Jarod again if Raman scattering is done, because Like I said, it's kind of too late now after the NAA. We'd have to get a fresh piece from the mother sample. But because as I said, NAA should be second to last. But there's like Raman scattering. There's different techniques like that that'll tell you what kind of molecules are present, what kind of compounds. This does not do that. And so if you're going to ask me, is it zinc oxide, magnesium oxide? My answer is I don't know. And this technique will not tell you that's not possible. And so this technique doesn't tell you how the atoms are put together. It just tells you what atoms are present. So we've devised a newer approach. I call it NAA on the cheap, or MacGyver's NAA, because, you know, I'm not Harvard. We're not at a rich university, because rich universities are not interested in touching this controversial topic, right? That's changing now, right? You've got Avi Loeb at Harvard, but I mean, most, like, I'm not at an Ivy League school. I'm not at a national lab. And usually the way NAA is done is you have to expose your sample to a nuclear reactor. I don't have a nuclear reactor on campus. Some schools do. Absolutely. Some universities do. I know some universities that do, and Penn State, Kansas State, I think, Minnesota, I think Ohio State maybe, but we don't have that. I don't have a nuclear reactor on campus. We have an ion beam lab, which my student Andrew works on. I'll mention him later, but that would be extra destructive. Like I said earlier, I'm already like super guilty over the fact that the sample is already toast. When I give it back to Mark, but there was one way to make it even worse toast, which I did not do. Maybe we'll do that later. I'll talk to Mark and Jarod. We could put a deuterium beam on it and then really do neutron activation. But it will burn the sample to a cinder and it'll just turn to dust completely. So that's even more destructive. So we didn't want to do that, obviously, at least for the initial neutron activation. So what did we do? So we don't have a nuclear reactor. We don't want to destroy it in the deuterium beam. So deuterium creates neutrons through indirect reactions. We don't want to do that. So what we do is we put it on top of californium, the californium source I showed and Jarod showed, and then we followed up actually with a plutonium beryllium source I'll mention. So that I don't know why Jarod didn't mention that. Maybe he didn't want to steal my thunder, but he said, and I can't tell you what this is, but Mark visited me a second time. First was Jarod, and then actually first time was not Mark, it was Tim and Jarod, and then I got a second visit that was it was Mark came to visit me, and he was actually there when we placed it next to a plutonium sample to try to get better data. So we don't have a reactor, but we have neutron sources. So we want to do our faster, cheaper, easier, more accessible neutron activation analysis. Another way to make it faster, cheaper, easier is to focus on lifetime, not on energy. So what that means is we can look at just the decay times and pull the information out of that. What's the benefit of that instead of looking at energies? Well, if you have got betas mostly coming out instead of gammas, you're not going to get good energy resolution of that anyway. But this means you can get, like, instead of several $1,000 detectors, you can use few $100 detectors. And so we use the MIT Cosmic Watch, same as we used on UAPX for like hunting for external radiation. And the other thing that's really useful about looking at the decay times is now you don't need a calibration. And so this mitigates like a really important need that you have constantly in science engineers. You got to calibrate things, but when you're just looking at the decay times, that mitigates the need for the same level of strenuous calibration that you have when you look at energies from peaks. We are going to follow up, and we have already started following up, however, with better detectors than the Cosmic Watches, which is the upper image. And in the lower image, we've got the Radia Code 102, which is one of the best radiation detectors in terms of quality to cost ratio. It does automatic identification of peaks in software and automatic isotopic identification, and it comes pre-calibrated. So that's pretty awesome. So now we're going to take the cheaper technique of using Cosmic Watches and just look at half-lives and make it more like traditional NAA, where we also look at the energies of the gammas that are emitted, energies of the betas. So how do we get, if we don't have the energy resolution though, how do we pull out information? And it turns out that you can take an exponential and you can do a Fourier transform on it. And now instead of this ugly exponential, which is really hard to fit, very, very hard to fit once you have more than 3 things going on. And here we could have like 20 or 30 elements, like Jarod was saying, times the number of isotopes per element. There could be hundreds of isotopes in one piece, like the art part. So what do? So you can't just do like a fit to an exponential curve when you have that many different half-lives or mean lifetimes. But something that we discovered at UAlbany is like, again, I'm shocked that nobody's thought of this in 50, 60 years of doing neutron activation analysis, is instead of just looking at exponentials, you do a Fourier transform of the exponentials, and now you have peaks. And so now it looks just like a traditional analysis where you have peaks in energy, but now these are peaks in time, where the peaks are at the mean lifetime, not the half-life, but the mean life, the 1/E time constant. And now you can pull out multiple peaks much more robustly. So you're probably all familiar with the Cooley-Tukey algorithm for fast Fourier transforms, because that's the standard one for FFTs. I came up with my own algorithm. I can't tell you how it works. This is going, on YouTube. I need to publish it first. But I came up with an even better algorithm than a traditional fast Fourier transform in order to go from turn an exponential with multiple time constants hiding in there into multiple peaks. Now it's still tricky because in real data, you don't have a pretty, like this blue hand drawing, exponential. It's going to be noisy as the sample is decaying away in the NAA. So you're going to have some noisy data, which means you're going to have false positives for peaks. You're going to have peaks that should be there but are smeared out. And so this isn't as easy as it sounds. And I should emphasize one of the strange things about NAA is, so in fact, zinc, remember, makes up like a huge amount of this sample. It's mostly magnesium, but then like the next biggest thing is zinc. I can barely see zinc, and it comes and go, like, depending on how I analyze the data, it says like no evidence for zinc. So you're like, what? But that's like way more than the bismuth and the other stuff. And the biggest signal I see is bismuth. Why? Because the way neutron activation analysis works, and this is again why the analysis of the data is so hard, and why it's going to take me and my students and colleagues at UAlbany several months, like most of the rest of the year. It's not trivial, because the height of the peak in my cartoon example on the right does not depend directly on the concentration. You think, oh, if there's more of isotope X, X will be a higher peak. No, that's not how this works. That's how every other material analysis technique works, or most of them. It's not how this works, because it depends on how strong the neutron absorption cross-section is of that isotope, of whatever isotopes plurals in there. And so you might end up with an enormous signal, and that's the case where like the highest signal I have, like off the chart, is bismuth for the NAA. It's just bismuth. It's like, bam, it's like 10 times bigger signal than everything else. Why is that when it's mostly magnesium and zinc? Okay? And so what that means is that you have to be very careful in interpreting the data, okay? Very, very careful. And so what we need to consider here is that, I'm sorry, I got distracted because I got a chat from Jarod. So Jarod has pointed out, and I said I might be wrong. To be fair, I said Jarod will correct me because Jarod has researched the crap out of this. And Jarod has corrected me, the Ubatuba sample did have NAA. So that's excellent. However, I talked to Hal, I talked to Eric, I talked to Travis Taylor. I did not talk to Lou, but I talked to all the scientists. Like, they told me NAA, didn't even think of it for arts parts. And I'm like, what? And so like, so, okay, this is not the first. Okay, it's not the first, but I think it's the first, at least for arts parts. So I'll have to correct that later. But anyway, back to my main point about the peaks. So you could get a peak from something that's like barely in your sample. That's like 1 part per billion. And you get a huge peak from it. If it happens to love to eat neutrons, and it happens to create a strong gamma ray or beta or both, and that's easy to detect. So the height of the peak in NAA is about the ease of detection. It's not about how much there is in something. That's a disadvantage, because then you miss the big things, but it's also an advantage, because the advantages is then you're going to find the things that are very, very tiny amount. But then the disadvantage to the advantage, second order, is you have to be careful, because what if what you're seeing is a random low-level impurity and was not intentionally part of the sample by whoever manufactured it? So that's the danger. So we have actual preliminary results on one of the art parts. I'm not talking about the art part. I am, but I'm not showing any pictures or the story about it because Jarod already did. So for context and for the backstory, see Jarod's talk. But at my office and lab last fall at University of Albany, soon after the APEC anniversary dinner held at Falcon Space in New Jersey, Jarod visited me. Jarod Yates visited me with Tim, and we did 5 hours in California 252, and then about 2 weeks of counting back in New Jersey. And so plenty of photos. So one of the things that I'll get bombarded now by emails afterwards from Tim now and Mark, I couldn't find where I saved in the links to the photos. So like Mark took a crap ton of photos of the plutonium test, Tim of the California, and I'm like, oh, I'm going to put that in my talk today for March 15th. I couldn't find them, and I was trying so hard. I'm like, but Tim's got an Instagram, and like Mark has an Instagram, tons of photos. And I just was looking through my emails, and I just couldn't find them. And I didn't want to email them at the last second, be like, hey, can you send me the link? Because by the time they saw the email, it would probably be too late anyway. So anyway, mea culpa. But I should have had way more photos of what we did. There were problems with the initial data, though. First, piecemeal. So we had file restarts on the Cosmic Watch we were using as our radiation detector. The device was moved. This was solved with newer tests we did where I borrowed a battery from Mark that will solve any issues with like restarts from like temporary minor power failures in my lab. Not all sides were covered. So and also not moving it anymore. So not all sides were covered also in the initial testing. But that's fine. We solved that. Now we surround the sample with 2 radiation detectors and kind of like to try to capture all the betas and gammas that are coming off. We also had issue with file and data corruption. We not only have beta radiation detectors now, but the old ones, the Cosmic Watches, were repaired. It had nothing to do with radiation, actually. The Cosmic Watches can take all kinds of radiation. And remember, the sample itself does not become that very radioactive. But now, the most mysterious problem of all is the sample, after 5 hours on the Californium, was barely radioactive. Okay, this is very strange. You can't just chalk this up to the small size of the sample, because I've taken small sizes to calibrate and the NAA technique. I've taken small sizes of like chunks of all kinds of elements and isotopes and just done all kinds of tests. And I usually do 5 minutes on the Californium. And with 5 hours, this thing was like 3-4 times more radioactive than just the environment. Like the sample was so not radioactive, you could have eaten the sample and not died from radiation. Like it was so not radioactive. I've never in all the years I've been pursuing the NAA, I've never seen something that not radioactive after sitting on Californium 252. Now, to be fair, the Californium 252 sample has been decaying away over the years. So its half-life is only a couple of years. So the sample is significantly weaker than I first had it. Nevertheless, I could take another sample, and I did, of things I've tested before, put it for a few minutes, and on the Californium, it's much more radioactive, several hundred, several thousand hertz, and that goes up. That goes for things up and down the periodic table, and so that's the strangest result that we got, is that it gets actually, no, it's not the strangest. Again, it gets even stranger, because then we decided, oh, you know what, we'll put it next to plutonium, and then it's like, oh yeah, we have an old chunk of plutonium. Don't ask how or why. It's on loan at University of Albany. We have officially owned, like, I think it's a few hundred grams. Like, it's a decent chunk of plutonium. I mean, Mark will tell you he saw it. He took pictures, and we put it next to that. We're like, oh, this is gonna be great. This is gonna be amazing. Okay. We saw nothing. Not a little. We saw nothing. Like nothing. Okay, maybe when we first grabbed it off the plutonium, it was maybe like 0.1 counts per second higher than background, but that's it. Okay, what the hell? Now, part of the issue is, as Jarod explained, energy spectrum matters. And I said earlier that ambi can't be used, for example, for neutron activation. There's no mystery there. You put something next to ambi. But this is plutonium, beryllium. It's not pure plutonium. There's pure plutonium inside. But then there's beryllium, which is used to reflect neutrons and to change the neutron energies to where you should be able to use a plutonium beryllium source for neutron activation. You should. And it's also much higher flux than either the Californium source. So energy spectrum alone doesn't seem to explain this. I mean, we'll follow up with computer simulations of this plutonium, although we need to see which isotope of plutonium it is that we own. But this seems really strange that there was no activation from the plutonium beryllium source. Again, I have to caveat that with, we'll go back and test, because I haven't tested other sources with the plutonium. Got to make sure, is it normal? Could it just be the different energies? Like Jarod was saying, although the energies are too similar, if I look at the energy spectra, the differences, so the numbers that Jarod quoted were only averages, but the overall spectra of these sources are similar enough to where I'm like, well, what's going on? And it's not a sufficient explanation in my mind, but I have to check it mathematically. To me, it's not a sufficient explanation to say that, oh, it was activated, but everything decayed away, because then why isn't it constantly reactivating things with all the thousands of neutrons per second it's getting from that source? So it's strange that the plutonium, it was just remarkable to me that there was no registration of activation from that. So did we get anything at all? We did from the Californium. As Jarod said, not enough statistics for isotopic determinations, unfortunately, initially. So we did more tests, as Jarod said, more Californium, and I hope that by the end of this year, or hopefully by June at least, even we may be able to start getting through some isotopic ratios. So right now, we just mostly confirm same old, with a few extra surprises. So if you look at the list on the left, there are some actually additional surprises that I didn't add to the list that include argon, silicon, and some of the R elements. And I always confuse them. So it's rhodium and ruthenium, but not rhenium, not Re. What was really confusing is RH is rhodium, Re is rhenium, and they both start with an RH. And it's like, it's really annoying. All of those might be significant, so especially the argon. I'm going to come back to that, but the RH and the Ru, these are things that if you look up, well, where are these elements used? They're used in like aircraft and car engine parts and high temperature applications. So so that could be, those could be certain hints. Although with the caveat that we don't know if those elements are pure, right? We don't know if it's RH with something else. We don't know, because neutron activation doesn't do that. So we need to be extremely cautious about drawing conclusions that this element is used for this purpose without knowing whether it's just that element by itself. In some cases, we did, like Jarod was pointing out, some of the things like gold wires, and where we can say, oh, that's the element like in a pure form. But we need to be very cautious, because don't forget, H2O, which is water, has none of the properties of hydrogen or oxygen, which are gases at room temperature, and like oxygen you breathe, and hydrogen's flammable, and like that has nothing to do with water, right? If you put elements together, their properties of their compounds have nothing to do with the individual elements. We have to be cautious about drawing some of those conclusions. Now, there's silicon in there 100% for sure. It's not on this list on the left that I preliminarily sent to Jarod a few months ago, but I was gaslighting myself about the silicon, whereas like, it can't possibly be in there. It's not in the Aero report. And it's not in any of the other reports that Jarod had sent me about the arts parts. But then Jarod emailed me about quartz that he believed he saw in the microscope. And I'm like, there is silicon. Okay, so I was like gaslighting myself, because silicon kept coming up and coming up and coming up. And I didn't trust it enough to put it on the list on the left, even with a question mark. So you'll see a lot of things with multiple question marks, like neon. Is that in there? That is, again, we have to be, since the results are preliminary, very, very careful and cautious here. Now, if I had time and money, I would love to also test more samples, but I don't. Not at this time. But I want to thank Mark and thank Jarod and Tim profusely for letting me come so late into this big conversation, into this, this big story of the parts and testing these unknown parts. Now, you should compare my list, compare Jarod's list to the Aero report. Here's a link to that again. I'm sure it was in Jarod's slides. We found preliminarily way more elements than Aero did with Oak Ridge National Laboratory. That said, remember, be careful, because some of these might be trace elements that are not there on purpose. So, but at the same time, currently my thinking is leaning towards the Aero report being woefully incomplete. And I'll talk more about that shortly. So I should have more complete results by the SCU conference in June. I hope people can attend if possible. I'm giving a talk on crash retrievals, and I'm going to sneak this in. I'm going to sneak this in to the end of that, to the end presentation in June in Alabama. So if you can come to Huntsville, if you can't come in person, please at least register to attend remotely. So Jarod mentioned color changes. So we definitely saw, I'm almost certain we saw a color change. I wish we could be more certain. But the problem is, again, not being prepared to observe that. I wasn't prepared because we were doing I'm testing isotopes. Why do I care what color the sample is? In retrospect, got to be more cautious about that because radiation can change the colors of things. I had forgotten that myself. This may not be anomalous then. This may be what happens to something like the art part. So here's an example of a Coke bottle, famous example of a Coke bottle that irradiated. Now, one of the reasons I was not expecting a color change is because usually that takes nuclear weapon level, amount of radiation. So it's a little strange that, if you look at Jarod's presentation, he seems to show evidence of a color change. This does strengthen, this does not weaken, but this does strengthen Jarod's idea of he called it the mithril, that the idea that he got from me about the neutron, that maybe this stuff is supposed to act like neutron shielding. I had another idea though, which was my idea was I wasn't thinking about the color. I was hoping the mass would go down after irradiation. I had this crazy idea where, okay, we're doing this irradiation for neutron, for NAA, and I was thinking, what if there's some kind of magical inertial reduction or something? No, that didn't happen. I forgot who I got that idea from specifically about bismuth, because I met so many people that day that sadly, I want to give credit to everybody. It was like the first person, just when you walk in through the door, who was working on something when I visited Falcon. And Mark, and I just don't remember who it was, but somebody was talking to me about metastable states of bismuth, which I will come back to later, where I thought, oh, maybe there's some kind of mass reduction thing going on. No, that I think that was barking up the wrong tree. I think it was something very unexpected, which is the substance seems to do really well in terms of neutron irradiation. So some more follow-ups that we did. I said we tested with multiple californium exposures. We had battery-assisted cosmic watch sandwich in one spot. We did a sandwich of 2 of the radio codes, which are way better. For $200, $300, you can buy something that outperforms $10,000 radiation detectors. It's amazing. Highly recommend it. This is radio code 102. You see a picture of it. That's the model number. You see a picture of a hand holding in the upper right. This device does automated isotopic detection. And I wish I had that today. All I have for you are plots that are not analyzed yet because we haven't had time. My student Mia, who actually joined working with me and my colleague Cecilia and Kevin Knuth. Why is she working with us? Because she saw me and Kevin in the movie A Terror in the Sky. And so she wanted to work on UFOs. And finally, I think we gave her a project that's related. So what you see are these peaks, and these peaks are mostly from gammas and X-rays, but the ones that aren't very well resolved, the ones that are really fat, are probably those are betas, because betas don't give you single energies. So I'm showing these pictures, but we cannot get our hopes up for an isotopic analysis, only elemental. The reason is the radiation levels being so low compared to what we were expecting. We might not get enough statistics from this data to be able to say this peak is this percentage of that one. It just may not be able to stand up to even the Arrow ORNL tests that they publish using ICP-MS. That said, I think that we could try to do isotopic ratios for different elements than they did, because they only did like 2 or 3 of them, and to me that's very strange and very suspicious. So what's really another interesting factor is it looked like a shorter exposure of to the California might do better, and so we're looking at that. It could be that what's happening, as I said earlier, mathematically, is that the isotopes that are being activated are decaying away so fast that they can't be reactivated. But with californium, since the source is so old, I think that's plausible. But with the plutonium, I'm skeptical as that being an explanation for the weak result with the plutonium. All right, so we wanted to do, my student Andrew, I forgot we even had this technique on campus. He wanted to do an X-ray fluorescence. So this is an important cross-check. So X-ray fluorescence tells you elements, though, not isotopes. So we have no way, you're not going to use this technique to say whether something's terrestrial or not. That's not going to happen. But it could be a cross-check of the elements we've detected. And as you can see here, xenon's off the scale. And so like with, this is like one of those more traditional techniques where it's almost a little bit more intuitive, where higher peak probably means more of that thing. But here's what I find remarkable. My student, Andrew, who's a very smart guy, but this is like, he didn't invent this. This is like a device in the ion beam lab. He did a better job than Arrow in 20 seconds. 20 seconds. Okay. That's very suspicious to me. Like, how the hell can I do a better job with my student at University at Albany? Again, we are not Harvard. We're not Yale. Like, what the hell is going on here? We're not a national lab. Like, why did we do a better job on the elements in 20 seconds? Like, not better than the isotopes. Like I said, we couldn't get isotopes than this, but we found elements not listed in the Arrow report. And Jarod pointed out to me, he texted me today, that there's in the Arrow or Nell report, there's a sentence there about, well, things below detection threshold are not there. I'm like, how the hell can some of these elements be below your detection threshold? We have screamingly huge signals from several of them. So this is our nearly final. So the NAA, nowhere near final. And so I might delete elements you see from this talk today to be like, that was a mistake. We did not detect that. It was a mistake in the software or in my analysis. This is closer to final. Andrew still wants me to say, this is not, he doesn't have a final PDF, does not have a final report on this, but this is much closer to final than the NAA. Even though we've been trying to do the NAA for months and years, this is a 20-second thing. So because it's 20 seconds, of course, he did it over and over again, and he flipped it to both sides. The results between both sides are absolutely consistent. There's no differentiating them significantly. But what's really interesting here is this was also detected with the NAA. It wasn't my list in the NAA, but what about ND? We found neodymium. We found, again, some of these R, elements in there. And these are not cases of elements right at threshold. Okay, these are elements there where you can look at the counts and you can look at the statistical significance. These are not things that you can justify throwing them out and saying they're not there. Oh, they are most definitely there. And so when we publish an actual scientific paper on this, we're not just going to have a table. We'll show the peaks from the X-ray fluorescence, just like we have peaks from the NAA. Now, here is where I have to give huge credit to my student Andrew and to my colleague Cecilia. The presence of argon. Argon, right, is a gas, but it could be compounded with something else, and then it would be in the sample. This is very suspicious because it's used in zinc and magnesium mining on planet Earth. So that's very, very suspicious. It's a noble gas, so it's good for dealing with flammability of magnesium. Now, when I pointed this out to Mark, he pointed out to me, oh, that's just 1.3% of the atmosphere is argon. That's contamination. No, because we use XRF all the time, and there's never an argon signal, ever. It's not done in vacuum, but the thing is with XRF is like, you need a solid chunk of something. 1.3% sounds like a lot, but air has a very low density. So we are not detecting the argon in the air, because if that was true, we would have an oxygen signal off the scale or nitrogen. We don't. And so the argon is definitely in there because we also see it in the NAA. And that's another one where I was gaslighting myself, where I was like, there's no argon. What the hell is argon doing? And I'm like, it's got to be wrong. And it was like with the silicon. And then we see it in the, like a screaming argon signal in the XRF. And we're like, well, shit, now it's two different techniques. And so this is very suspicious because in terrestrial mining, this is what you use for, especially for magnesium, because of its flammability. Because argon's a noble gas, so you use that in when you're mining or refining or manufacturing high flammability materials. So this is very, very, very suspicious. So now, one thing to think about, though, is we have this giant number of elements, right? And Gary Nolan has always said, like there's someone who's out there who's quote unquote painting. His analogy, I think, was painting like an artist with way more elements and isotopes than we do. But there's a flip side of that: is could these all just be impurities? Because that goes then back to that helps the slag hypothesis. But you know what? A piece of slag is not going to have these wonderful shielding properties, and I don't think it's going to have these microscopic structures that we saw from Jarod. So I don't think that's a satisfactory explanation. But the argon is very suspicious in pointing towards the materials being manufactured on Earth using processes that we have here. So what are our current best hypotheses then? Since this is so good at neutron shielding, before we went into the argon and things like that, I thought immediately, spacecraft hull, right? What do you need to traverse space? So what's going to traverse space is you need shielding to do so, right? So in order to traverse interstellar space, if you solve propulsion, that's not the entire solution. And I had like a big back and forth with Mark, whom I met for the first time in person at the SCU conference last year. Tim was there, took some great photos of me talking, giving my talk there on UAPX stuff. But I got into like a heated debate with Mark. I'm like, you could have you could solve propulsion, you could have anti-gravity, this and that. You still can't traverse the universe because you also need to solve shielding. Because if you're traveling at relativistic speeds, starlight will kill you. It becomes fatal. It becomes Doppler blue shifted. Starlight would even kill you. Cosmic microwave background would kill you because it becomes Doppler blue shifted from microwave up to ultraviolet. Okay, so basically, we need to be extremely cognizant of the fact that even if we solve propulsion, we need to solve shielding. And so I got really excited because neutrons are neutral particles, so you cannot shield them electromagnetically. No way. No how. I don't care if it's 10,000 years from now. I don't care if you're a billion-year-old civilization. And this is where I got a debate with Mark. I'm like, no, it's not scientifically possible. You need magic, not science. Like neutrons are neutral particles. And so what do you do about them? What do you do about the gamma rays I mentioned? You can't do anything with them electromagnetically. What's good for electromagnetically is to repel charged particles. That will work. I believe you could create like a Star Trek or Star Wars type deflector shields maybe someday. Absolutely. For charged particles. But neutral particles, yeah, that's a non-starter. And neutrons are neutral. So that seems pretty great, right? Here are the cons to that, though. I'm showing you pros and cons because Mark pointed out very serious flaws in this argument. And Jarod, it's brittle. You touch the part, right? This thing can crumble. So the cons are this is too brittle. Maybe it's brittle from crashing. Also, neutrons are not the biggest problem in outer space. They are not. Gamma rays are, and other particles that are charged. Like, what's going on? The neutrons. So I got super excited initially, but then I realized, but neutrons are not the main problem in outer space. Where the hell are neutrons coming from? It's muons, it's gammas, things like that. And why does the sample appear terrestrial? It's not just the argon, it's also the isotopic ratios that we do know. Again, of course, do we trust Aero? We're going to try to replicate it ourselves, but the sample appears to be terrestrial. And I asked Eric and I asked Hal Puthoff to confirm that. They said, yes, every isotopic ratio. They claim to me that even the ones that are in the reports that's like you can't FOIA, that are classified, like none of the isotopic ratios come out to be extraterrestrial. So, okay, so what's going on here? So what I want to suggest is that maybe this has nothing to do with propulsion, or maybe it's a red herring. Maybe we're thinking of it reductionistically. So it's entirely possible that everything that Jarod listed is true, but so is this. And so maybe this is the equivalent of taking your laptop, smashing it into bits, and giving it to a scientist from the 1890s. Okay, maybe we're thinking of this the wrong way. And maybe this doesn't just have purpose number one, and that's the only purpose, has purpose X. Maybe it has purposes X, Y, Z, et cetera, et cetera. And so, yeah, I just saw in the chat, why would something that Aero says in a nothing burger be beyond FOIA? Yeah, exactly. Exactly, Brendan. Yeah, exactly. What the hell? And so there's a 90-page report out there that I've been told, don't talk about it, don't ask about it ever again, because it's been hidden using private companies. And so it's FOIA exempt, so you will never see it. Period. Don't waste your time. And so what's the next best thing we can do is we can do our own analyses like this, and we can rediscover what has been hidden from us and figuring it out on our own. Now, one of the biggest things I need to mention, because there was going to be, I think it got canceled, got rescheduled, a talk on nuclear fusion. A neutron activation resistant material would be a godsend to nuclear fusion, a godsend. Because the reason why don't we have like tokamaks and this and that, nuclear fusion power plants powering everything, right? What's taking us so long? Because I don't know if you guys know this, but I'm sure you do. If we had a nuclear fusion power plant, we'd have to disassemble the damn thing every 10 years because it would be so radioactive from neutron activation. Like, it's still safer. Of course, way safer than fission. You're not going to get a Chernobyl or a Fukushima. Nevertheless, you're doing alchemy basically on your fusion power plant. You're neutron activating the crap out of it. So basically, if this material does what I'm claiming today to use, that it's neutron activation resistant, not proof, not neutron activation proof, because we got it working with the Californium, but it seems to be neutron activation resistant. If that's the case, and it's not just because it's a thin sample and the neutrons are passing through or some mundane explanation, that would be a godsend to nuclear fusion. So actually, my colleague, Professor Cecilia Levy, who's actually, we call her our Dana Scully, because she's always got the explanation that here's why it's not aliens. And she actually had a great hypothesis, which is she thinks she believes she's figured out what this is. This is an atomic bomb casing. And it's terrestrial. Here are the pros of that argument. There's presence of uranium. Did you catch that? Did you catch that Easter egg on my previous slides? We found uranium in the XRF. And initially, it wasn't statistically significant, but we did both sides. And now, Andrew's on the fence about it. It may not be, but I don't know if you caught the earlier Easter egg with the isotopic analysis also. Yeah, there is uranium in this, okay? And David Chester, whom I met also when I visited, just said that Michael Perrone also hypothesized it could be nuclear bomb shielding a while back. Well, damn, then he was way ahead of us and way ahead of what we just learned then. That being said, again, a word of caution. I'm not concluding that for sure. Absolutely not. Because Mark has pointed out some serious flaws. But first, let me give you the pros. What the hell is uranium doing here? Number one. Number two, what about the neutron shielding processes? And this is even more damning. You ask Google Gemini or ChatGPT, magnesium, which, remember, this is like 97% magnesium, is used for uranium refinement. And this would also date to the correct time. It's late 40s. And here's another thing. What do nuclear explosions do? They make lots of elements. Right, through neutron activation. Now, what about the structures Jarod saw? Now, again, I'm not selling this argument. I'm absolutely not poo-pooing what Jarod showed you. I'm just giving a devil's advocate counterpoint. I'm not saying I believe this argument myself, but those structures that Jarod showed, let's say, again, devil's advocate for the sake of argument, let's say, what if they could be similar to what you see in trinitite, samples of trinitite, where you do see structures that were created that look man-made and look like advanced technology, but they were just created by the explosion. That might explain the silicon also, because you got sand. However, here are the cons of that argument. Mark said, well, how the hell would a little piece survive the explosion if it was part of a bomb test? And he reminded me there's a mother piece, right? And so there are definitely cons to this argument. And so we cannot conclusively state that. I actually confronted Eric Davis with that possibility. He goes, these do not match any elements that are in nuclear bombs that we make. I'm like, okay, all right, but this sounds like I got excited when Cecilia said this and Andrew, and I'm like, I don't know what to think anymore. So I'm going to make one bold claim, though, which is we do have evidence this does something. Not that we think it might do something, but we actually have quantitative evidence that it appears to work as a good neutron shield. Even that, though, there's some still chinks in that claim, is chinks in the armor. Why are there no obvious neutron absorbers and poisons in it, like gadolinium? Where's the gadolinium? Gadolinium is used, for example, in my dark matter experiment. We use that as an outer shield because that'll just gobble up neutrons left and right. It actually, gadolinium isotopes have the highest neutron cross-section, capped cross-sections known to humankind. Why isn't it in there? It doesn't appear to be in there in any of the analyses. Beryllium, I thought beryllium was in there, but now I'm really questioning that. There was a software glitch where it just so happened that beryllium had a half-life that just matched with where I was getting a false positive peak. So I'm not so sure anymore. We do see cadmium, and I pointed this out to Eric, but a small amount of cadmium. And so not enough to be used as a neutron poison. So what I was thinking is, could we be dealing here with nonlinear multi-particle effects? So could it be, and I recently saw a YouTube video by Professor Sabine Hassenfelder, really like her, and she has a video where she says, you know, we've run out of discoveries in science of new particles, like we haven't found anything since the Higgs boson, I haven't found dark matter. What if the new discoveries are all in multi-particle interactions, where we put the particles and the isotopes and the elements we already know and love together in bold new configurations? That might be the next frontier in all subfields of science and engineering. It's that we've run out of new particles to discover. Is that true? I don't think that's true. You know, I still look for dark matter, like I said, but what if she's right? And what if what we're going to discover now are, you need to put this isotope together with that one in just the right ratio? And so what if the reason why this works as a neutron shield even without gadolinium and beryllium is that, what if there are nonlinear effects where you put these isotopes together in just the right ratios and bam, you get better neutron shielding than anything else? Now, I'd love to, I need to point out, and this is just some friendly ribbing on Jarod, where Jarod and Tim show up in my office with lead vests, and I'm like, oh my God, guys, don't you know that lead makes neutrons worse? So neutrons are not like other radiation. So lead is bad. Lead will make neutrons worse because you'll have what's called spallation, which is just a fancy word for fission. So if you want to block neutrons, you need water, oil, wax, plastic, concrete. This is none of those things. And yet it seems to be really interesting. So I am no longer convinced that this was, at least I don't think this was manufactured off-world. Asterisk. I put an asterisk there because we still don't have all the isotopic ratios. We only have the ones that were published by Arrow, so that's why I put asterisk. But I think that this material has very interesting properties. If it's from Earth, could it be from some, is it from Wakanda? I don't know, some, breakaway civilization? Because like Jarod said, I don't think we had some of the technology he's finding evidence for in the microscopic images. I don't think we had that technology if the sample is really from 1947. So moving forward, what's the plan is get a peer-reviewed scientific paper published, and I want to put Arrow to shame and put Oak Ridge to shame. Oak Ridge specifically should be ashamed of themselves because it turns out, I visited them last summer. It was just random accident, part of a conference. They're the world-leading experts in neutron activation analysis. Okay, so why did they not do a neutron activation analysis? Or maybe they did, and it's in the 90 pages we're not allowed to see. I just realized, I'm like way out of time, but fortunately I'm almost out of slides. And this is really funny because earlier I told Jarod and I told Tim, oh yeah, I'll have a very short presentation. But I just keep going off on these other tangents, but I have a very small number of slides. But the trick is, I want to turn the peer review process around on itself. I was telling Jarod this the other day. I want to make an instrumentation paper where we just tuck the art part in, just sneak it in, just slip it in at the end, be like, oh, there's some unknown thing. We don't know what the hell it is. And not use the word UFO, UAP, definitely not use the word Roswell. And we just play dirty. Where basically we just say, oh, we don't know what it is. And then after it's too late and the paper's published, we'll be like, by the way, everybody, this is what that was. And so it's sneaky, but here's the thing. I'm sick and tired of the stigma and the taboo against UFOs preventing us from publishing physical evidence. Because Neil deGrasse Tyson's always whining about how, oh, it's just blurry photos. Where's the physical evidence? So if this is actually an anomalous metal part, I want to be like, bam, here's physical evidence. And then their counter argument is, then where is it published? Well, you don't let us publish it. Because as soon as you have the word UFO, it's not allowed to be published. But so you know what? We're gonna be sneaky bastards. We're gonna get this in. So Jarod told me, but wait, this is live stream on YouTube. And I'm like, yeah, so physicists in my field, they're never gonna go. They're not gonna see this YouTube channel. It's gonna be totally fine because yeah, it's gonna be fine. And so basically, that's actually extra insurance because I told Jarod, you know, look, there's a difference between lying and not saying anything. We just don't say what the part is. We say it's unknown and we publish results on it. And then if we get in trouble, we're like, but there was a viral YouTube video. Did you not see it? And so it's insurance policy today to be like, but we have a YouTube video from several months ago. Not my fault. You didn't, you know, and so it's like I put a chess piece on here. We're thinking it's a chess game, and we got to think multiple moves ahead of the debunkers to really move things, to be able to move things forward. So this is my last slide, and I'll be, you know, thrilled to answer questions about this. I think we do have time because even though I ran over, I think we had a 1 hour hole that opened up because of a rescheduling. But please be patient with us because we're not going to be able to finish this analysis and publish it for many, many months. And it's because I'm not paid to do this. But you know, neither is Jarod, right? And so we will have hopefully further results by June and hopefully final by the end of the year. But, you know, here's a little shameless plug. I know we all need money. Everybody here at APEC, they need investors, they need money. But for a really, really small number, really small, $30K per year per professor. So if you want me plus Kevin, so this is just the change on the nightstand for a billionaire like Elon Musk, for example, or even for a millionaire. This is change on the nightstand. If somebody right now listening to this video on YouTube wants to pay me $30,000 a year for the rest of my life, that only covers my summer salary because University of Albany covers my salary during the year. I will drop all of my other projects and work only on things related to UAP. I've been saying this for years and nobody's been listening to me. They think I'm joking. I'm not joking. This would not cover equipment, of course. It would not cover supplies, but this means I would, for 3 months of the year, I would drop everything else, but even for the rest of the year. So what most people don't realize is how academia works. So if you're a professor, you're paid for 9 months, and then you got to scramble for the other few months. But the way it works is whatever you're paid for those months of summer, you also work on the rest of the year part-time when you're not teaching. So for paying for me for 3 months, you get me for almost 12. And so somebody out there who wants more stuff like this, if you're willing to give me 30 grand a year for the rest of my life funneled through to UAlbany, to my university, I will drop every other project I'm working on right now and work only on UAP related projects. And that's a tiny ass amount of money if you're a rich guy. If you make that 60K, you get me and Kevin. Make that 90K, we'll convince Cecilia to join us. Like I said, she's our Dana Scully. We need her too. And so we're looking for investors, and I will be at Deep Tech Week on April 4th in New York City, looking to shake hands with somebody who's got a tiny amount of money to part with. Because again, you're a millionaire, billionaire. This money is a joke to you. It's change on your nightstand. You give me that change on your nightstand, you will get great things. Instead of 1 year to do a neutron activation analysis, we'll be done in a month. And to analyze all the different peaks and get what the isotopic ratios are and everything. I'm also looking for investors for my small-scale nuclear reactor that I don't have time to talk about. Patent pending also on it is I've come up with a new type of fission-fusion hybrid. It's patent pending through UAlbany is yet another thing, but that's a whole nother talk. So with that, I'll conclude because I went an hour 15 when I promised Jarod and Tim I didn't need this much time. So I'm going to conclude there, and I'm very happy to answer any and all questions. Thank you.
That Matthew, amazing. I do not have the words. Absolutely stunning. Let me leave that up for just a moment. I'm going to bring everybody back in. So we absolutely have to give Professor Matthew Szydagis a giant applause. Man, you brought it. I mean, in terms of evidence, in terms of data, in terms of energy, wow. And so the reason I left that slide up was people should register for the SCU conference. Absolutely. Visit explorescu.org right? So that's one thing they should do. Think about the funding thing. If you know any millionaires or billionaires for whom that would be chump change, give that some thought. Again, exploresu.org or uapexpedition.org. And Matthew's bio is on there. And so I have some stuff I want to share as well in a moment, but let's do this. If it's okay. Okay, so now I'm going to take the slide down now. And I want to see, okay, so he is not here yet. So I'll give him a few more minutes. Michael Perrone has Frank Kimbler bounce site samples. And I think that I've been chatting with him, but he is trying to get things organized. Again, we are ahead of time for today, which is awesome. But I think that his schedule was like an hour behind still. So do you guys want to do open discussion right now? I mean, questions for Matthew? I guess that would be the place to start.
Yeah, I'd be very happy to answer any questions. Hit me with hard questions.
I've got some on board here. Hi, guys.
Hi, Brandon.
Hey, good to meet you, Matthew. Excellent presentation.
Thank you.
So about halfway through your presentation, and given Jarod's presentation, I was screaming in my head, radiation shielding, because it's one of the major concerns with going to Mars and further, right, leaving the Earth's magnetic field. So that makes a lot of sense. But what sprung out to me is, I don't know who else watches or follows SWR stuff, but they were digging in the mesa and they found a material that they had molecularly analyzed that showed some commonality with thermal shielding on the space shuttle tiles, right? And so this stuff seems like some sort of it's almost like thermal tiling, except way more advanced and for a much broader spectrum of radiation than just infrared. And I wondered if anybody had, in your team or anybody else, had been in touch with that group or got to see that stuff, whatever they found structurally, to see if it's anything like this, because they didn't cover structure.
Yeah, no, unfortunately, no. I probably shouldn't say this in public. I got to choose my words carefully. I already said something I wasn't supposed to, and Jarod yelled at me already in the text. But we've had a difficult time. I love the scientists. I know Eric Bard and I know Travis Taylor very well. But the issue is because there's a production company involved in this, that, and NDAs, it's very hard to do an open discussion. And so the problem is, because there's a TV show and a production company, that's not conducive to open, free science and thinking out loud. So anything they would tell me, they'd violate their contract. So I'm not blaming them at all. And so I'm not permitted to talk details with them, which is, I think, a horrific shame, because I feel like the way we're going to solve this problem, the mystery of UFOs, mystery of how do we get better propulsion to get humanity to the stars. This is something where we all need to bring our pieces of the puzzle to the table and put them on the table. Because I think we can't play the game. And again, I'm not blaming Travis or Eric on this. No, I'm not. But we cannot play the game of we're going to all take our toys home and we're just going to play at home with our toys and we're not going to talk to other people. And so I would love to get the details, because I know which episodes you're talking about. I know, Brendan, exactly what you're talking about. But thanks to your question, you reminded me something I forgot in my talk, which I think is blows my mind and makes me so excited, and yet I forgot to mention it, which is some of the bismuth isotopes in the sample, they have half-lives of several million years. So what that means is let's say this is radiation shielding, either for a bomb or a ship. Again, I'm trying to be neutral. I'm not going to sit here and tell you we've conclusively proven it's an alien ship. I wish I could, but we're not there yet. And so regardless of what it's for, I think the bismuth has this very important property where it'll eat radiation and just hold on to it for several million years. And to me, I'm like, wow, what else would you want from radiation shielding? And so basically, it doesn't break any of the known laws of physics at all. And these are just well-known bismuth isotopes that will just eat a neutron, and it'll go into what's called an isomeric metastable state. And it has a half-life of several million years. So what that means is you just take in radiation as you're traveling along, and you rendered it safe. You lock it away for a few million years. And I think that's just wow, who thought of that? What genius, human or non-human, right? Who the hell thought of that? But to me, that's one of the most amazing things about this part is the fact that it's like not thermal. It's different than thermal. Like you said, it's a more broadband type of shielding.
Matthew, where do you think that table is?
Sorry, which table?
You said there's a table where everyone brings their stuff and then takes it away.
Oh, Mark is
speaking
pushing for New Jersey.
Metaphorically. I was metaphorically speaking. That basically, I think that just like APEC is working together on propulsion, I wanted that to happen for all of UFO and UAP studies, where everybody who's got a piece of the puzzle comes together at the virtual table, probably on Zoom or StreamYard or Google Meet. So it's a virtual table, Mark. You're being way too literal.
Well, if it's a virtual table, it could be at APEC or it could be at Sol or
yeah.
Drew, go for it, sir.
Drew has a question. Yeah.
Yeah, I'm really a novice when it comes to radiation and such, but if you have a material and you wanted to say charge it like a battery, would radiation be able to like charge up a battery? Like let's say you had some sort of battery that operated on radiation. Could you use the radiation as the energy source to charge up the battery?
Yes.
You're saying that this stuff is radioactive for billions of years or something.
That's right. And so I should clarify because it seems contradictory because earlier I said it's radioactive for short periods and not at all. Because of the multi-million-year half-life of bismuth, we're not going to detect that. It's very, very faint. But to answer your main question about the charging up, the answer is yes, but it's at just in a gray area. It's at the current cutting edge of technology. And in fact, it just so happens to be one of the things I'm working on right now. I mentioned my modular tabletop fission reactor. One of the ideas I've had, and I'm talking to other companies and people have similar ideas we can combine, is could you use radiation to store energy and convert that to electricity? And the answer is yes, but it's very complex. And as human beings, we do not yet know how to do that. Not on a small scale, but we're kind of getting there.
Okay.
We're kind of getting there.
Yeah. I got a yes out of that somewhere.
Yep. Yes.
So if I had a magic cracker and it didn't do anything until you charged it up, but when you charged it up, it generated lift or thrust. And I put a whole bunch of radiation into it because it's designed to absorb the radiation. Then I would have a material that's charged at the factory that stays on as needed.
It's plausible.
Because I see that every day on my testing.
Yeah.
I can charge up one of my thrusters with actual charge, actually electrostatic charge, and it stays on. So maybe the little alien dudes are clever enough to figure out a way to charge up their spaceship engines with radiation that just locks the energy in the molecular structure for whenever they need to use it.
That's very plausible. Very plausible.
You know, if I could jump in, actually, Drew, I think Drew, I know where Drew is kind of going with it, but you're bringing up a really interesting, larger idea, which is the universe, right? And Matthew, you work with dark matter, so this would be the universe is full of energy. It's all around us, and it's an intriguing notion. So what if your radiation shielding was able to convert those cosmic rays into some kind of usable electricity?
Exactly.
That would be really interesting.
Now, I'm not going to tell you I have all the answers, or Jarod, or any of us, because there's a flaw with that hypothesis, which is, I mentioned the bismuth. This ties in with what Drew was asking. I just mentioned that you can charge up the bismuth like that, but only with neutrons. And then, as I point out in my talk, that's not that great in interstellar space. But maybe we have only one tiny fragment. Both literally, we have this tiny art part, and also figuratively, we only have a small piece of the puzzle. What if there are other parts of the hull that are designed to take care of gammas and the other radiation and do what Drew said? Because I think I've solved like 0.001% of the mystery, small piece of the mystery.
What if they just charge up their little toys at the factory?
Yeah.
And what if this isn't radiation shielding? What if this is part of the engine and they literally charge it up at some
No, but what if it's both?
Whatever.
What if you turn? This is where
Jared,
Tim's
start
getting at.
talking.
Yeah.
Yeah, Jared, go for jump in, Jared.
Oh, Jared needs to jump in. Yeah.
I just wanted to say, so during your presentation, when you're saying, you're accelerating through space, and as you get closer and closer to relativistic speeds, right, all of the incident rays are getting blue shifted, right? The wavelengths of the incident energy is getting blue shifted, right?
They're all fatal.
So,
yeah.
Yep. So you've started putting in all this energy to accelerate, right? And so now that you're accelerating, you might be able to recover some of that lost energy from the acceleration process by harvesting the now blue shifted instant beams. If you wanted to do that, you would probably need to have resonators that are able to resonate at those wavelengths, which would probably be, if I had to guess, around the 10 nanometer to 20 micron range, maybe, like all of the little balls and beads on this thing. It's an interesting idea if maybe there's a whole like ramjet angle. This is just what I was coming up with during your talk.
That's exactly what I was trying to say is I was in answering Drew. I was saying maybe it's different than what Drew suggested. Maybe you don't need to charge it up at the factory. What if the harmful radiation itself, you've just turned your biggest downside to interstellar travel and you've just converted it into your best friend? And you take the radiation that's coming at your ship that's unavoidable, and instead of fighting it, you work with it, right? It's like the expression rolling with the punch, right? In mixed martial arts, again, fighting, roll with the punches. And what if you roll with the punches? To me, what's so astounding is, I said this in my SCU talk last year, even if we can't prove this is alien, to me, this is an inspiration for the scientists and engineers, like the people here, to build the future, is to see this, something like this, and be like, maybe we can actually do this and do that and have, wormholes and inertial propulsion. And so even if if aliens don't exist and there's no warp drives and wormholes, which again, I don't believe that, but even if that was true, what if all these ideas inspire us to make tomorrow happen today?
I want to jump in. I was just thinking for the last 5 minutes, I've been thinking that even if Arts Parts is completely prosaic in nature, right? Even if this whole thing is just going down a rabbit hole and we all look back and try and forget it a few years later, even if ET is not real, which I don't believe either. Right?
I don't believe it. Yeah.
but even if this is all prosaic, the process of taking this and brainstorming and using scientific knowledge and expertise to come up with new applications, you guys are, right here today, you guys have come up with at least one, maybe 2 or 3 new applications that science and technology has not thought of yet, new ways to solve age-old problems that really need the work, right?
I mean, if there was a nuclear war, Tim, I would love to have a vest this thin that blocks neutrons. You know what I mean? Like this is remarkable. If this material actually shields.
And you're talking about shielding for fusion reactors, shielding and potentially energy conversion for spacecraft, right? So like even with a SpaceX rocket, okay, you're going through space. We send missions to Jupiter in these high radiation environments all the time. So what if your rocket is able to use that instead of solar panels? I mean, there's all sorts of potential applications that come out of this. And I think that is incredibly valuable. And again, I generally cannot thank yourself and Jarod enough, as well as everybody else who's doing this work. I mean, like Mark has been burning the midnight oil. Drew has been burning the midnight oil for like several years at this point, I mean, and Bryan is doing the same thing. I mean, we're all doing this stuff and it's really exciting. So thank you. Thank all of you.
It takes a toll on all of us, for spouses, children, families. It's really hard. Because like I said in my talk, this is a side project on top of a side project. And it's like, but I'm really glad that you, Mark and Jarod, like roped me in with this art part, because I feel like I'm part of something bigger than myself, because it is anomalous. Like I said, can't conclude it's alien, but I can conclude it has interesting properties. It's anomalous.
Yeah. It's absolutely amazing. I think all this really originates with Mark. Mark is a lightning rod for strange stuff.
In that sense, the whole UAP issue is sort of like, I personally, when I was a kid, I thought the alien angle was far more exciting, and I still believe in aliens and UAP, but now I don't necessarily, you just can't say that it is ET, even so, right? So Functionally, what does it do better as, though? It's a flying puzzle box in the sky. It's a mystery. It's meant to make our ape brains run in circles trying to figure out what the hell is happening there. And so you have this material, whether or not it's that, can you look at it and can that tell you through what you've discovered whether or not this in any way explains the 5 observables with the UAP phenomenon?
Yeah. I think that we have to do it ourselves as a species, right? It doesn't mean that we can't observe what's going on and try and take lessons from that. But like the goal of the accomplishment is deep understanding. And we're not going to get that unless we do it ourselves. And again, that's what makes what you guys are doing so amazing, is you are doing it, as opposed to, people who are just like, well, somebody's going to give it to us.
No one's going to give it to us.
Yeah.
No one's going to give it to us.
And if they did, we wouldn't understand it.
No, and honestly, and if we're talking about, for example, the UFO disclosure movement, I have deep respect for people in that, like Nick Gold, but I don't think it's going to work. I think we're going to have to figure things out on our own. And the other issue is also funding, is we're not going to get federal funding. You know how many times I've had funding proposals rejected because I've literally been told it's too innovative. What the hell has happened to this country, right, in the world? How can I propose an idea that's too innovative? And I'm not allowed to have money for it. I'm like, what the hell? Like, there's something very seriously wrong with that. When scientists and engineers are disincentivized from coming up with outside of the box ideas, there's something very, very effed up about that.
Yeah, it's incrementalization. And in fact,
yes.
I've done a couple of podcasts
Incrementalization.
on that. Yeah.
You are not permitted to come up with an idea that's a sea change, that's a paradigm shift. You're only allowed to tinker at the edges. I don't want to tinker at the edges. I want to upend everything, like the people here are.
If it's okay, guys, I would love to, just for a moment, I'd like to put my screen up, and I'll show you kind of some of the stuff that I've found. Some of this I have done before, so please bear with me while I do my proselytizing. Okay, so this is my Flickr gallery. Again, I'll drop links in all of this. This is Mark's trip to do initial scanning electron microscopy analysis on the Arts Parts sample. I just want people to know that this is out there, these high-res photos. This is everything that Mark gave me. Again, we have hundreds, potentially thousands of photos, certainly hundreds of SEM photos, many of which we cannot share now, and I don't want to get into the details of that. But everything here is public. People can look at it, and it's right there. It's been up. So that's one of my Flickr galleries. The other gallery I wanted to show you was Jarod did metallurgical microscopy analysis. This was actually at the same time that we were up at your lab, Matthew. We came back and he put it on the metallurgical microscope, and he's pointing here at again, the whiskers, if they call them that, these interesting striations in the material. The photos are not going to come over StreamYard at the same quality they are online, so I will post links to this. There's actually a photo. See, Matthew was down in the lab. This was when we were in Falcon Space in New Jersey. And then we have a bunch of close-ups there as well. I am also going to put up, I have photos, or I have video that has not gone up yet, of us basically shining different lights on the sample from different angles. And the idea there was just to show, here are the surface features, and here's what it looks like when you change the angle, right? Because again, this is a granular sample. This is not just a flat brick. So that was helpful. So I think those are those albums. I also wanted to show you, before I forget, so this is Jarod's profile. Mighty
Tim, we're
Brain.
still seeing your Flickr, by the way.
You know what? Oh, I didn't share the. Okay, you know what? Here. Okay, sorry. I will scroll through the metallurgical microscope very quick. Sorry, I forgot to switch. So again, these are the photos that he took with the metallurgical microscope. All of these are up on Flickr. And I know you guys have seen these many times, but for folks who are new, if they haven't seen them, those are here. And these are super high res. I uploaded them as big as they'll get. so you should be able to see those. Okay, let me share. So this is Jarod's profile, Mighty Brain, and this is on Reddit. This is where Jarod has been doing all of his posts. So, again, if you're watching, if you want to follow what he's doing, like on a month-to-month basis, that or minute-to-minute basis, this is his feed. So this is out there now, right? So just so you guys know. The other thing, let me see. Oh, so I do have, okay. I'll just go through some of the other stuff that I found. So this is a foreign press note on the Dalnegorsk crash from the CIA, CIA.gov. And basically they are talking about the initial report, I believe in 1986, of the crash. And so I've uploaded this to the archive for this one. I want to share this tab. Jarod used some of this in his analysis. This is Dalnegorsk, basically a write-up on what they found when they did analysis of the crash in Russia. And I have a PDF of this up online as well. Let me see. I want to, so Jarod did show this. This is a blow up of the photos. These are examples of some of the wreckage from Dalnegorsk in Russia. And again, that is up there. You can download that. This, I'm going off my train a little bit here. This is Ubatuba UFO sample analysis. This is Walker and Johnson analysis of it. I do not know the year of this, but I did upload the PDF. Again, this just kind of shows you that this material has been around and different people have looked at it for quite a while. What we're doing now that's so amazing is Jarod and Matthew and the folks who are taking a look at this are using modern tools and techniques in imaging, right? So in the past, I mean, you could see this is just like a text written write-up. This was all they had, and that's not that helpful. Not as helpful as super high-res photos. I also want to show you, this is Glimpses of Other Realities, Volume 2. This is the book that contains a detailed analysis of Travis Taylor and Linda Howe looking at the Arts Parts sample back in 1996. Again, this was given to Art Bell, the radio show host, who gave it to Linda, and they did the first detailed analysis. Jarod found this, and he used this as the foundation for some of his research. When he showed me the material that they'd collected back then, I was blown away. I had no idea. This is incredible. So again, Glimpses of Other Realities, Part 2. Okay, and where's my StreamYard at? Ah, there we go. Okay, sorry. It was in a completely separate tab. I lost myself. So I want to see if Michael was here. Michael is not here. Do you guys want me to share the Kimbler samples really quick too? Okay, let me do that then. And Michael can come in and explain those because I did promise folks that we would have those. So,
Tim, could I share something really quick first?
Oh yeah, go for it.
Possible?
Go for it.
So I don't know if it'll work because I tried to upload it, but maybe through just the regular screen share. I wanted to show just for fun when I made a cracker radioactive because I think it's pretty hilarious. It's like 10 seconds. It's a 10-second video. That's it. So let me see if I can get it up there. And I hope I don't get fired for this. I broke all kinds of safety rules to do this. But I've got 10 years, so I'm good. So I'm going to share. Let's see if this works. I think I can. Okay, I think I can get it. Do you see the my screen and you see the video? Okay, I'm going to try playing it and see what happens.
You're not seeing your screen.
You're not seeing it. Okay. Let me try. Let me stop.
Maybe he'll come back.
Okay. Oh, he dropped. Okay, his thing dropped. Okay, we'll give him a sec. Yeah, sorry about that. I have another tab open, so it, for some reason, it got confused. Let me close down all these tabs. Okay, he's back.
I clicked exit by accident. That was totally on me. You know, I have a
I've been doing that
PhD in
too.
physics.
Put those right next
But
to each other.
StreamYard, present and leave are right next to each other. I'm really sorry about that. So why don't you present what you wanted to, Tim, while I figure this out so that I'm ready to go later. So why don't you show what
Okay, yeah.
Yeah.
I have a couple. Actually, you bought me a couple moments. I uploaded those to Drive so that I can scroll through them. So
Awesome. Why don't you scroll through them while I patiently study the options on the bottom here.
Okay, so let me go to this one first. I uploaded these. So these came from Steve, and I'm forgetting his last name, but this is the St. Augustine crash wreckage. Again, I'm going to have a link in the alt propulsion page to these, so that you guys can download if you want. It's fine by me. I took this photo of St. Augustine. Jarod has done deep analysis on this. It is sitting on a piece of aluminum. It's just textured aluminum that made it easy to shoot against. So these are just a few of the samples. These are the Ziploc bags that he gave us for it. And again, there was a lot of stuff that we could not show today, but this, we are good. So St. Augustine crash wreckage samples. Okay, and then let me share this tab as well. So this, Michael Perrone just found this for us, and if Michael is able to make it, I would love to have him to explore more about it with you. He has been working on this alongside Jarod, sharing data with him. This is part of their coordinated effort. Michael is over in Massachusetts, and so he just got these off his computer for us. These are SEM photos of the Frank Kimbler Roswell bounce site crash. And unfortunately, I cannot explain these to you. I lack his technical knowledge on them. But I did want to at least show those to you. I think that he has more that he will be getting. And so we'll see if he can do a presentation on that in the future. Again, this is the most interesting. Obviously, highly complex surface. To me, it looks like a galaxy, but it says 50 micrometers at the bottom right. So I'm guessing it's not a galaxy. Okay, so I think, guys, I think that for in terms of UFO samples, I think that's it. But we've showed people God knows how many photos, and again, we have hundreds more. It's possible in the future we'll be able to show those. It's kind of stinks that we're not able to today, but we want to respect the scientific process. And so Jarod and Matthew, thank you guys for the last minute switcho changeo on that. And again, there's lots and lots of SEM, XRD, Matthew, your NAA analysis, all of that stuff has been done and it's public, it's out there, so.
Yeah. Oh, I finally figured out, I think I won't exit this time. Could I show my fun video of my crack? Yeah, I think I've got it this time. May I share it, Tim?
Yeah.
Right. So let me see. So I'm going to share screen and I'm going to just pick the specific window of just QuickTime.
Yeah.
It's working? Okay, but it's like, can you see the whole thing?
There we go.
Okay. Perfect. Thank you. All right. I'm going to rewind it and hit play then. I have to be careful. Do not try this at home. I have to emphasize that over and over again. I broke all kinds of rules. There's like food there. There's my lunch. So don't ever do this.
By the way, there's no sound on this.
Oh, there's no sound?
Yeah, if you're
Oh,
playing
very
it off your
quiet.
desktop, it's not going to work.
It's
Yeah,
No,
very
there's
quiet.
Very
sound.
quiet.
There's
It is,
there's
there is
sound.
sound. It's quiet.
okay. Well, if
I think it might be coming through his mic.
oh yeah,
It's
if
just quiet. Yeah.
if you didn't hear the sound, it was the Geiger counter going batshit crazy on the second cracker, going like. And so when the cracker calms back down to zero, I literally ate it. This was many years ago. Did I get cancer? No. I just did that to mess with my sister because she's not a scientist. And so she has not the slightest clue how radiation works. So she doesn't understand when it's decayed away, it's totally safe again. So I totally ate that. I did that to a salami as well. You know, I love salami. What can I say?
Speaking of radiation, I had some questions from the presentations, plural, about so a couple mentions of blue shifting and sunburns from UAP and this kind of thing. I think Jack Sarfati put out a challenge a couple of years back for people in the UAP research space to start looking for evidence of blue shifting and red shifting in actual UAP observed. That could be counted. I think Hal put some kind of challenge out there like that as well. And I was just wondering if anybody present has heard of any evidence coming up for that so far out there in the field.
I have it. I mentioned it at the SCU talk last year. I looked at the colors of UFOs, and actually I've got it. I've just been too busy. And then I have the art part analysis, didn't have time to publish it. But I would say I've got some preliminary evidence that I'm very excited about. Jack won't believe it.
That's
He'll
like
say it's
more
nonsense,
exciting than the art parts.
You think so? No.
Because I've been working with Dan Davis a lot and other people. I think like space-time metric manipulation is pretty much what we're looking at here. And I was also wondering what your thoughts on the arts parts and other materials, how like these structures could, like something that you said it was possibly absorbing radiation for millions of years into its structure. Like how does that bend? How does that affect the local space-time metric?
No idea. I know Jack has ideas, and says that he's right and everyone else is an idiot and wrong. I know Jack well, but like, I'm going to be completely honest and humble with you. I'm not even going to speculate because I don't think and also I'm not a theoretical physicist. I'm an experimental physicist. So I can't even speculate on the theory because
don't get out over your skis.
Yeah, exactly. I don't want to get out over my skis because I'm like a lot of the people here on the call and in APEC. I build things with wrenches and screwdrivers, okay? And in fact, one of the discoveries my colleague Cecilia and I made, we got our papers rejected because they said, well, we don't understand how it works. I'm like, I don't give a damn you don't understand how it works. It works, okay? Well, let's worry about the theory later. So yeah, I'm an experimentalist, so sadly I would love to be able to answer your question, but I'm not a theoretician. And I'm just be honest with you, I'm not good enough at math. I work with wrenches and screwdrivers and hammers, like Mark, like a lot of the guys here.
But
Okay,
you
I'm
do
just
have
dropping
some evidence of blue shifting and red shifting that it's just not published yet.
Yes, so I had this crazy idea, which is to look at the patterns of the colors over hundreds of thousands of UFO reports. And I had an idea, if there's Doppler shifting, there would be a certain pattern. I found the pattern immediately on the first try. Like I said, if I just didn't have to waste time sleeping or teaching, teaching students who hate science, I would have that published already. But I hope this summer or by the end of the year, I hope to have a paper on this. I did give a preliminary result on it at the SCU conference last year. I gave a very preliminary sketch of the idea, and but you said it's more important than art part, but I don't know, because a determined skeptic would just say, oh, it's a coincidence that everybody picked the red color or that color. And it's like, if you don't have physical evidence, it's still like, but I hope you'll read what I have when I get to it in a few months. And I really hope that it's as exciting as I think it will be.
Okay,
Matthew,
so I just dropped a link into chat, by the way, just so you guys know.
I gotta say, Matthew. Oh, sorry.
Oh,
Go ahead, Jim.
well, just so you know, everything, all the photos, the PDFs, everything in today's presentation, right? That is all in that Google Drive link that I just dropped. And yes, this is live, although only for another couple hours, and then, mind bending.
Matthew, the fact that you have analyzed the color changes brings me great joy. A while back, I started doing that and got a little ways into it and observed the pattern, but didn't know what to associate it to. So the fact that you've associated it to blue shifting is like outstanding.
Well, and not only that, well, quantitatively, I was able to match, but again, I just have no time to write this down. And so I'm not secreting anything away. I want to write this all up and publish it. But one of the things I found was if my hypothesis is right, then it would be a natural explanation for why maybe we're seeing more UAP with FLIR. Because if I'm right, they're invisible the vast majority of the time. And we just don't see without the appropriate FLIR and the appropriate terahertz range of FLIR.
And on that note, I've come across a few different people who have found really high-end thermal gun scopes that go for anywhere between a few $1,000s up to about $20,000 is the range for these things. And these scopes, it seems like that's the market for high-end consumer-grade thermal scopes. It turns out that there's a lot of good data out there with thermal scopes on YouTube that a few people have done. Just wanted to say that's worth looking into as well.
Jarod, didn't you also have some potentially speculative ideas about how there could be some, was it negative birefringence?
Yeah, so I scrapped out with the redo slideshow, I scrapped out a good chunk on the hypotheses for propulsion.
Fair enough.
It's not enough there.
Yeah. I mean, yeah, it was an idea, but I mean, that's just kind of making the link to what Jack Sarfati is trying to do at the end of the day. And, Professor Szydagis was talking about how, combining elements to get more, exotic quasi-particles. That's kind of the theme of condensed matter right now. And really not that many physicists in condensed matter also study gravity. So that's kind of really where the forefront of what is needed here to kind of get what Jack Sarfati is after is really, how do you study exotic metamaterials in general relativity? Even just studying macroscopic media in general relativity is not very common. So yeah, I mean, it's kind of, I find that at least encouraging that it's kind of like there's this wedge of combining these two areas of physics that still is relatively easy to do. It's just no one's done it yet. So maybe we can learn a lot more in the future.
I think we're over specializing ourselves. We're over siloed. And I think to solve the greatest challenges humanity's facing, we need interdisciplinary endeavors.
Yeah, definitely.
David, since you brought it up, I will give like a few minute blurb here just on some of the research that I was coming across that I found interesting. I don't know how relevant it is, but it may be, so it's worth sharing. So for those who don't know, birefringence, if you take a block of quartz and you shine light through it, the light will split into two rays instead of just one ray. And one of those two rays is going slower than the other. That's because the grains of the thing are aligned in a certain way. So light going through this way has a shorter path than light going through this way, right? So you get, bink, two split. Well, that makes it a natural metamaterial. A metamaterial is something that has a weird refractive index like that. Quartz is one of the few natural occurring metamaterials, bismuth being another one. But the effects are very, very small. That said, there's some really interesting papers out there regarding these metamaterial asymmetries. One of them has to do with chirality. So if you have a right-handed circularly polarized beam versus a left-handed circularly polarized beam, that difference in the direction of rotation creates something called a time symmetry violation. So basically, if you run the clock backwards, you don't get the same start value that you normally do with normal stuff. And a normal thing, you throw a ball this way, it lands over here, you can reverse the clock, it follows the exact same path back. With left-handed versus right-handed, stuff like that, it's not the case. You run the clock backwards and it doesn't follow the same path backwards in time. So this time asymmetry seems interesting. You can get similar, but not the same, not time asymmetries, but you can get other kinds of interesting asymmetries with regards to bismuth at terahertz levels in very small pieces of bismuth. Some of these asymmetries have to do with quantum effects that are going on. And I'm not going to go into it much more than that because I'm nowhere near like read up enough on it. Just I saw a good 3 or 4 papers that were talking about this special kind of asymmetry that exists in bismuth at the very small scale at the far infrared wavelength.
You know, it would be worth mentioning, I don't know if this is accurate or not, but the path that you have been kind of going down, Jarod, Clee Irwin at the gravity research, quantum gravity research, he has gone down a similar path, and he was talking about potential higher dimensional symmetries. And like you had a photo that you showed where it was a series of dots of different sizes, and that was interesting for a couple reasons. One of them was I thought, how would that interact? Like if Drew used that in his devices, if he used that as one of the asymmetrical layers. But then the other thing that Clee had talked about was in a flat 2-dimensional plane, it may not make sense. These little kind of fractally spaced dots. But if you visualize that as part of a higher dimensional, right, 3D, potentially 4D, maybe 8D, it might potentially have all sorts of effects. So
I had, like I said, in the redo, it was very, very put together very, very quickly. And I ended up getting rid of all of the, like, you know, how to thrust slides, right? Which was kind of unfortunate because it was a rabbit hole. It was kind of a reach, but it ended up leading me to Dr. Winterberg's work. And, you know, I won't talk about quantum mechanical stuff that I don't understand, but I'm happy to dive down any woo rabbit hole. So what I was looking into was with Winterberg's work in like the most small synopsis I can give you on what his Planck ether thing is. He says that space-time is a plasma that consists of equal parts positive and negative charged plasma, and that you can have rotations in this plasma. You can have these little spins, and it can happen at the Planck scale, and that all of the oscillations of the ether, the dipole plasma we live in, all the different kinds of oscillations you can get in that end up predicting all of the different fields and particles that we see. And he goes into great detail in his book on how to make that happen. Well, I thought that I might have found a way to utilize his theory with the arts parts piece, because there's ways that you can get negative effective masses that end up having the potential for an asymmetry to exist, where you can actually extract meaningful momentum transfer. So propellantless propulsion, right? So normally negative effective mass would be like regular mass. You kick a ball, it goes this far. You kick it harder, it goes farther. Negative effective mass would be like you kick a ball, it goes so far. You kick it harder, it goes backwards, right? So this is very similar to birefringence. This is very similar to negative permittivity. And so go figure, they have found in plasmas, specifically in plasmons, and especially, not plasmons, sorry, in exciton polaritons. That's why I had that part up on my slide. Exciton polaritons have negative effective mass. And exciton polaritons seem to be one of the potential decay states that could be occurring when the terahertz stimulus is being applied to the sample. Well, okay, what good is negative effective mass if you don't have an actual asymmetry in there where you can exchange the mass somewhere else and go? Well, that's where Winterberg's theory comes in. In his theory, you can exchange the momentum with the vacuum, and it's magic. It's just straight up magic. You can get negative effective masses within the Planck ether, and then you can exchange between the two. You can get like extremely hyperbolic levels of momentum transfer between your craft and the vacuum.
Well, so Jarod, on that note, It is actually, you took us right there. It's 4 p.m. Pacific exactly. You guys want to go to lab time? Okay, so let's do this. Before that, one more giant applause for all of our amazing presenters and for you guys. You guys give yourselves an applause, but especially for Jarod and Matthew and Bryan. You guys are hitting it out of the park. I mean, this is just overwhelming. And Mark, do you want to go in terms of lab presentations? Mark is hitting it out of the park also with the DNP stuff. So take it away.
Definitely hitting a lot of foul balls. I don't know about hitting it out of the park. We're swinging. We're constantly swinging over here. So when Jarod was doing all this research into arts parts, that got me thinking in connection with the work we're doing on dynamic nuclear polarization. How could this connect? And something interesting about magnesium. So magnesium, if you do a little research online, is the third best conductor of electricity by weight. The best conductor of electricity by weight is this over here. This is lithium metal. Actually, you can see a little bit over there. That's pure lithium metal. This is has the density a little bit more than like styrofoam. It's very light. It needs to be covered in wax because otherwise it will oxidize immediately. So what you see here, yellow, that's not lithium. It's actually underneath it. The next best conductor of electricity by weight is aluminium, which we have lots of. You can very cheap. And the third best is magnesium. And aluminum and magnesium are pretty close to each other. You wouldn't want to use lithium in the craft because that could be kind of dangerous and it's very weak. Magnesium is kind of stronger and it's a bit rarer. So, but aluminum and magnesium both have that property of being one of the best conductors. And the reason why you'd want good conductors is for dynamic nuclear polarization or for electron spin resonance. You need lots of free electrons or conduction band electrons in order to interact with it. And the slightly more ferrous materials like the zinc and all the others, the bismuth, which is diamagnetic, those could be also playing a role of like reflecting the dynamic nuclear polarization back into the sample. So you'd have like a resonant chamber of different materials, like resonant layering. Also, because of the skin depth effect at these higher frequencies, you wouldn't need any material thicker than the skin depth of the material of the frequency. So at 3 gigahertz, that would be extremely thin. Lower frequencies, it gets a little thicker, but they seem to be running around 3 gigahertz. So that got me thinking we should try making some ourselves. And that's why I came up with this. We're calling it Mark's Parts, just because it rhymes. Basically, that's aluminum foil, bit of zinc and bismuth had been layered on it. I've also tried a different variant of it where we're basically take a puck of aluminum and put thin layers of zinc and bismuth on that. And this is one of our first samples that we have been running through the dynamic nuclear polarization machine. So it's mounted at the end of a glass rod over here, and this sits on a scale as it undergoes dynamic nuclear polarization. So we have the capability of mixing lots of different types of metals over here together and trying out various samples. So far, we have about 50 samples that we have to run. We bring you over to our next station. We're going to show you what's happening, the latest, what's happening with our dynamic nuclear polarization machine. So in previous tests in the X-band machine, we have seen what was a very obvious signal. Running the same sample through this machine, which has a different magnetic field orientation, that signal didn't show up, or at least it wasn't as obvious with the previous tests. Now, some things have changed. One thing in particular that changed was magnetic orientation, the field strength, and the RF frequency. We're going at about 1/3 of the X band. This is S band, so we're 3 gigahertz instead of like 10 gigahertz. And the magnetic field orientation. Now, why the magnetic field orientation is so important is because the way these electromagnets work, they tend to be more homogeneous in the center. And as you go out towards the sides, at the edges of like the edges of the disk, of the area that's that the magnetic field is on, that's where the biggest drop-offs in magnetic field happen. So with the previous setup where we had the magnetic field going horizontal, the sample could have been sitting in an area where it was varying magnetic field slightly. And that led me to believe that it's possible we need a slight varying of magnetic fields in order to maximize this effect. So what we did was we added a second electromagnet power supply. So there's two power supplies now. Each one of them is running one coil. So there's two coils in the system. It's all surrounded by iron, which kind of acts as a dampening effect. So even if you turn on only one electromagnet power supply, both the top and the bottom, it maintains a lot of homogeneity. But you can see there we have about a 17 Gauss difference between the top and the bottom. And these were both, of course, calibrated. So that's actual. That's an actual real effect. Now, if we're turning both of them on, you'll see it actually gets a lot closer. I added a little bias switch over here that allows me to control the difference between the top and the bottom. But it's actually not. It's actually very difficult to get them to be non-homogeneous because the amount of iron in the system kind of really just dampens whatever difference in magnetic field that we have being created on the top and the bottom. Here we managed a 2 Gauss difference. So this is the next variation of this experiment that we're going to be trying. We also did a large cleanup of it, clean up all the wires. Some of the wires are actually being supported overhead. And this allows us to do a full walkthrough around the device. And we actually are able to now see the inside of it. So let me grab a little wire over here. So there we go. You can actually see into the chamber right now. So previously, the cryogenic system used to be sitting over here, but I removed that because we're going to be using our nitrogen laser to excite the sample. And we're trying something that's called triplet state or triplet pair excitation. So basically, you have a molecule of pentacene, which is a kind of carbon molecule that is excited with light. And this creates two electrons that are paired together and they're excited in the same direction. And they increase the coupling of the microwaves to the sample many orders of magnitude. According to the paper that we have over there, which came out of Japan, they saw an increase in NMR signal to noise ratio on the order of 250,000 times. And Jagnar over here, these are latest higher. Oh, thank you. That's the paper. Yes. So this is it over here. So this is what we're going to be trying to do. Michael Perrone came by and we made what we're calling anti-gravity paint. It's essentially a mixture of that pentacene with a styrene limonene paint. So it's made with styrofoam and limonene, which is basically orange juice. Like the juice that comes out of the peel of an orange, it smells like oranges. That's what this is made out of. It acts as a pretty strong debasing agent, I think, or something like that. I don't know if that's Michael. We also infused it with xenon. And what that does, xenon is one of the best retainers of dynamic nuclear polarization. So when we get a chance, we're going to be painting some of our samples with this paint. It's slightly purplish color. And we'll be hitting it with various lights. We have a nitrogen laser over here, which produces ultraviolet light. And that should be around the range that we need. I think it's 337 nanometers. And we're gonna have to find some way to mount that in the system in order to excite it simultaneously. Now, back to what Jarod was talking about earlier. Everyone's very excited about this. I don't know if I'm going to have time to work on it, but we got this massive laser over here. This is a terahertz laser. It's really a CO2 laser. It's like a 100-watt CO2 laser, and it uses a mechanism where like they're finding like a beat frequency between different wavelengths in order to put out terahertz frequencies. So you're going from a 100-watt CO2 laser to like a 1/10 of a watt terahertz laser. So all of that heat energy needs to go somewhere, which is why we have a massive chiller, which is still in its box over here, that is going to absorb all of that energy. There's a lot to do in this system before we could ever turn it on. The people at Edinburgh Systems, they warned us, you have to do a lot of stuff to make sure that you're not going to break it. It's very easy to damage the thing. And thankfully, all the glass inside for the CO2 laser looks healthy. I think we're good to go on that side, but we just need to hook everything up properly, get the right electricity for it, and we'll have our own terahertz laser source. Check out the size of this opening. So that's actually the opening for the terahertz laser. That's my thumb for, it's about the size of your palm. And the laser actually is almost that wide. That's actually the width of the laser beam, because we're talking about very large wavelengths. On this side, you can get an external beam for the CO2 laser, just to put things in perspective. That's what a CO2 laser, the output looks like. Now, obviously, if this thing was running right now and we had a CO2 laser coming out here, it would blind people and destroy a lot of things. There's a lot of work to be done before we can play around with that. And I think that's pretty much all we got going on. Oh wait, no, we got some more stuff. Another thing I noticed about our DNP experiment, dynamic nuclear polarization, or orienting subatomic particle spins. In the original paper where Overhauser discovered this effect in 1953, he wrote something pretty interesting. That here it is on the second page of it, and I have it highlighted over here. That the relaxation time of dynamic nuclear polarization was 100 times smaller than expected at cryogenic temperatures. So what that means is as you cool down the sample, the thermal effects on the sample reduce the amount of dynamic nuclear polarization. So there's a relaxation time. But as the thermal effects drop, the relaxation time increases. And they noticed a ratio, and they theorized or came up with a mathematical formula of how that should interact based on the known interactions of thermal effects on nuclear effects. But at cryogenic temperatures, or like near 0 Kelvin, the effect was still 100 times faster than expected. So he wrote in here that an important relaxation method has probably been overlooked, so that the correct temperature dependence of T1 is not yet known. So that important relaxation method is where the anti-gravity comes in. Because the only thing interacting with a sample that's undergoing dynamic nuclear polarization at near 0 Kelvin is gravity. So gravity is doing work on the sample in order to reduce its oriented state. And if gravity has to do work on it, maintaining that state is anti-gravity. Also, something else interesting happened. I don't know what this actually means for us, but this book, the one by C.D. Jeffries, the only book ever written on dynamic nuclear orientation, just sold on Amazon for $5,000. So if you got one, hold on to it. And that's it for today. Oh, we got all these samples over here too. Jagnor organized them. We got about 150 samples over here, all of them in their little cases.
Oh, sorry, I'm muted. Mark, that is amazing. See, you have been burning the midnight oil, man. That is awesome. Awesome. Jagnar, it's good to see you again, dude.
Yes, sir. Likewise.
Jagnar's
Okay.
kicking ass, by the way.
Yeah, no, that's awesome that you guys are making it work. Making it work. So let me see. Where'd Drew go? Oh, there's Drew. Drew disappeared. Drew has updates. Drew, take it away, sir. Oh. It says your mic is not why is it? Uh-oh. Now it says his okay. Drew will be back.
David, do you want to do an update on the Alzafon plotter?
We might have to wait for Drew.
Sure.
Yeah.
I can do that real quick.
David did something really cool that where he built a tool for us that we're using for analyzing the data that comes out of this machine.
Okay. Here, let me I'll do
see.
solo layout for David.
All right, cool. Thanks. Yeah. So basically, I had worked with Mark and the Falcon Space team last year on the data that was collected last year. I'd written some Python code. And so I took that code and I just spit it into AI and said, make a GUI to implement this. So basically, we have this nice little graphic. Oh, you can't see this window that just popped up, but I'm basically loading in some data. And then it's probably a little hard to see on the screen here, but I can select different columns in the data set. And then I click this update preview button. And there's actually a pop-up saying updating plot, please wait. I probably should have shared my whole screen. And then so you can see the whole data run here. So we had this magnetic field strength that was sweeping up and down. And then this was the measurement from last year's data on the scale, the weight measurement in grams. And so, yeah, there's some different functionality here. But there's some other, this is kind of like I'm calling a basic plot. And then it has this multi-cycle plot. It's please wait, switching plot mode. It'll pop up in a second. Hopefully. Oh, not responding. Let's see. There we go. So then it attempts to automatically calculate how many cycles there were in this sweep. And so when I update the preview of the plot here, it's updating the plot. There we go. So now we can see all these different, there's all those sweeps of the magnetic field are now right over the top of each other. And this is a huge mess. So we could focus on, let's just say 19 to 22, and then do it again, and then focus on a few. So this was close to the interesting signal that Mark was referring to. There was a few cycles here that appeared to, well, at least there was at least some, the scale, which is measuring forces, at least picked up something, right? And so that's measured there. So yeah, there's a bunch of different little things in here. We've been working with AI to generate this. I was using Cursor AI, which is basically it's an IDE that allows you to integrate AI in with there. And so it's pretty cool. It's kind of a fun experience. Well, it's fun at first when it's working well, and then once the project gets a little larger, then it adds new functionality and then breaks other things. But that's not too much different than humans at this point, just typical software development. So I barely even looked at the code. I just got AI to basically make this program. So yeah, that's kind of what. And so I made an executable that was sent to Falcon Space, and now Jagnar and Mark have access to that. And we're setting up a GitHub account so we can make further updates to it and fix a couple bugs here and there and stuff like that. So yeah, that's pretty much all it's to it. Yeah. Anything else worth mentioning, Mark?
Oh, it's amazing. It's amazing what you're able to put together with just a little coding knowledge and some AI tools.
Mm-hmm.
Yeah, it's a lot easier now than it used to be. That's for sure. So it's encouraging. It gives you a lot of confidence.
What AI tool made a full EXE for you?
Well, I eventually so I used Cursor AI. I mean, it can run stuff in the terminal now, so it can run code. It's really good at working with multiple files. So I started in ChatGPT. I gave it my old code that I had written, and I said, turn this into a GUI. It gave me one file. I started, and then I copy and pasted that code, put it into Cursor AI, which is like VS Code. They basically took VS Code, which is a popular IDE, and they just added some functionality to it where you can chat. That has like, you can select things and press tab, and then it'll autocomplete. It'll try to like predict what the next line of code is, or you could just say in the chat, hey, add this functionality, and it can read multiple files. So then eventually I said, okay, once the single file was getting, over like 2,000 lines of code, I said, okay, take this file and separate it into multiple files, and it just go. And it has this fairly agentic workflow at this point. So it can, create files, add files in different folders, read them. And then, it's just Python code. So that I use some package that you can just run a line of code in the command line and generate an exe from there, which I also asked AI how to do that. And it can run stuff in the terminal as well. And it can debug stuff on the fly. I mean, it's not going to debug like user interface bugs. You still have to do a lot of testing, but if you set up right where it runs it in the terminal, and if the code doesn't run, it'll just be like, okay, and like, let me read the error message and fix the error, and it'll automatically do that. So that's with Cursor AI. So they've been sequentially making it better and better over time. It didn't quite have that functionality a month or two ago. So yeah, it's a nice tool. It's pretty popular for programmers right now. And it just, if you didn't know how to code, now you're a beginner coder. If you were a beginner coder, now you're an intermediate coder. And I feel like I was kind of at that intermediate level. So, I mean, maybe it's not exactly true, but now I'm like, I could do anything. Well, really with the help of AI. So, but you got to tell it what to do. So, it's pretty nice. I mean, and if you are careful to, make a pretty elaborate prompt to really specifically specify what you want and put a little time in that, it can go pretty far with that.
Yep. Amazing job, David.
Oh, thank you. Yeah. So, just trying to help out Falcon Space and everyone, and this will just help them more quickly analyze the data now that they have a GUI. Last year, they were sending me the data and I was analyzing it. So now they can use this, look at the data more quickly, and then try to figure out what to do next based on that.
Now next, can we take the space-time metric manipulation simulator that they made to go with MATLAB and put it into a downloadable Steam game, please?
Maybe. I don't know. Yeah, I mean, anything's possible, right? You just gotta be more
when you
specific on what
integrate
that
it
game is.
with FPV goggles, that's what I'm.
There we go. Awesome. Well,
Awesome.
Yeah, that's that.
Okay. Oh, did I take it down too early? Sorry about that.
No, I stopped
Okay.
the screen share right around the same time. Maybe we both clicked at the same time.
Yeah, I think we did. Okay. Yeah. Okay. Well, yeah. Awesome. Drew, you were back, sir. Give it a try.
Yes, can you hear me?
Yes. Woohoo!
Oh, it won't let StreamYard work out in the shop for whatever reason. It says no. I'm not going to let you upload sound for reasons known only to you, probably. But anyhow, I was going to show off that I'm vapor depositing right now. The one thing I want to bring to mind is about every 1,000 minutes of use of your vapor depositor, you need to completely rip the thing apart and clean all of the coated metal off of all of the surfaces, or your system will go into garbage mode and bad things happen. That's the technical note for the day. I have decided to pursue a slightly different avenue. I want to make as much thrust as possible with the engines off. So I am going from copper. Normally I deposit copper, which this is a copper target. As you can see, the inverted electron, the inverted magnetron burns the copper in the form of a kind of a ring. So I'm going to switch from copper to a ridiculously expensive metal called yttrium, which comes with a stupid high price tag. But anyhow, it has to stay sealed in triple layers of material. Otherwise, the stuff just corrodes instantly. It's on par with lithium, how dangerous it is. But it will inject, it will convert free charge into bound charge about 10 times better than copper. And the only reason I'm doing any of this is because I had a very interesting test result. And I'm going to throw it up on the screen if I'm lucky. Share screen. Screen with screen. I don't know what this means. Share screen. Screen sharing works best. Don't share these screens. Okay, working on it.
Yeah. Oh, yeah. So it's, let me see, press the present button and then share
Press
screen.
the present button.
Okay. And then
It
over
says
on
I'm
the
sharing
right, it should have
screen.
entire. Yes, you are now. Hold on. Sorry.
Okay, so you can actually see my screen, or yeah,
There we go.
Okay. So what I'm going to do is I'm going to zoom in. This is a test I've been running. This is actually the fourth run of this test. This is the fourth run of it. And what I've been doing is it's slowly injecting charge into the test plate. And the test plate, hang on a second. I'm running way over on my coding. Basically, as you can see, I'm at 4.32. I'll kind of zoom in. This is in millinewtons. This 4.32 is in millinewtons. So when I turned on the system, I was at 4.45. That's where it started at. And then I was, over the course of a few minutes of running voltages. These are, various voltage levels. This is very difficult. Anyhow, just by alternating the voltages and bringing up more voltage, it's about 7,500. So I slowly, every time I turn the system off after a high voltage, while the system is on, it's injecting charge into the polymers. And when I turn the system off, the mirror charge comes up from ground and the thing goes crazy and makes more thrust. So when I got all done, I was at about 5.5 millinewtons in the zone, which for the amount of mass that I'm talking about is about 55% Earth unity. Not particularly exciting because I've had 1.85 times Earth unity before. But what's interesting about this is I was able to put this charge, this is using copper, I was able to put this charge into the plastic, into the polymer at 100 times the rate that I was a year ago. And by switching to the yttrium, I hope to bring that rate down to almost immediate. I hope to be able to throw the switch, inject the charge, turn off the power, and have the magic run, forever. So that's what's going on here at Exodus Technologies.
Ah, thank you. Okay, I was just looking for the button for that. I'm updating the page too. I'm getting everything all set up. So folks who are watching this now, if you visit altpropulsion.com, you'll have links to all of our stuff there. And that's, all the presentations and all that stuff. So I'm just getting that ready. So I think, is that it for lab updates, guys? Curtis is not able to make it today. I know him and Jim are still testing things. And then it has been just, I think we're getting into the new year. It's been crazy busy. So if you guys want, I don't know if this is causing trouble or not, but I can show you guys kind of what I've been doing on YouTube lately. And hold on, I'll go to YouTube Studio right now. Well, why don't we go into open discussion then? And I will kick things off with sidetracking folks on our YouTube discussion. Okay, so here's our alt propulsion channel. Okay, so Okay, so yeah, well, I guess we're officially limping into the open discussion part of our presentation. And again, guys, thank all of you so much. Today kicks ass. I mean, there's no other word to describe it. So what I have been doing is this APEC channel, we have 773 videos. Again, way back in the day, this used to be my American Anti-Gravity channel. I have a ton of stuff that's buried. So I've pulled some of that down and made video shorts from it. And I'm also working on organizing things and making shorts for other stuff. Some of the footage that I shot last year, I'm trying to just get different things and make good video shorts of it. These get good views. Jeremy Riss made these. And so what I'm trying to do is reformat these, right? So this is just one example. I'll keep the sound off, but this is Isaiah Ritchie, and I want to go back down to Portland to get some more footage. So he's doing the Searle effect generator. This is just one of many clips that we have. So I would urge people to, again, subscribe. There should be a subscribe button if you haven't already on this page. We also have tons of videos. One of the biggest videos was, where's it at? Of course, it's hiding on me. Yeah. So this is a long version of short that has gotten a ton of views. And this was testing that we did at Falcon Space last year. So again, lots and lots and lots of clips. Also, all of the APEC conferences, because they're through StreamYard, are in the live category. And what I'm going to do this weekend is basically make some video shorts and promo clips for this, as well as maybe break out a couple of the presentations and try and get those out as well. So we're rocking and rolling with this thing. You know, so that's kind of what I've been up to. It is heavy duty on the video, and you know, but I'm happy doing it, and it's getting a good response. See, my life isn't as exciting as your guys's is.
All good. You're in on the action too, Tim. It's great to have you.
Well, thank you. I'm like the support tech.
So Mark, when are we gonna see some weight decreases? Are you gonna put something in that cool toy, or talk to us, man?
We've been doing that continuously for the last couple of months. I mean, I recently stopped in order to change up the setup, but yeah, we've been doing that a lot.
Have you seen anything interesting?
Well, we saw with the X-band system, we saw something a lot more interesting. With this new system, it's been a lot of noise, and I'm trying to use this new plotter that we got from David Chester to dive through all the noise and see if there's actually anything there, or it could be that our scale is just too noisy to see it. We did cause some permanent weight loss, and by permanent weight loss, I mean like burning up the sample. So that's not ideal, but yeah. So our best results so far that show up on the graph have been with the X-band system. So I'm trying to replicate them with the S-band system, using the same sample before moving on and just trying everything.
Cool. Yeah, I've been having a huge amount of problems just replicating previous results. I'll build a brand new set of thruster plates, reposition them in the chamber exactly the same way. Every dimension's the same. Run the test and get radically different answers. Like, it's just driving me crazy because I've done it maybe 30 times now, and I just keep getting different answers. I'm like, something curious is going on. They're always in the same general ballpark, but they never reproduce the exact pattern from the previous run to the next run.
You should look into T.T. Brown's notes, he noted that as well, and he attributed it to the position of the moon and the sun.
You got to be kidding me.
Nope. David, you want to chime in on that?
Please explain. Smiley
Wait,
face.
sorry, I think I missed something. I was reading through the comments.
I'm sorry, man. That's just funny.
T.T. Brown's early experiments with gravity or capacitive thrusters, he attributed changes in thrust to the position of the moon and sun.
Yeah, I don't know what to make of it. Yeah, I don't know.
I got nothing on that.
Have you, Drew, have you watched Jesse Michaels' video on T.T. Brown? It's about an hour long, and it's...
Don't think so.
You should watch that. It's very, very condensed, well edited. Jarod had something to say. I see him nodding.
I was agreeing with Jesse Michael.
Jesse Michaels?
Yeah, he's got some good stuff, and there's a good book or two on T.T. Brown stuff that's like super informative. What I was going to say though was regarding the position of celestial bodies and how that might affect things. If this is doing some kind of vacuum interaction, if having like the limit of an electric field gradient in a material is somehow able to result in thrust, right? Then, and it's interfering or altering virtual particles somehow, it might be worth looking into chiral geometries. So virtual particles can come in all sorts of different kinds, right? So right now, the way that you have it set up, it seems like it may be more of just like a catch-all, right? It's like an antenna that's like poorly tuned, right? So it can pick up all stations, but none of them very well. Well, I wonder if you tune it for a specific station and pick it up really strong, if you might be able to get more oomph out of it. So if you can design it so that all of the charged surfaces have a specific angle to them that is not your normal, angles, but like that meta surface thing that I showed, where you have all these like different angles of like metal that are like little antennas and they create like this rotation. If you could capture circularly polarized virtual particles, or virtual particles that already have like an angular momentum built into them, if you might be able to capture a greater interaction with the vacuum.
Well, if it's okay, let me jump in really quick. Curtis, did you want to do an update today, or do you want to skip this week?
Yeah, I'll just say real quick that we're still working on the linear experiment.
Okay.
We kind of showed like some preliminary things, but as with experimental work, as you guys know, sometimes you get surprises. Anyway, so we're still that's still in the works.
Okay. I'm just trying to kind of plan my schedule here, and then Michael, did you want to do Michael, did you want to do a presentation, or did you want to discuss the photos? Or
sure, yeah, we can. So we have some preliminary results from that sample from the bounce site at Roswell.
Okay. Let me put those up.
What's the guy's name? Frank Kimbler, I think.
Frank Kimbler, yeah, yeah. Let me bring that up in Google Drive because I can scroll through them better.
Finally, thanks very much for your patience, Frank. We finally have some preliminary results on these. Initially, it looks like it's just some aluminum 7075, or 7000 series aluminum alloy. So these were very preliminary because we didn't have time to sputter coat before this APEC thing, but we wanted to show that we're getting the data now. So the epoxy around one photo at a time, Tim. I'll discuss each one in.
Okay, let me know. I just kind of started with this one, but I wasn't sure if that was the right one.
So the epoxy around the samples was reflecting a lot of electrons just charging up like crazy. So we weren't able to get a lot of like of the electron beam onto the sample itself. So we didn't get enough. We didn't get as much counts as we otherwise would. But yeah, I mean, you can see the microstructure. I was hoping we might see some dendrites, or we etched the surface a little bit here, but we didn't see the grain boundaries as much. Which, I mean, for a 7000 series, if you're just using sodium hydroxide, that can happen. These regions in there the brighter regions seem to have some silicon as well as aluminum, and there may be traces of manganese. And well, we'll get to that. But yeah, I mean, this is very preliminary. We'll go back and redo it tomorrow with some sputtering or some other way of anti-staticking the surface. Next one. So our initial very, very preliminary data, it looks like there's some manganese. Maybe there's a little bit of copper. And then magnesium, aluminum, and silicon, which is fairly standard for a 7000 series aluminum. There's copper and oxygen there too. We suspect maybe the copper and oxygen are from the epoxy surrounding it. If it was really, really charging up severely, it would have been like bouncing electrons back into the detector, even though it wasn't in the field of view. So, yeah, I suspect that might have been the case, but we'll see. We'll see what we can do about that tomorrow. Next one. So this was the sample under ring lighting and a metallographic microscope. The blue is colloidal silica nanoparticles, which we etched. Afterwards we were checking the surface, and so we etched those away afterwards with sodium hydroxide. I mean, we if it was something native to the sample, we had cleaned. I mean, we had polished the sample flat with colloidal silica in the first place. So if there were silica microstructures anyway, we wouldn't have been able to tell them apart from the colloidal silica that we had used to polish the sample anyway. So that's what that's. The larger white particles, those are actually inclusions in the aluminum that. But yeah, actually no, wait, sorry. In ring lighting, those would be holes. Those would be holes, like little air pockets. The fact that we have so much porosity isn't too much of a shock for a human-made alloy, but it would be weird if something alien-made. Well, I mean, unless they have some function. But yeah, there's little amounts of porosity. I'd say like 95% to 97% solid. But anyway, next slide. So these were the amounts that it measured for each of the elements, assuming we didn't get rid of the carbon and oxygen, which that kind of throws things off. And also, it was integrating these. It doesn't add to 100 or anything, but it's integrating these counts over like a. We didn't get to integrate very long before something went wrong with the EDS system anyway. So we got to go debug that tomorrow. But yeah, that's it's mostly aluminum, a little bit of magnesium and silicon, and maybe some manganese and copper. That's in line with many earth alloys, but I'll have to double check which alloy it would specifically be. And with the copper, I mean, with the carbon and oxygen removed, because we suspect that those are from the surrounding epoxy, the aluminum, and well, yeah, it's basically 95% aluminum, 2-point-something% magnesium, with a little bit of silicon, a little bit of manganese, maybe some copper, but basically under 0.5%. You really can't trust EDS data too much. So, yeah, we can be sure about aluminum, manganese, silicon, magnesium as well, and maybe the copper, but not really. Like there's not enough signal noise. We didn't integrate for long enough anyway to be sure about that. So that's what that is. Was there one more picture? Yeah, and this is the optical microscopy, and you can see that there's two phases. so it's probably like an aluminum silicide phase dispersed in an aluminum phase, and then the magnesium and manganese would be at such a low percentage that they're just they're not forming any third phases or anything. They're just diffused throughout the other phases. The black stuff is probably holes. There are a few areas where the material's black, but it seems like it's sort of bowed outward, which suggests that there was a hard material at that location. We'll take a closer look at that next at the next opportunity. But basically the two main phases are a dark gray phase, which is aluminum and silicon, and then the lighter phase is aluminum in the optical microscopy. And then the black phase is mostly just pits, and some of it might be a hard material. Yeah, that's
Michael. Thank you so much. I genuinely appreciate it, and I should mention thank you for.
There's one more thing I forgot to mention. We took some SEM from. We didn't get pictures of it yet, but we have SEM from the side and the top, and we basically took the XY plane, the YZ plane, and the other, we were looking for anisotropic crystal structure because 7000 series aluminum is sometimes like a raw alloy, and basically if you squish the material, then the aluminum silicide will, if you really squish it, the crystals will sort of align along a specific dimension, and you'll be able to tell that it was mechanically deformed and worked. But we don't have enough data to suggest that it is yet. If it was deformed that way, it wasn't by a large amount. Sorry, go ahead, Tim.
Yeah, no, I want to thank you yet again and mention that. So you were running across town or across Massachusetts, I don't remember which, to get these photos for us today. And that was just a lack of my poor communication. So thank you for the last minute work, and thank you for explaining this. I would love, if you're able to do a future presentation as a drill down on this, I would love to see more. I should ask, in your opinion then, you're talking about 7000 series aluminum. Do you think that this has kind of a prosaic explanation?
It would, but I'm not discounting anything yet. It's too soon to say.
Okay. The reason I ask is, from what I've heard at these crash retrieval sites, supposedly when these retrieval crews go in, they dump all sorts of metal scraps and garbage specifically to confuse UFO parts hunters, right? So
yeah, and Frank found a ton of that before he found this sample too, and this didn't fit with any of the other stuff, but it could just be other aluminum trash in the area. But the other thing is that region of New Mexico had a lot of like bomb testing for military applications and things. So it could be a piece of shell casing from something. That could also be a possibility. Some shrapnel.
Here, and I'll stop sharing that. Michael, again,
well, hey, Matt,
thank you.
I've been
so
here
much.
the whole time, but I just turned off my camera.
He's been hiding.
Bandwidth.
Yeah. So yeah, we're in open discussion. So I guess keep it loose, keep it real, guys. And thank you all. You guys are absolutely knocking this out of the ballpark. I mean, it's like amazing. I'm just thinking about how much work this is going to be. I'm going to have like 25 video shorts to make here.
Tim, I had a comment on the part dump you just said. I've experienced that.
Oh yeah. That's all over New Mexico too. Like
so I don't want to say who it was because I don't want to offend anyone because they were really mad. But there was somebody who gave me and Kevin, we had parts from St. Augustine, right? We were so excited. And those are the parts I mentioned in my talk. Is it was clearly a secret airplane, but American made, like on Earth. And he was pretty mad, but I'm like, the truth is the truth. And probably what happened is this is in Diana Pasulka's book where she says they do this. What they did is they dumped garbage on top. And so I have personally experienced this where I was like, it's an airplane. It's an American airplane. I'm sorry. This is like not special.
And it's important to point out, and this was something that kind of dawned on me, right? It makes sense, but it doesn't connect. At least for me, it didn't. crash retrieval is an existing specialization in the Air Force. Nick Cook wrote about this, I believe, in The Hunt for Zero Point. There was an F-117 that went down many years ago, and you've got the retrieval team that comes in, they clean stuff up. I believe they dump garbage to throw people off the scent, and they do witness intimidation, right? So this happens with all sorts of test aircraft. It's not just a UFO thing. It's like this is standard practice.
Also, aliens sometimes is a bit of a red herring, isn't it? Like, if it's the case that early in the 20th century we had the beginnings of some kind of breakaway civilization or sort of breakaway technologies using principles discovered by Tesla and so forth, wouldn't you find different engineered materials that seem to be anachronistic but still made of stuff that we can track here on this planet? No weird isotopic ratios or anything. Seems like, I mean, there could still be ETs flying around in the sky for all we know, but if you don't need it as an explanation. If you look at some of these tracks that they were looking into, like T. Townsend Brown was looking into more than half a century ago.
That's why I said Wakanda in my talk. I was joking, but that's exactly what I meant. Is that would explain why Art's part seems to have terrestrial ratio, seems to have argon in it from zinc mining, yet it's a part out of time because it appears to exhibit technology we did not have in the late 1940s.
Well, we
don't even have today.
We had electroplating. I think maybe we could have electroplated the magnesium bismuth composite. That hasn't been attempted yet, as far as I know. It's worth a shot.
Yeah. Again, my thought is the value of this goes so far beyond the actual samples. I mean, again, if you say, I mean, you could come back and prove beyond the shadow of a doubt that these are prosaic, but the thought process, the new ideas, and the problem solving that goes into it, this is where, I mean, again, you guys have come up with like 2 incredibly new applications in like the last hour, So
I'm thinking of like 3D nano bioprinting, like this. Some of this seems accreted. Like this is how abalone shells assemble their shell. They put out a very fine mesh of like proteins. We've looked into this protein. And it just so happens to be a fine mesh sort of glue that assembles all these random molecules that move past it in the seawater column. So they're slowly putting together this shell that, on some levels, for certain scales, is like stronger than steel. And we've now developed the ability to basically prompt our own specially engineered proteins with something equivalent to like, Mid-Journey for proteins. So we can do that one, and we can engineer proteins to do biomolecular fabrications like this. And like, I don't know if it's made by us or made by something else or made by something far older than us that's been here for a long time. These are like the principles it seems like it would follow.
Well, that raises another interesting point, right? But like Dr. Kevin Newth he almost like reworked the Drake equation in reverse. And his thought was that if ET has been here, they have been here for hundreds of thousands, potentially millions of years. So it very well could be ET craft made here on Earth, right?
Kevin's paper is really important. He estimated 1.1 million years ago on average, with a large error bar, of course, but what's interesting, I cited his work in my crash retrieval paper because I pointed out if his average number is correct, and if we believe, for example, if we take like Dave Grush's crash rate, and we take that as true, obviously massive grain of salt. I estimated in my paper that there are like something like 200,000 like spaceships at the bottom of the Pacific. Because the planet's mostly water.
Well, yeah. And people have talked about again, Catalina Island is a hot spot. People have talked about this base off the coast. I forgot the name of it, but there's that shelf off the coast of Los Angeles. And then I did an interview with Debbie Zegelmeyer, and she said, even though it's right off the coast, it's right next to the population center, she was like, getting a submersible down there to investigate is really difficult because of the currents and things like that. So
there's also some really interesting stuff around Guadalupe Island off of Baja. That's also happens to be a UAP hotspot. Also happens to have some weird geomagnetic fissures and strange stuff going on near the seafloor there. And a very strange, like almost perfectly L-shaped. So you go a little further south along the California coast, and there's some weird stuff there too. That happens to coincide with hotspots.
Yeah, it's amazing. And again, one of the things that I love about APEC is that we're able to cover both reverse engineering of UAP stuff, as well as like this incredible legacy of human-built ideas, right? And then you get stuff like with what Mark is working on, where it's kind of somewhere in between, you know? Alzafon was really kind of inspired, you know? So it's like he saw this and he said, here's what I think is going on. And then he developed this whole idea based on it.
So, Jarod, I noticed that book you popped up and your comments on.
Oh, yeah, the Winterberg.
I had like 3 or 4 slides talking about the Mega Drive.
So what's interesting is I've actually made progress on the theory side. And I'm working on getting all the math nailed down and trying to figure out, how do you go about releasing things nowadays, right? But what I'm working on sounds a lot at the outside of what you pointed out in that book. Actually, I looked it up on Amazon. It's not available anywhere.
No, all of the copies are sitting in a shed. Now, I have a few extras. Text me your mailing address and I'll mail you a copy. There's a digital copy that I can give you like right now, but
yeah. Send a digital copy. That helps.
The digital copies equations are all messed up. The format's messed up. But yeah, I'll do both.
Yeah, I'll send you that. But
have you guys oh sorry. Have you noticed an uptick in people sending you screenshots from AI, ChatGPT, Gemini, Grok? People
there's
don't
an
actually.
uptick of people send me AI stuff for everything, like the emails. The people are just using it.
Yeah, like our brains just turned off. All of us.
It's a good way to get your emails ignored, in my opinion.
Okay. So let's talk about the physics, because I think this week it's kind of funny. APS is going on here in Anaheim next week. I'm not going. I'm not going to give a presentation. I'm not going to go talk to anyone, and that's kind of a problem. I mean, I don't know. So a lot of the guys I worked with, like Roland, he passed away last month, Roland Whiston, and he really liked what I was doing with theory, and so that means a lot. But the trick is, like, who do I talk to, right? So I did find a group that I'm going to give presentations and get some peer review from, and like I said, I'm willing to talk to you guys as well. And basically, like I said, it's kind of what's pointed on that book is based on quantum, and we kind of know experimentally that quantum has some limits in terms of its domain of applicability. I'm not one of those people that say quantum mechanics is like flat out wrong, like Roger Penrose said. But it's, in terms of it, I would say it's not fundamental, right? It has its domain where it actually works, right? It gives us a descriptive predictions and all that stuff. So the big problem is kind of like, a lot of us are trained to think quantum mechanically, and so how do you stop doing that? And it's like a human limitation. So anyway,
if extended electrodynamics is true, and that's an extension of classical electrodynamics, then we're going to have to do a lot of reworking of quantum before we even have correct quantum theory, maybe.
Yeah. So I don't know if you remember, I was asking the question, like, okay, if you're going to recreate the standard model or the predictions of the standard model, not even the predictions, the measurements of the standard model, do you need to predict the rest mass energy or the actual what you see in experiment, right? What that curve is, because a lot of these particles are observed at higher energies, right? And so you extrapolate, okay, if I was going at that speed with that particle, what would be its mass, being the rest mass? But that's not how they're observed. So that's kind of like a fundamental question. And I'm kind of curious how that fellow that wrote the book you have, Jarod, how he handled that, and whether his attempt at a ether, whatever, I don't know what mathematics he used. It looks like he had quantum, so he was probably using some kind of spinner thing, is my guess.
He calls them rotons.
Okay.
So a roton is as far as I understand it, it's a phonon with angular momentum.
Okay.
So all of his particles and everything, it's all quasi-particles existing within this plasma.
Superfluid.
Superfluid plasma, yeah.
Okay. Yeah, and that's one of the things I'm finding there's a lot of things out there like that, which is, for example, there's that whole model where, the universe is like this quasi-crystal, and it's like stiff, right? And and it's just, people are just trying to take these materials ideas and kind of put them into the fundamental stuff where, really we that's not the way to do it. You got to empirically look at what experiment points to, how if there's something there, how it behaves, how space-time behaves, or what do you want to call it? The vacuum field. I don't know. It's probably a better term, but how does a vacuum field interact with light and matter? What is matter anyway, right? All those things. But it was interesting to hear you talk about the symmetries, Jarod. Because that's one of the things in Jim's theory, is that he's taking advantage of a sort of putting in an asymmetry artificially in the Mach principle, right? So you get the inertial motion, and you have more energy when you push one way than you push another, and so you should get a preferential momentum, right? That's an asymmetry that you have to artificially create, but you can use materials that have that asymmetry into it. And so one of the things I'm looking at is one of the experiments that we're going to be doing is something called the Mach-Lorentz thruster. I don't know if you guys are familiar with that, but part of that is what we're looking for is like Gallifred, like materials that have high magnetorestrictive effects, where it can have the motion, but you're using magnetic fields, so that our dPdt, our energies, are much higher. So that's something that we want to do as a parallel track and start doing that again. So anyway, I was kind of curious about your comments, Jarod, about what was it, beryllium?
Bismuth. So
Bismuth. Okay.
For how I understand it, with that whole negative effective mass concept, right? First off, you really, like, for anybody, you really got to get your basic physics under you before you start talking about negative effective mass, because it's not negative mass, at least not in our standard model. Now, if we live in a superfluid, then you can have negative effective mass in the superfluid, in which case you can now ride that wave. You can do a lot of fun things, if indeed that's the right way of going. Additionally, this was the thing that I was getting really, really excited about, was exciton polaritons and some things you can do with bismuth nanoparticles. This idea that you can have these special effects that happen where you have much, much stronger negative effective masses that you can then use to interact with other things that convert that energy from one form to another. So you can convert that momentum space, because it's got an asymmetry to it and it's acting like a diode. It means that in one direction, it is stronger negative effective mass than the other. So you can end up utilizing that because you've gone so small, those forces get so strong.
Yep.
Lastly, Banduric's stuff, where you're talking about the drift of electrons through a material and how you can kind of get a push with that. So that is kind of an extension on the phonon gravity relationship. So it's been found that phonons actually source gravity, even though it's extremely small. Any oscillation like that is generating a small gravitational field. If you, instead of going from phonons within like liquid helium, you go into like extremely dense plasma states that have much greater energy density, and you're able to do the same thing, you should be able to get much more punch from that phonon sourcing gravity relationship.
So
might be analogous with gravity.
In a similar note with asymmetries and things, I've been really doing some deep digging with the extended electrodynamic stuff recently, and I'm starting to wonder if there is some sense in which you could rotate momentum into energy. So like there's this like relativistically conserved mass, which is like E squared times C, or E times C squared minus the momentum in each of the three dimensions. But like with this S term in extended electrodynamics, I'm wondering if you can manipulate this, if you can curve space-time in such a way that somehow you're exchanging momentum and energy in a non-trivial fashion.
Yeah, so treat what you're doing with the electromagnetic sector as, okay, there's a space-time field, right? But don't assume that you're on the same part of it, right?
No, so there is a sense in which for the scalar mode, it must interact with gravity, because like I've been saying recently, the units of the scalar term are Webers. So there must be a relativistic derivation of that. If you try to use special relativity, like they do, like you can derive the normal magnetic field from the application of special relativity to
But scalars are Lorentz scalars.
One minute, yeah. I know, David, but there's a higher order symmetry here possibly. But anyway, the magnetic field is a special relativistic electric field. People derive this even like the standard Griffith's electrodynamics has it at the back. But this scalar term, it has units of Webers, so that is a hint that maybe it's a relativistic thing. But if you just apply special relativity, it's not obvious how it should connect. But then if you try to apply general relativity, now you can make it work. And then what that's suggesting is that if you need to apply general relativity, there's curved space-time involved here somehow. So
again, I would say, of course, I gave the presentation where there is a connection if you're changing relativity or expanding it, right? You get the electromagnetic sector pops out, right? So I've given that presentation. I don't know if you've seen it, Michael, but what I'm trying to say, I'm not saying that there is not a connection, but what I'm saying is when you're thinking about the electromagnetic sector, it's going to have its own kind of like degrees of freedom. And yes, I believe it does have the degree of freedom you're asking about. And of course, it's all one field, but the field is more complex. So there's different, the way I think about it is there's different sectors. There's a kind of like the gravity inertial sector, and then there's the electromagnetic sector. and there's
that's just making
kind of
it
like a
harder,
little interaction between
harder
them
for
on
yourself.
one field.
You got to think of like these forces have to unify somehow. So that's in some sense that they have to be the same thing. So where is that connection? And it seems to be with the scalar term and the dilaton, and then the Hertz potentials and the axion, like David Chester's been looking at.
Yeah, well, the thing is, they're one field, right? But that field is more than complex, right?
Yeah, but there's got to be an interaction term somewhere, and that might be it.
If it's one field, then it's a self interaction, right? I suppose.
Yeah. Yeah. So there is an interaction, and that's the trick, right? So, and then how does electromagnetic, the stuff we are familiar with, pop out of that, right? So that's the thing I made progress on. So
excellent.
But okay, guys, I gotta head out. So I just wanted to mention that, and yeah, Jared, I'd be interested in that book as well.
Yeah, I sent it to you in Signal.
Okay. All right. Thank you. You guys have a great rest of your weekend.
See you around, Curtis.
Catch you later.
So Matthew, I was wondering, we got this sampled. Maybe it's just a 7000 series aluminum, but maybe it's from another planet. Who knows? So want to give it a shot with the neutron bombardment or something?
I wish I could. I don't have time. So if you gave it to me now, I would get to it in like a year and a half. Things are so bad. Like, I'm just so overwhelmed. I was just telling Jarod the other day, and like I said were you there for my talk today?
I just arrived recently, unfortunately, but I'll rewatch it.
Yeah, so in my talk, I even said, like, I wish I could look at more samples. I can't. There's no time because it's not automatic. Since I've invented a new, better, ideally, technique for neutron activation analysis, but it's not like I just push a button and computer tells me everything. I have to manually analyze the data to make sure it's correct. Like, someday I want to have an automated software, but I don't, unfortunately.
Well,
So,
I mean, can you like write up the instructions for how you would do that? Because I could probably like make that software in like a week or two.
No, you understand, like, even the act of, it's so complicated. No, you should, like, even the act of writing those instructions would take more time than I have right now.
Oh, man.
I'm teaching 2 classes. One of them is 150 students. Like, the only reason I'm here today, the only reason is because next week is spring break. And so I don't have to teach next week. That's the only reason.
Wow. Well, thanks for all your work and collaboration, Matthew.
Yeah, thank you. I was just so out of it today that I have to apologize. You're going to watch a video, and I couldn't remember. I'm pretty sure it was you, and I couldn't remember your name because I was just so stressed. And I think it was you who gave me an idea about bismuth and metastable states when I saw you in person.
Oh yeah, that may have been, yeah.
Yeah, and I try to give you credit and talk, but I'm like, I remember who it was.
Oh,
no worries. It was the guy on the right when you first walk into Falcon Space. That was you. That was you. Yeah, I think, yeah. But I felt so horrible because I've just been so stressed lately.
No worries. But yeah, let's here's some more collaboration once you do have time in your schedule.
Yeah, I would love to. What I would love to be able to do one day is just create an automated assembly line where you just give me stuff and I just do sample analysis. But there's another issue with that. Even if let's say I had time, magically, I don't have money. So the problem is the californium source that I have, it's dying. It's a 2.6 year half-life.
Yeah.
And soon it'll be completely unusable. It's already on the border. And I got a quote. It's $4,500 for a new source. I don't have that. It's just not happening. That's a non-starter. So if I had money for a new californium source, I would start a whole like factory assembly line where it'd be like, you send me a part, someone sends me, people send me parts, be like, bam, exposed to californium. And then I would just give you a PDF report the next day. Here are the elements, here are the isotopes. Bam, next one. But like, I need a few grand. I just need a new californium source.
Yeah, that's not out of the. I mean, we'll see, but maybe something can happen there.
But no, because nobody could help me with it unless it has to be through the university because it's one of the most dangerous sources. You can't just buy this. Like if one of you guys tried to buy this, you can't. It's illegal because you're not at a university or a national lab.
I have lots of friends at universities and national labs who could get one for their I don't know. There would be some sort of collaboration that would have to come about.
No, but that doesn't work because you're not allowed to transport sources. So basically, if one of your friends got it, that means I'm out of the loop because they can't give it to me. That means they have to do all the work, and I'm out of the loop. They do the neutron. See, it's a really tough problem to solve. It has to be bought through the university. I have to have a grant in the university to do it, and it cannot be shared with anyone. It is illegal to transport, and so yeah, it's a tough problem. And californium is a highly controlled substance. It's highly controlled. Yeah. So, and it's got to be californium, because as we learned, plutonium is not as good. Ambi's not as good. It's got to be californium, and it's one of the most dangerous. What's
the energy level difference between californium and uranium?
Mark, you've asked this like 4 times now.
Well, let's get it on the record.
It's been on the record. They're almost the same. It's always MEV scale neutrons. It's always MEV scale. There's a slight difference. It's in Jarod's talk, and I've also sent you slides about it where like their energy spectrum are covered, but they're pretty comparable.
So Matt, this a technique. It is very sensitive. But what do you do for isotopes that have either very, very short half-lives or that don't have a large neutron cross-section?
Nothing.
Nothing? You just don't detect those ones?
Yeah, you just don't detect those ones. So, I mentioned this in my talk today. Look, there is no magic technique. It doesn't exist. So basically all techniques have pluses and minuses.
Yeah.
And so if you want to do what you just did, we said, what about short-lived? What about neutron? Then you have to destroy the sample. So you have to do ICP-MS, basically, like Arrow did. So if you want to do those things you just said, then you must sacrifice. You got to break off a piece and vaporize it. There's no other technology.
Got you.
Yeah. So with neutron activation, if there's like a millisecond half-life, you're SOL. Or if there's not a high neutron cross section. But see, this is again what I meant is I can't just tell you, oh, here's what you do in a week. You're going to help me write code. That's just not happening. Because you would need to basically download every single neutron cross section database as a function of energy for every single isotope, not element. So that's several thousand. You'd have to digitize all those plots. You'd have to stick it into C++ or Python or whatever. This is a multi-month, multi-year effort. There are no shortcuts. ChatGPT is not going to give you code for this.
I was hoping that such a database was already digitized.
Those databases exist, but it would take a lot of time to make sure you put the data in right and you uploaded it right. Yeah. And so I've been doing this for the past few years, painfully, slowly on my free time because I got to work on my funded projects on dark matter. Although, thanks to Trump and Musk, I might be out of a job this summer. So we'll see if they don't unfreeze my grant. Yeah. So
then you'd have more time to collaborate with us.
But then because then I'm moving my house because I lose my home because I can't afford the mortgage anymore. So unless President Trump decides to unfreeze my grant, I'm taking a $20,000 salary cut this year. Yeah, my wife's really worried. Like it's bad.
Yeah, they shouldn't cut the NSF stuff. That's just dumb. Like,
no, I'm not NSF. I'm not NSF. I'm DOE.
It's
even dumber.
That's even dumber.
Yeah. Department of Energy. Like it's dumber. Yeah. Like, what did I do wrong? Like, I'm a father of 4. I don't do any woke DEI anything. I'm a white male. Like, why am I punished? Like, why is my money being taken away? It makes no sense.
And in terms of like competitiveness with like China and like Russian places, like that just knocks us down a peg.
It does, because now the European and Chinese dark matter experiments are laughing their asses off. Yeah. Because I'm frozen. Like, it makes no sense. Like, I didn't know making America great again meant like destroying it from the inside. Like, it's starting with science. Like, okay. Well, like, I
so
don't
are you saying that cold dark matter research is freezing in its tracks?
Yeah, it is here, not in Europe, not in China. You know, if I was China, I would be so happy right now. I'd be like, yes, let Trump destroy the U.S. If I was China, I would be so happy right now. Like, they think the tariffs aren't going to do anything. Instead, science is being destroyed. So,
well,
whatever.
Elon's style is to kind of overfire people and then rehire. So
Yeah,
hopefully things will come back.
I hope I come back. I hope I'm one of those like, oh, sorry, you're good. You're
Well,
good.
the challenge is then like all these people who have to like move because they lose a mortgage or all these other things.
Exactly.
And
Yeah.
then like,
Yeah.
what do you? Those people can't necessarily come back. They might have moved on by
It's
that time.
it's so friggin' easy to fall off the wagon in this culture too. You know, you're
Yeah.
well-to-do scientist with a federal grant, and a year later, God forbid, you're homeless and you can't get your stuff back together, and that's
Exactly.
really crappy.
Yeah, and then they're like, oh, here's your job back, and it's not gonna. Genie's
Like,
not
I
gonna
can't
go back to
actually
normal.
do this anymore because I don't have the stability necessary to muster.
Yeah, exactly. So it's a very difficult. It's going to be a difficult time.
If I don't have my money back by August at the latest, I'm screwed. I would have to sell my house and find a crappier, smaller house, and I've got an amazing house.
Well, Tim, make sure to take a short for this and send it to Trump or something, or Elon. This is important. This is important stuff, you know, like.
It's not political. I'm just talking about this specific policy. I'm not getting into any other policies or conservative versus liberal. It just doesn't make sense to punish people like me who are not doing anything controversial. Again, I'm not doing anything on climate change. Like, it's not logical. The DOE
is allegedly hiding a lot of the like tech that's been discovered over the years we're trying to reinvent here.
Oh,
allegedly, but like you don't take a big hammer to that. You go through it with a fine-tooth comb, you know.
Yeah. No, I know
that's my only problem with it. In principle, it's like the idea of cutting government. A lot of people think the government should be more efficient, but you make it so with a scalpel, not a chainsaw.
Oh yeah,
exactly. Yeah.
Okay. Well, yeah, and I promise you, one of my tasks tonight is, since we're in open discussion, I'm migrating from one OCD project to another right now. I guess you guys are too, so I'm in good company. But so one of the things I've been doing is making lots and lots of video shorts, and it's demonstrating all the weaknesses in my system, and one of those is like my backups. So I'm putting new backup stuff in place. I'm organizing all my files, all that kind of stuff. But it's pretty cool. I'm leveraging YouTube Shorts now. I'm growing out 2 or 3 new social networks, and there's some interesting stuff happening. I mean, this is kind of off topic, but for quite a while, UFO Twitter was like the mainstay, and it's kind of been quiet lately. I mean, there's still people posting big tweets and stuff, but I'm starting to build out over on Blue Sky, and it's kind of a more supportive community. It's kind of like less hate-filled. You know, so
I have had. I'm not even on Twitter, and I have had so much hate directed at me when I'm not even on there. But I'll be named and be like, with my name, of course, terribly misspelled, like that Szydagis guy doesn't know what he's talking about. Blah, blah.
Half of those are probably bots, Matt.
Yeah. Oh,
sock
puppets. Yes.
I can tell you that the issue that I'm running into. So I do pretty much all of the social networks, and in fact, I could show you my. You know what? Maybe I'll pull up my link tree. Do you guys want to see my link tree?
Oh yeah. Well.
Yeah. Hold on. Okay. Here we go. I will share this. This is not self promotion because you can't actually click on any of these, but it will be interesting to kind of see. So this is what I'm rolling with right now. I've got my website. This is my YouTube channel, podcast. Then Twitter or X. I haven't updated it yet. LinkedIn, Facebook, Instagram. I got the Flickr, which technically is a social network, not really. Of course, I've got APEC, and then let me see: Threads, Mastodon, Blue Sky, Pinterest, and TikTok. So I've got a lot going on.
With all that social media, you got to automate that, I guess.
Where's
one of the reasons
you're missing Truth Social?
Okay, hold on. You know what? I was on Bernie's channel last night, and he was talking about what's the other one that goes with Truth Social? It's like the YouTube for Truth Social, Rumble.
Oh, okay. Yeah.
I've never heard of it. I've never heard of it.
Now, is a link tree like to replace the web SEO functionality of a website, or is it just another place to put a website, or another
It's,
place to
you
put all
know,
the sites?
I started using it. So some sites, YouTube is an example. YouTube lets you put multiple links in, but they're only going to show your first link. And so YouTubers use it, but then a lot of sites like Instagram only lets you put one link, and so the idea was you've got all these different social destinations and different people want to see different things. So you use Linktree as an intermediary. So they go to Linktree and then they can go to any of your others. I have one for Alt Propulsion too. I created a Linktree just for Alt Propulsion. And if you go to the Alt Propulsion YouTube channel, you can, in fact, well, yeah, I won't get into that right now, but that's a whole nother world of hurt. So yes, I have lots of social stuff I'm managing. And what I'm seeing is that because the new administration, people are hating on Trump, they're hating on Elon, they're hating on each other, and it's just like impossible to get people's attention because it's so filled with just like political crap, So
yeah, for the next couple of weeks, I'm just going to read a book and not go on the internet. I think that's wise.
How about do that for the next 4 years, just to be on the safe side?
I think in 2 years we'll see.
To try to steer the conversation away from the last 20 minutes that's been kind of political. Matthew, do you think that paper that I was talking about, that with the 32 authors, the mega UAP study that you and Dr. Knuth are on with 30, can you talk at all about parts of that like stood out to you that you think might be useful, engineerable data somehow? Like I identified the Hull temperature, but are there other things?
Yeah, that's an excellent question. But first, I should say, before I answer that, I really did very little. This was Kevin's brainchild. My brainchild was the UAPX paper, although Cecilia, Kevin also contributed, and my crash paper, which I wrote by myself. But really, this is Kevin's brainchild. So you shouldn't say Kevin and Matthews. I contributed almost nothing because I was too busy. I can't even take the aluminum, from Michael. I would love to, but I'm just so overwhelmed. But to answer your question, I literally didn't help write the paper, but of course read it. I'm a co-author, so I'm not gonna not read it. I read it for cover to cover. It takes 10 hours because it's so long. It's really not focused on engineerable things because it's really about the history of the field and what people have found, like what observables people have seen in all of the instrumented studies that have been done over the years. But it tries to, especially many places, take a more agnostic approach and not necessarily talk about engineerable things because, again, we got to be more neutral and balance the scientific paper and say, look, on this call, all of us know there's a very good chance it's aliens or some side of craft, right? But the thing is, you can't really say that. And we do say that in the paper, but there are also sections we kind of stay away because, it could be atmospheric phenomenon, whatever. So off the top of my head, I can't really... because we wouldn't even know. We see high speeds, we see high accelerations. They're mentioned in the paper, but how would you, what would you engineer, from that?
So like Dr. Knuth, took a look at Ray Stanford's beam ahead image, and he's like, "Oh, that's an ion beam. That's excellent for doing this, right?"
Mm-hmm.
Or the Faraday rings. Oh, that has probably a magnetic field strength of this. Like those are numbers. You can use numbers.
No, we're not allowed to talk about Ray Stanford. Because we'll get attacked immediately. We'll just get raked over the coals and dragged through the mud. So that Ray Stanford is that is not a permitted topic.
Aside from his stuff, but hard numbers that you can calculate, like he's done with the accelerations and.
But that's not the point of the paper. For those kinds of things, we'll have miniature separate papers, like Kevin's entropy paper. That's not the point. It's basically, it's a historical overview where if you want those kinds of details, you need to go to the bibliography of the paper and read the individual references. Because if we actually did, as you say, then it would be 1,000 pages. Okay, then it's not a paper anymore, it's a book. It's already a book. But
it's 158 pages, yeah.
It's meant to create a central web where you use the bibliography, you can go deeper into each of the things that Kevin and the authors mentioned in the paper. Yeah, I'm sorry. I wish I had a more solid answer for you, but we couldn't go into to go into the things you're talking about. It was considered going into the weeds, and we wouldn't be able to go into that kind of depth. The purpose also, we wanted to legitimize the topic because it's going to be in a very high impact peer-reviewed journal. And so that's going to help legitimize the topic. I don't know if you saw, there was an article about it. I don't remember if it was Popular Mechanics or if it was, it was phys.org. Phys.org had an article about it. Kevin was like thrilled. He was over the moon.
I'm amazed that they would publish anything UAP. Like, they're so. Like,
I know. I'm dropping the link in the private chat right now. There's the link.
And guys, we got about, let me see, it's 5:30 now. Should we close things down around 6 tonight?
I could go a little. I was going to head out soon, actually. Yeah. So, I mean, maybe not even half an hour. I don't know.
Yeah, it's 8:30 for me, Tim. So it's like we're dying here on the East Coast already, falling asleep.
Oh, well, and you don't have to. You do not have to stay. You know what?
No, but I want to stay.
I genuinely.
Michael just got here. Can't wait.
I am so thankful that you guys were able to present today. I mean, words cannot express. I'm so appreciative, and I think that we've done just hitting it out of the park, and my hope is to get that research out there. And then what Mark is working on, man, I mean, he just upped the game there, you know? So,
but
I mean, all of you guys are kicking butt.
I feel so bad because I warned Mark, that part is toast. Okay, nothing's happening with that terahertz laser. I would bet my right arm and my firstborn that zilch is going to happen because I toasted the source. But to be fair, Jarod knows this, and you too, Tim, because you're copying on the emails. What did I say? 6 months ago, I said this should be the last or second to last test. Don't plan any more tests. And now you got XRD, you got this, and no, the sample's dead. I killed it. Okay, it's very dead. It changed color, for God's sake. It's dead. That terahertz later isn't going to do it's not going to do shit.
It'll buff out.
I broke it.
Yeah,
it's fine, dude. Just because you left it sitting on a pile of plutonium for a month. That doesn't necessarily kill it.
I mean, any normal human electronics would be dead.
But maybe it's like Ninja Turtles.
Or maybe it's better. Maybe it'll work for Mark now because I made it better. Who knows, right?
Just needed a juice up of radiation.
I just needed a little,
I don't know about that.
It needed a little je ne sais quoi. It's just I don't know.
But Jarod relayed to me. He emailed me a couple months ago when you took it off the plutonium, and you're like, "There's nothing there," and I'm like, "It's been sitting on a freaking slab of plutonium for a month." That's the scary part.
It makes no sense because
it doesn't make any sense. There's bismuth in there. There's bismuth in there. That should definitely get neutrons.
Yeah, and the thing is, it's not plutonium. It's plutonium beryllium. So specifically, it's an enhanced neutron source because plutonium mostly makes alphas, actually, not neutrons. But when alphas hit beryllium, they make neutrons. So, and it's sitting in a vat of beryllium. Mark was there. Mark took photos. It was a vat of beryllium this big. Do you know how many neutrons that sucker? Beryllium is a neutron reflector. And so neutrons should have been coming back in through the sample over and over again. We took it out and it wasn't radioactive. I'm like, the hell is going on here?
Yeah, that was very bizarre. I have to admit that's a really weird. Yeah,
it's not
but
normal.
if it's shielding, if it's some kind of space shielding, which you'd expect on a UFO.
Yeah, it's just
or
bismuth would have turned into polonium. You would have definitely seen the polonium.
I know. I should have.
Yeah,
I do see it with the californium, but not with the plutonium. And even with the californium, it barely works with the californium. Barely.
Let me throw something out there, okay?
Oh, the californium source was dying though too, so that's a factor.
Well, but if I take that's why I tested other samples. The californium is still strong enough to activate the crap out of anything else. So
that is very strange.
It is, yeah. But Jarod wants to jump in with something.
Go ahead.
Yeah. So radiation is a function of time, right? And how radioactive this thing is getting is a function of time. And your experiment, we're having a real hard time figuring out what could possibly explain how this thing can be exposed to so much radiation and yet not demonstrate that it has been. One thing would be if its time function is changing in the presence of a very strong radioactive source. If there's some magical, drink your Kool-Aid magic where this little sample with the right radiative stimulus ends up reacting to that stimulus at a different rate in time. Right?
That's Interstellar. I just watched that. I just watched Interstellar.
So if it's sitting on the block of plutonium for a month and it has the same amount of radioactivity when you pull it off as if it had only been sitting on there like a fraction of a millisecond, right? That would be like it experienced time at a different rate while it was sitting in there.
No. I don't think we need to go to. There are more prosaic explanations that could explain it more easily than that, actually, because what you could have happening is that it's made up of a certain set, just the right set of isotopes, where it's got an overabundance of short-lived isotopes, and so they're decaying away faster. I think that would be a much more prosaic explanation before we go into time, warping or whatever. But I'd love for you to be right, Jarod. Don't get me wrong, but I just worry that Occam's razor. There are much more mundane explanations for what.
Well, one thing I've been looking at recently is nuclear vibrations. If this device is indeed a terahertz waveguide and you can get some coherent phonons in this thing, or at least polarized phonons. Those can interact with the nuclear vibrations, and maybe that's changing the neutron cross sections.
I don't know. Yeah, I don't know. Or actually, so my favorite explanation that I only touched on very briefly in my talk is that there's no new physics at all. Nothing. It's simply what we're seeing is the product of something that is beyond the best current human supercomputers. Because imagine if I had an infinitely perfect, if I had a hyper quantum computer, I would be able to ask it and it would tell me what is the best material for different kinds of radiation shielding. Right now, you can't do that because it would take, all the supercomputing power of the world. You just have to guess and check. It's like drug discovery, right? Or proteins and things like that.
I would argue that even being able to properly set up the query would be a challenge for that sort of question.
Yes.
So
exactly.
Even if you had the computer, like the quantum computer, then you would need to know how to set the problem up, which is not necessarily trivial. But go ahead. Continue.
Yeah, no, exactly. No, but what I'm thinking is that there's no new laws of physics, but what the art part represents is absurdly intelligent, clever engineering that would require the right query and then even thousands of hours of the human best supercomputer to do. So you were asking about the query. I don't mean this as a prideful way. I try to be humble. I think I could set up the right query to do this. It's the kind of thing I do all the time in my field of study. The problem is there aren't enough supercomputers in the world that would be able to answer my query, which is how do you put the right isotopes together? And so what I'm thinking is happening in this material is it's just using the known laws of physics, all standard neutron cross sections, but it just so happens to be the right elements and the right isotopes and the right ratios where they pass. It's like hot potato. They have the right combination of cross section to pass neutrons around between each other and lower the energy more effectively than anything else we've come up with. Because that's what I think is happening. And I'm going to test that idea because I can simulate the part now. I can simulate the art part using Jan4, which is the world premiere, like this is what they use at the LHC. And turns out I'm one of the experts in Jan4, like from the last, I've used it for 2 decades. The computer, the only computer where I had Jan4 working, of course it broke. It died. And so for months now, I've been desperate to. First, I was trying to get the data off the hard drive. I had to go find it. It took me 3 weeks to find my backup. I finally did. I just haven't reinstalled Jan4 anywhere, but I wanted to test the neutron shielding idea. It's totally testable. I could simulate like a block of arts parts, like take arts parts and make like a meter block of it, fire neutrons, fire different kinds of radiation into it, in simulation. Because the beauty of a computer simulation like Jan 4 is it's very robust. Like you can trust its predictions. I use Jan 4 to predict what I'm going to do, and then I build it in the lab, and guess what? It matches like within 10%. So it's a very, very powerful software. So nice. I want to test whether is this actually neutron shielding. And then Kevin Knuth gave me the trick. He goes, you don't need supercomputers. You already have the answer. His idea was just take Art's part, model it, and then take every isotope, make it a little higher, a little smaller, a little higher, a little smaller, and prove that it's the optimum. And I'm like, Kevin, you're a genius. If you already have the answer, all you need to do is work backwards, and that's way easier than finding in the first place. You see what I mean? You just take every component and say optimum. It's like a recipe. It's like a recipe. Add more sugar, take out sugar. Add salt, subtract salt. So his idea is if this is truly some alien's perfect recipe, prove it by adding too much of one thing and taking too little. And I'm like, damn, that's a great idea. Again, if I had time, if I could just make my students go away, if I could get a new job where I'm just paid to do this, I would do this tomorrow if I could.
You got to get a student with an independent study project or something. Or
I can't. I do have students on independent study projects, but they're on my dark matter project, the funded project.
Darn.
So, Matthew, I wanted to be able to finish up that thought with the whole time aspect, because I try not to bring things unless I have at least 2 data points, right?
Okay.
So I don't even know if this is a data point, but it seems like it might be. That's why I wanted to run it by you. So in addition to the radiation thing, when we look at Dalnegorsk versus Art's parts, and we assume based upon the number of overlaps I've shown that they might be coming from similar craft, the other part of it that maybe could relate to that is the elements. Instead of looking at what's the overlap, look at what parts are unique to one versus the other. So for the Dalnegorsk, right now I'm on this row here. There we go, this bottom row. The ones in white are the ones that are in Dalnegorsk and not in Art's parts. So
we're not seeing what you're seeing, unfortunately.
I think we have to wait until Tim actually.
No, I think you can just press present.
I did, but there we go.
Yeah.
Okay, so whoops. So let's see if I can.
This is really tiny. We can't read this.
Let me.
And I'm over 40 now. I can't read anymore. I need to put my glasses up to read.
Is that more visible?
Slightly. Yeah.
Okay. Let me zoom even more. Is that better?
Sure. Yeah, I mean, I can read it.
Yeah, I can see it.
Okay, so in this row here, see if I can make that a little easier to see. There we go. So in this row here, this is the combination of Art's parts and Dalnegorsk's elements. And I was saying that the ones that are unique to Dalnegorsk are in white. So if indeed they come from similar craft, looking at what's unique to one versus the other might shine some more insights, right? Because if they're similar craft, what could possibly cause one to have so many differences, right?
Mm-hmm.
So the ones that are different tend to be very near neighboring atomic weights. So we have scandium is in Dalnegorsk, not in Art's parts. Silver, silver is in Dalnegorsk, not Art's parts. It's right next to cadmium, right? Lanthanum, right next to barium. Samarium, I don't know. It's kind of halfway in between neodymium and thorium, but rhenium?
We have rhenium. Remember in my talk today.
Wait a minute. Am I in the wrong?
I sent you a few weeks ago the
X-ray
results. There is rhenium.
I put it all in here, but I must have gotten this.
But
it's interesting that there's such they match up so well. That's very interesting.
Yeah. No, but
where was the Dalnegorsk thing found again? I don't recall.
That was in my presentation. It was 1986.
Oh, where, not when?
Russia.
Okay, that makes it a lot more interesting because my my initial hypothesis for the arts parts was that it was just a radiation shielding for a nuke test in New Mexico, but like if it's a sample in Russia, that's different.
And
yeah,
this was
exactly
like this was a tiny town of like a couple hundred people or less that was like way out in the middle of nowhere in the mountains and like right up on the mountains.
So
this was just like right up the hill, and they all saw it crash.
That's really interesting.
But wait, Michael missed my talk. Michael, actually, I had no idea you had that hypothesis. That's exactly what my colleague Cecilia said, and my student Andrew. We came to the conclusion it's probably an atomic bomb casing from New Mexico. That's what I said.
Yeah,
today.
Yeah.
I had no idea.
A while back, but
no, but it doesn't.
That is the most prosaic explanation.
It is,
the fact that there's one in Russia too, in a random small town.
Yeah. No,
That's
but also, Jarod, are you
Well,
mind?
you could probably look that up. You could probably see what the shielding used.
Yes, and it does not match. It does not match at all. And I double checked that with Eric Davis. Yeah. And then, and also, why would Arrow be playing dumb then? They would just say, "Oh, it's an atomic bomb."
I mean, I think most of the shielding we use these days is like tantalum based or something.
It's definitely not this. But wait, so Jarod, are you ready to get your mind blown?
Please.
Yeah, those elements you think are discrepant. Yeah, they're probably not. I wasn't ready to say it today because I'm not 100% sure. But everything you have in white, I think there's traces of them also in the art part. It's just there's such small traces that I didn't want to get out over my skis, so to speak, and I didn't want to claim it's there. But like they keep coming up again and again, and I'm like, is this real or is this a false positive? And every time I think I have a signal that's not there, you then come along and give me evidence it might be real. But some of those I can explain, like the scandium, there's a prosaic explanation. You're saying how they're right next to each other. There's a very prosaic explanation for that. No, if you hit upon that's what radiation activation will do. It moves things up and down the periodic table +1. And so actually, I think I saw traces of scandium, but I didn't put it in the list. The reason is because I thought, well, there's definitely titanium. I have a gigantic signal from titanium in the art part. Huge. I don't think titanium's even mentioned in the Arrow report. I got a giant signal from titanium.
Cool.
And scandium is right next door. And so some of the scandium signal might be an echo, in a sense, created by the neutron activation. That wouldn't explain why it's in the part that hasn't been neutron activated unless it's a bomb casing. But then, like Michael said, why the hell are the Russians using identical to American classified bomb casings? That doesn't make sense.
Well, so that allegedly the classified bomb casing would have been from the Roswell crash, which would have been some sort of nuke test or something, maybe, that was like 1940s, and then this was 1980s, so there would be plenty of time for the Russians to potentially get their hands on that technology.
Okay.
Well, but that's a stretch.
Yeah.
I mean, so there is a way to say, okay, maybe it is still a bomb casing thing, like a neutron shielding component, but even then.
What about the gold micron mesh that they found?
Well, I'm just saying that it's more of a stretch to say it, but like the bomb casing hypothesis isn't completely out just due to the timing of these, but it is very strange that it just shows up like that in Russia in a completely different circumstance.
And I wish I knew.
Actually, how far from that was Ukraine? Because like the Russians, they tested most of their nukes around Ukraine. So how far was that from Ukraine?
That's a good question. I'm not sure what method they used to identify the elements in the Dalnegorsk. I got all of those elements from the book that I shared.
Oh, okay. So then if it could have been neutron activation analysis, in which case some of those signals are fake. So like scandium was created because there's so much titanium in the sample. You got to be careful.
So one of the other important things about it was they said that they did some vacuum tests on it where they put it in a vacuum furnace. And when they did that, they lost some elements and they gained a bunch of other elements.
That doesn't make any sense. To me, that means their furnace was dirty. and it's a very bad test. Yeah, that's it's either that or it's magic. I'm sorry, those are the two possibilities.
I choose magic.
I do not choose magic. I think it was a crappy Russian oven.
Or it was aliens, like Giorgio Tsoukas just said.
I think the hypothesis that it's a messy oven is probably the right one in this case.
Yeah.
Well,
I'm looking it up now.
But it's still interesting that you. Okay, so Dalnegorsk, I just looked it up. It's definitely nowhere near Ukraine, so it's unlikely to be a Russian bomb test.
Yeah,
so
it's like
very interesting.
really. I think it's Eastern Ukraine. I mean, Eastern Russia.
Well, that's what you think.
Western.
They want you to think.
No, oh yeah, Eastern. Yeah.
Or the atmospheric bomb tests in both cases knock down something else.
No, but guys, I think you're missing a big picture here that Tim was saying earlier, which is let's say for the sake of argument, classified bomb casing that we're not meant to know about. Well, guess what? We just solved nuclear fusion power plants, right? Because if it's neutron activation resistant, we just solved the 30-year-old problem, which proves, by the way, how dangerous it is to overclassify things. Because if this really is a classified nuclear bomb casing, it's kind of shitty that the U.S. government had a solution to nuclear fusion and the people working on fusion weren't allowed to know. That's really shitty. Right?
Yeah,
the
one thing I would say is like maybe it's good against neutron activation, but magnesium and bismuth, that's going to melt at a super low temperature.
You could ask. I mean, we could. You mentioned Eric Davis. We could also ask John Brandenburg. He worked with bomb guys, and then, but another thing that kind of runs against that is, in terms of sharing that kind of information, if they had something like that. A lot of the guys who worked on the bomb worked on fusion reactors. That they were part of the same culture, right? Just
it doesn't make sense. Yeah, but also there's another issue, which is why would you need this kind of great shielding? We didn't give a damn about safety, about like the safety of people moving a bomb. Like we didn't care about why would we have this like super good stuff? We would just slap some lead on it and call it a day, even though I was just making fun of Jarod again that lead doesn't work for neutrons. Seriously, that's what we would have done in 47. So even if this is a bomb casing, it's too advanced.
Are you familiar with the hafnium controversy?
No, I'm not.
Yeah,
yes, I am.
Bomb.
Yes, I am. But I don't
nuclear
remember
isomers.
What it is.
Okay,
yes,
so
nuclear isomers.
Yes, I remember now.
Nuclear isomer gamma ray lasers.
Yes.
So if you want to increase the capacity of the warhead, you might make a shielding around it, which once irradiated with a large amount of neutrons, sends that flux back as coherent gamma rays into the center of the thing.
But it's controversial because there are people who say it's real and say it's not, and it's kind of
so some of that was the fellow who was shopping that around. I've read up on that story, but it's been a while. The guy who had that idea shopped it around the DoD, and they got excited about it because it opens up this whole new range of like intermediate power nuclear weapons. But but then at the same time they had some absolutely ridiculous ones. The worst was. Sharon Weinberger covered this in her book. She wrote a book on it. It was called Imaginary Weapons. And he had a slide deck that he took around D.C., and one of them was a nuclear hand grenade, right? Which, and it's like, you think about that for about 10 seconds, and it's like, oh, God, okay.
No,
it's not possible, but I will tell you a suitcase nuke is absolutely possible. Absolutely, but it would require californium, that dangerous element that I was
Well, they had those. They had those. This is if you're ever feeling bored and you want to relive sheer terror, look up the nuclear, look up the atomic age in the 50s. They had backpack nukes. They trained Navy frogmen, and it was a one-way mission. The idea was they would swim these up to the hulls of.
I was just at the nuclear museum in New Mexico.
There you go. Okay.
It's duck and cover. See, it's a duck on the.
Yeah, they had a bunch of different. They claimed they weren't, but they were suicide weapons. The other one was the Davy Crockett, and that's in Wikipedia. It's well known. You guys have probably read about that, right?
I saw it at the museum.
Just look up Operation Fractured Jaw if you want to not sleep well.
Yeah. Well, Jarod,
Jarod has got his hand up. Yeah.
Yeah. Tim, can you allow me to share screen?
Oh, yeah.
And if anybody was worried about being on a government watch list somehow, don't worry about it anymore. The answer is yes now.
Oh, I'm already on every possible watch list with all the stuff I do with radiation.
Is this big enough to read?
Yes, it's very clear. Yes.
Okay. So what's super interesting about this, just at the very beginning, they say that the metal fabric stuff, that it was resistant to all types of acid. That actually lines up with another sample owner tester that I'm in contact with. This guy was given a piece of a sample by the head of MUFON up in Washington back in like the 70s or 80s. And this guy's like a chemist, and he did all sorts of tests to it. And he said he tried everything in the book to destroy that sample. And the only thing that made it do anything was, I think, Brown's gas or something, he said. So it's interesting, the little bit of overlap there where they said that they did the same acid test that he did, and like he couldn't get anything to do.
I can assure you that the art part is destroyable.
Oh no, I believe that.
Yeah, they vaporized it at Arrow for ICBM. Yeah, it is destroyable.
What I'm getting at though is that Art's parts is not just the layered material. There's also blocks of aluminum that were included with it as well, which according to Linda supposedly are doped somehow with iridium. Now I don't know.
I want to get my hands on that because I can prove right away with neutron activation analysis whether there's iridium or not. Trivially,
if there is, so what she
if there is, it's extraterrestrial.
She was saying that somebody approached her after one of her conferences in like early 2000s, I think, and that person proved to her that he had worked in S4 for like forever. So she was confident in it, and he told her that he had like a 3-foot long section of that craft, and that it was, the double layer thing with the outer hole being the layered material, the inner hole being the aluminum. And he said that it was only when you activated the iridium in the aluminum that the two halves would work together to create any kind of meaningful effect.
Send me a piece. I'll put it in the queue with Michael's aluminum, and we'll just put it in the queue and like, just send me a piece. See, there are all these stories, and they're always trust me, bro. I want physical evidence.
I know.
Me too. If you wanted to make somebody think that something was from off-world, couldn't you just go and scrape the KT boundary for some materials and mix it into whatever you're doing and throw off some scientists?
You could, but it would not be cost-effective. And it would be really weird.
It'd be a really expensive hoax, in other words.
Yeah, exactly. Expensive hoax. That's what I said in my talk.
You
can never rule out expensive hoax. It's like Contact. You remember in Contact the movie Contact, where they accused the billionaire of hoaxing the aliens? You remember that? But then there was lost time. There was lost time proved it at the end. Yeah, with the static. Yeah.
But still, everybody on the planet hated her.
Of course, yeah.
But talk about expensive hoaxes. Do we want the Mexican ETs? Are there any mummy fans around here?
I know a lot of people who are true believers, so people get really angry when I bring this up. But like, it's a hoax, but it's a very good one. It's
super elaborate. They did a really great job.
It's very elaborate. But like, 30% of the DNA is lima bean. I was talking to Dr. Mike West about it. Yeah, it's clearly, and in fact, Eric Davis. Okay, the Eric Davis, right? UFOs, telepathy. What does that guy work on? Eric Davis sent me as a joke on Signal, Spirit Halloween. You know, those memes, costume, alien mummy, and it had like all the ingredients. And I'm like, if Eric Davis says something's BS, okay, like that should tell you something. That's like Hal or Travis telling you something's BS.
I have a question though.
Yeah.
So do you know how many mummies? Not the little shitty thing that they showed, but the actual real full-size one with like eggs and embryos in the eggs and all that stuff. Do you know how many of those that they have now performed tests on?
I do not know. Some might end up being real, but I'm super skeptical.
It's like over 30 now.
30? And are they? All right, so somebody went through a lot of trouble.
What I'm getting at is what happened with that story is at the beginning, it was released in a way that everybody just laughed it off. And from what I've seen, whenever you see something that's immediately dismissed, you should be a little curious. You shouldn't believe everything, psychic space wavos, not necessarily. but
Dude, that is, you know what? That is a band name. That's a band name. That's,
I know. Can we
band.
start a band called the Psychic Space Huevos? Yeah.
But the follow-up analysis that they've done regarding like open source science, like they've been great. It hasn't been just a here they are and we haven't done anything, or here they are and here's a bunch of really shitty data. No, they have released like super high quality CAT and MRI and other stuff. Like it's impressive.
But even GN, you know who that is? You told me not to say his name. He says that he thinks the mummies are crap, and he tested at least some.
No. That was the little one. That was the little one.
Okay.
Once again, anything that's shorter than like 3 feet, I would completely disregard. But the 5 foot tall ones, of which I think it's like 15-ish of them are that big. Those ones, like it is very worth people's time to give the larger ones, especially the larger ones that have metal in them. That's also kind of interesting. Plus, especially those embryos that are inside these eggs that are inside their center, and there's no, there's enough of it there that it's worth the time to give it at least an hour.
Unless it was built from those embryos out and layered like that.
Kevin Knuth always gets mad when I talk ill of the embryos, because he meant, and not the embryos, I mean the mummies in general, because he doesn't mention like the osmium and like metal implants. But here's the thing, Jarod, if there was a there, we would do a neutron activation analysis and prove the isotopic ratios are extraterrestrial. It's as simple as that. And so you're going to show me all these tests, but guess what? Zero, were any of them NAA? If none of them were NAA, you can't conclude anything was extraterrestrial.
I wonder if we might
should
be able
do
to
that then.
So here's how this goes. I already was put in contact with one person connected to the study on that.
Yeah.
How this could go is if we could make a contact down in Chile. I don't know if they have states or whatever, but in the area where they have the mummies and they're doing the testing, if we could make a contact down there that has a radioactive source, we could take one of the not the cosmic watches, the nice one of the scintillators. We could take a scintillator down there. We could do, because you can't, the Chilean government has been blocking all attempts to send these things outside of the country. The Chilean government will not allow these to leave the country. So if you go there and you're friends with the scientists there and you say, hey, here's a test we can do in like a couple days, like that might actually be a thing that could be done.
And then you've got radioactive psychic space huevos. That's even better.
It might.
The real.
Can you bring?
Are they going to have a California source? They're not going to have a California source, Jarod. So the thing is, the California source I own is at the limit of what's legally allowed in the majority of countries. I'm sure there's too. Like they wouldn't even have the Californian there to buy. So it comes from a German company, and they don't sell to every country either. And like I said, it's $4,500 at current rates. So are they going to have plutonium or Californium? If the answer is no, then we can't do it, right? They'd have to break off a piece and send it to me, which you just told me is illegal. So again, see, the problem is just human laws and just stupid things like this prevent science from getting done.
Well, guys, on that note, we just passed the 6-hour mark. Why don't I shut things down for today? This has been, thank all of you. Thank you guys again. Wow. Wow. That's all I can say. You guys knocked it out of the park. Home run after home run after home run. So thank you so much.
Thank you, Tim.
Okay.
Thank you, Tim.
Yeah, so this has been APEC for March 15th, 2025. Signing out. We will see you again next month, guys.